give their practical experience how to get a structure from images. Ali, it's all yours. Thank you.
Thank you so much, Bob. I'll just start sharing my screen in one moment. Can someone confirm that the screen can be seen?
Yes, we're seeing the screen. Thank you very much, Ali.
Excellent. All right, well, welcome everyone, and thanks so much for joining us today. And thanks to the organizers and everyone who's put this workshop together, and especially to Dr. Jerose for the very insightful and useful lecture this morning. I want to give a specific shout out to Professor Wachu for inviting us to do this workshop today, and to all the participants and viewers who are watching with us. We're very excited to be here to talk about CryoSpark and how you can use it in practice for single particle reconstruction. And yeah, we'll be very happy to answer questions and explain absolutely as much as we can. Just to give a little overview of what we're planning to do today, this workshop is a little bit of a long one, and we're going to be going quite in a bit of detail. Today's session, well, overall, we'll be focusing on the theory, algorithms, and practical aspects of single particle data processing in lots of detail from end to end, from raw microscope data all the way to refined 3D structures. We'll be using the latest version of CryoSpark, that's version 2.15 for the actual tutorial. There will be approximately 60 practical participants who are using Stanford Slack compute resources to follow along with us with the practical using all the data sets that we've prepared. And of course, many remote viewers who will be can also follow along. We'll also be doing a demo of all the data processing that we're asking the participants to do on my screen here. So you'll be able to see exactly how things work. And this whole video is also going to be recorded to be available later, along with the slides. The webinar portion that we're using right now will be used, Zoom webinar rather, will be used for lecture and demo presentations, as I mentioned. That's for all viewers to see. There are also going to be some times during the day today and tomorrow that will be reserved for meeting times, where we'll switch over to a Zoom meeting that will be interactive question and answering for practical participants only. But at all times, please, all viewers, feel free to ask questions via the Zoom webinar Q&A feature that's now being moderated by our team members, and we'll be trying to answer as many questions as possible. We've actually set out specific times at intervals throughout the presentation for answering questions, so we're hoping to get through a lot of them at those moments. And for practical participants, if you have any questions about the computing system setup, being able to log in, etc., those can also be asked via Q&A. The Stanford team members will be able to answer those, and we can also take up those questions during meeting times. Before we actually get into the whole presentation and practical, I just want to make sure that all the practical participants have tried and are able to log into your CryoSpark instances that are hosted on the Stanford servers. So please take a moment and read these instructions. It's hopefully relatively easy to log in. You've been sent an email already from the Stanford team with 2 usernames and passwords. The first one is an HTTP authentication username. When you attempt to go to the particular CryoSpark instance that you have been assigned to, which has also been listed in your email, you'll be asked for that username and password first. And there you can put in the first username and password. Once you enter that outer authentication, you'll then be greeted with the CryoSpark login page where you have been given a participant-specific CryoSpark username and password. So those should be used for the second login. I'm going to leave this page up for just a minute or so that if anyone needs to take a screenshot or if there are any questions that come up in the Q&A immediately, we can address those. But hopefully, relatively quickly, everyone should be able to log in.
Hi, everyone. This is Sarah from the CryoSpark team. Ali, sorry to be raising a technical issue so early on, but I'm actually not able to see your screen at all. And I think we might have a couple of other people on the call who are in a similar position. Would you mind resharing?
Sure, I can do that. Just give me one moment. Can you see the screen now?
I cannot.
Is anyone else able to see the screen?
There are people that can. I can. Yes, there's a lot of people that are saying I can see the screen. Some people said that they had to log out of Zoom and back in again. They themselves, not you, they had to log in and until I left the meeting and joined again. So there are apparently some people that need to log back out and in again. I'm sorry, but it looks like people who log out and log back in again can see the screen, in addition to other people who never lost it in the first place. So I don't know. Okay, anyone who cannot see
I
the
will
screen,
take that.
try it again. Remember, Joanne, if for the panelists who log back out and in again, you have to remake them co-hosts. Technical issue from our side. Okay.
I'll just pause for a minute on this slide so whoever can see can also start to try and log in.
Yeah, apparently everyone else, everyone who cannot see who logs out and logs back in again can. So that's the fix for anyone who can't see it. But again, like I said, Joanne, we'll have to re-promote people back to co-hosts who are on the panel. Sorry.
They are already on. None of them were changed.
Oh, good. Okay, I guess it carried over. Thank you. Now let us, don't say that you can, but anyone who cannot see it now can try chatting or use the chat box for that, I guess. Anyone, don't say you can, please say if you cannot. Whoever's not here, raise your hand. That's I am getting no responses, so I presume that everyone can see it. Thank you. Okay, go ahead.
All right. I will continue then at this point. Thank you. So hopefully all the practical participants have been able to try and log in with the instructions that are on the screen here. If not, please do feel free to ask those questions in the Q&A. Coming back to the overview of the workshop, today's session, which is day one, will cover a few topics, and day two will be about more sort of advanced topics. On day one today, we'll be talking about CryoSpark algorithms and methods in depth, the specific techniques for how we perform all the various operations to deal with the issues that were outlined in Dr. Dorsey's talk for how we can actually recover three-dimensional structure information from electron micrographs in a single particle context. There will be some light mathematical theory, not too much math, mostly focusing on intuitive concepts and the actual methods that we use in practice. Concurrently with that presentation, we will be doing end-to-end processing of a simple T20S proteasome dataset, where we'll see how to use all the different parts of CryoSpark from raw movie inputs all the way to a refined high-resolution structure. And we should be able to reach around 2.9 angstroms, and if someone's lucky, maybe 2.8, depending on how your particle picking and so on goes. We'll also have some brief case studies about other results that people have had using CryoSpark, using some of the more advanced algorithms, which we will discuss in much more detail on day two. Day two will cover advanced processing jobs and parameter settings for each different type of processing or phase within single particle reconstruction. We'll be covering how to deal with heterogeneity, how to deal with membrane proteins and other forms of other proteins that have disordered regions using non-uniform refinement, dealing with continuous flexibility using 3D variability analysis, etc., as well as various advanced versions of the simpler algorithms like 2D classification and things that we'll be discussing today as well. On day two, we'll be processing 4 different data sets at various stages, either starting from scratch or with particles already extracted. Those will cover a GPCR complex, a AAA plus unfoldase protein, a simple apoferritin example that goes to a relatively high resolution, and a VA ATPase molecule that has interesting conformational dynamics. So all of those will be covered in day two, and hopefully those who are watching and listening can choose to be here for all of it. We'll be covering lots of things in detail. The agenda I'm going to post here again for just a moment in case anyone wants to take a screenshot or anything so they can remember what time we'll be trying to do things. And this is a little bit more detailed than the agenda that was previously shown. Just give this for a second. Okay, so getting started, I'd like to give a little bit of background about CryoSpark. CryoSpark is a full pipeline computational platform for single particle cryo-EM. It includes the computational tools for all phases of single particle data processing project, and allows users to interactively and intuitively process their data in a visual manner via a streamlined user interface that we've designed. Today, CryoSpark is used around the world on a daily basis by thousands of users across hundreds of institutions and has been cited many times in major structural studies, which is something we're very, very excited and happy to see. And CryoSpark originally, when it first started, was a research project at the University of Toronto in the computer science department. The first versions of CryoSpark we built at that time in 2016, and since then it's been under heavy development by the great team that we've assembled at Structura Biotechnology Inc., which is a spin-out from the University of Toronto. Our focus in building CryoSpark is to combine new algorithms that we develop through our research projects, fast GPU implementations of various methods from around the Cryo-EM community that we try to optimize into a streamlined workflow, as well as professional software engineering to create a reliable, robust, and ultra high performance as far as possible computational platform for single particle reconstruction. The reason we're doing this is that we see single particle Cryo-EM continuing to grow in adoption and capabilities in many biological contexts and across different types of users. And our goal is to support the Cryo-EM community that's evolving and growing with the best tools and workflows possible. That's why our team spends a lot of time and effort that we do and energy to continually improve CryoSpark. We release updates usually on every couple of months and distribute it freely for academic users. It's also available for commercial use through our company. Just to give some more context of what's been going on with CryoSpark development, since CryoSpark is really one of the newest and youngest single particle data processing projects. Over the past few years since we released the first version of CryoSpark, there have been many major updates and versions. In 2017, we had our first major publication in Nature Methods around some of the new algorithms that we had developed at that time. Those were techniques for doing ab-initio reconstruction of protein structures from 2D image data without initial models, as well as very high speed refinement of those to high resolution structures. We also developed during the year fast 2D classification techniques, new methods for 3D heterogeneity analysis, and the first web user interface for dealing with particle datasets in CryoSpark. In 2018, we developed and released CryoSpark version 2, which at that time was and is still by far the fastest full pipeline for single particle EM data processing, covering motion correction, CTF estimation, particle picking, and all the stages that you need to get a reconstruction. We also introduced some new advanced techniques for refinement for things like membrane proteins, specifically non-uniform refinement, as well as some new pre-processing and post-processing routines, and created a new web interface that encompasses the entire processing chain. That's CryoSpark version 2, the same one that we will be using, or has been developed since then, that we will be using today. Last year in 2019, we continued to build on CryoSpark 2, and we also introduced CryoSpark Live, which is something we'll touch on very briefly in the workshop today, which is a real-time processing solution for recovering 3D structures in real time during data collection while a sample is in the microscope. It's being used by many large facilities today around the world, and we'll hope to show you just a little bit of detail of what's possible in that realm at this point. We also developed some new methods for dealing with continuous heterogeneity, flexible molecules, and dynamic molecules. This year, we're continuing in all those directions, and we have lots of new exciting developments on the horizon, so please do stay tuned for more CryoSpark updates every little while. Finally, just as part of the introduction, I just want to give a shout out to the CryoSpark team of great people, dedicated and energetic people who are building CryoSpark today. 4 of us, and you can read all their names here, 4 of us, myself, Ali, Sarah, Sohail, and Stefan, are all part of this workshop today to help answer any questions and present all the topics that we have to discuss. Once again, before we actually get started with the practical, I'm just going to show everyone the slide again about logging in, and hopefully all the practical participants have been able to do so. Otherwise, please message in the Q&A. And otherwise, I'm going to now hand it off to Sarah to start talking a little bit about, before we get into actually processing with CryoSpark, documentation and user support, so that everyone who's watching knows where they can go to read and learn more about everything that we're going to talk about in the next few minutes.
Great, thank you so much, Ali. I'm just going to start sharing my screen in a moment.
Thank you.
Please confirm you can see a series of Chrome tabs.
That's correct, yeah.
Okay, so before we get too far into the tutorial itself, I'd like to go over some of the documentation and resources that are available for all users of CryoSpark, both those attending the practical session of this workshop, as well as those who are following along remotely. So the place that you need to start off at is our website, cryospark.com. And specifically, I'd like to direct you to the documentation section. So if you head on over into that section, it's organized into several components. If you're first setting up your own CryoSpark instance, you'll probably want to start at the quick start, which is everything you need to get that set up and going, as well as our introductory tutorial, which we will also be going through today. The other sections that are of relevance rather are the tutorials and the reference guides. You can also browse all of these links on the left-hand side here, and that's how I will take you through these sections at the moment. So under the reference section, you'll want to note the installation and management guide, which is a detailed instruction for how to actually configure and set up CryoSpark in your specific environment. The user interface and usage guide is what you'll want to look at for getting an understanding of the user interface, how the different components such as projects, workspaces, and jobs are actually laid out, and how to navigate the different information that's present when you're going through the CryoSpark interface.
Sarah?
Yes.
This is Mike, and we have a question on the chat box that if people are using their own resources, these are not the people that are signed up on the Slack resource,
Right.
Can you give them the Empire information for the data sets that you are using during the tutorial so that they can use those data sets if they want to follow along exactly with what you're doing? So this would be information about people getting data, that the same data that you will be using for your own tutorial here for the practical for the people that are logged onto Slack computers.
Sorry,
Sure.
if you'd like, I can answer that.
Yeah, go ahead.
Sure, okay. So the data processing that we're going to be doing today is going to use the same data as our standard CryoSpark tutorial that's online. And so anyone who has a CryoSpark instance can download this data with a single command, which is, it's from Empire 10,025 rather.
I actually have the page open at the moment. So if you navigate here, you can find it.
You don't need to download the entire data set from Empire since we're only using a subset of the movies. But if you're using a CryoSpark instance, you can use the command CryoSpark-M download test, and that downloads the entire test set that we're going to be using for this. We will provide the information about tomorrow's data sets a little bit later on. We don't have a slide for that right now, but we can make that up perhaps over lunch.
Thank you.
Okay, thanks. So sorry, I think I was on the user interface and usage guide. So this is a really handy way to kind of remember how to access and navigate the CryoSpark interface. There are various things covered in here, like how to build jobs, how to use various keyboard shortcuts, and how to basically really do anything in the interface. The other thing I'd like to point out is the jobs and parameters guide, which is kind of like an A to Z reference of all of the job types that are currently available in CryoSpark. If you navigate into any one of them, you'll be able to find out more information about what it does, the various inputs and outputs that you expect to have and to generate, and other notes that are useful. There's also a number of tutorials here on the left-hand side. So I'll just pick up one of them as an example. These cover everything from how to use various aspects of the interface to data management to actually in-depth theory on some of our job types. So as an example, 3D variability analysis, which will be covered in day 2 of this tutorial. We have a 2-part tutorial online here that you can access and read at your leisure. Finally, I'd also like to point out that on our documentation section, we're making more efforts to create a comprehensive guide for CryoSpark where all of this information, which sometimes can be a little bit disjoint, will be able to be found in one place. So if you head over to the new CryoSpark guide, which is currently under construction, but you can view the sections that are already live and available for you. For example, the entire setup, configuration, and management section is available here, including things like management and monitoring for example, various command line interface commands that you may be interested in using. And then also the T20S tutorial, which we'll be covering today, has also been made available here. And all of these sections will be further populated with a lot more detail in the coming weeks and months. So these are really great resources that you should definitely start off at. Finally, I'd also like to mention that this new version of the guide is fully searchable. So as an example, if you're looking for information on how to update your instance, you'll just go ahead and search for that and find the relevant links throughout the entire documentation. So so how to actually get help and stay in the loop is the next thing that I'd like to kind of touch on. So the main way that you can communicate with us at any time is through the discussion forum. That's discuss.cryospark.com. It's fairly heavily used at this point, and also, like our guide, is fully searchable. So if, for example, you're looking for data processing strategies for membrane proteins, you can find information like that by doing a quick search and various posts from the CryoSpark team as well as from other users of CryoSpark. Similarly, if you received a traceback in a failed job and you're not sure what to do about it, you might want to put in some keywords and also look up various information related to that error. For additional help, you can always contact us for academic users at feedback@structura.bio. We're fairly good with our replies. And lastly, a really good way to stay in the loop about new updates and tutorials is through our newsletter. So you can subscribe on the bottom of the CryoSpark website page here in the footer. And just to give you an example, we send up approximately 1 newsletter per month, so it's not really too much. And here's an example of the most recent one that we sent out regarding the version 2.15 update that was released last month. Finally, as Ali mentioned, I will be reviewing all the questions that are sent in via the Q&A feature throughout the webinar, and at specified points, I'll actually be gathering those questions together and getting them answered live. So please do continue to send in your questions, and we will answer those as soon as possible in that form. Thank you.
Great, thank you, Sarah. I'm just going to start sharing my screen again. Can we all see the screen? Great. All right, thank you, Sarah, for covering documentation and user support. Once again, just to remind everyone who is a practical participant, please do log in as soon as possible using these instructions. You are assigned a specific CryoSpark instance. These 2 numbers are filled in the email that you received, and you have a password for the authentication layer as well as your own CryoSpark account, where you also have your own numeric user ID for which you need to log in on the CryoSpark page. Okay. When you do log in, you may be presented with a non-commercial user agreement for new software. Just click accept at the bottom and continue. Okay, next we're going to move over to the CryoSpark user interface overview that Sohail is going to present.
Great, thanks, Ali. Can everyone hear me?
Yep.
Awesome. Just gonna go ahead and share my screen. 1 second. Can everyone see my screen?
Yes.
Great. So hi, everyone. I'm Sohail from the CryoSpark team. Before we get started processing the T20S dataset, I just wanted to give a quick overview of how to use CryoSpark's web interface in order to create jobs and also view results. We'll go into much more detail about different job types available in CryoSpark, as well as how to configure their parameters and the outputs that they produce later on in this session. And as Sarah mentioned, we have comprehensive documentation available online, including references for the user interface. So CryoSpark is a software system that's comprised of multiple components, allowing you to easily run and inspect jobs. One core component of CryoSpark is its web application interface, which becomes available automatically when CryoSpark starts. The web interface is accessible through a modern browser such as Chrome or Firefox and is hosted on the local network of the machine that is running CryoSpark. You can connect to the web application locally or remotely as long as you have a connection to the machine that's running CryoSpark. And we actually have a post on our blog that details how to access CryoSpark and its web interface from a remote computer, such as your laptop when you're working from home. So make sure to check out that blog post. I have the web application open in this tab. The first page that you'll see once you log in is the dashboard, and it contains some helpful links as well as information such as our changelog, which is a list of our recent updates to CryoSpark. Additionally, the dashboard contains some statistics about the instance, which is helpful to keep track of as you process more data. The CryoSpark web application has a pretty simple and intuitive layout that's comprised of 3 main sections. You have your navigation at the top and the bottom of the screen. They contain buttons to go to different pages, such as our resource manager, as well as actions to create new projects, for example. Next, you'll have the content area, which is where you'll browse and inspect jobs. And then finally, the sidebar, which adapts to your selections and houses the job builder, which is where you'll create jobs, set their parameters, as well as queue the job to available compute resources. We've specifically designed the web application to make working with lots of projects and jobs easy. And to that end, I'm going to explain a little bit about how project management works inside of CryoSpark. There are three main layers of entities within CryoSpark. You have projects, workspaces, and jobs. Projects are the main containers for jobs that you run inside of CryoSpark. Each project is associated with a project directory on your file system. The metadata, as well as result data of jobs, will be stored in these project directories within subdirectories. Next, workspaces are logical grouping of jobs within your project. You can create as many workspaces as you'd like and assign them a name that will make it easy to refer back to as the number of jobs within your project increases. And then finally, jobs are containers for a specific step in the data processing pipeline, and they're unique to projects. They're created inside of workspaces and can be either moved or linked between workspaces. This diagram depicts a typical tree structure for a project within CryoSpark. Workspaces are shown as different colors, and they act to split the project into manageable groups. Raw data is imported once, but can be referred to in multiple workspaces for different iterations of processing. Projects, workspaces, and jobs all are identified by a number prefixed with either P for project, W for workspace, and J for jobs. Workspaces, as well as jobs, have identifiers that are unique to the project that they're created in, which means that the first workspace in a project is always W1, and the first job is always J1. To view a list of projects in the user interface, simply click on the Projects button. You can also choose to look through the project and workspace switcher UI at the top of the screen, which allows you to quickly navigate to a particular project or workspace. I'm just going to click on the Projects button at the bottom of the screen. When you select a project by clicking on the card, the sidebar will update with more information about it, such as when it was created, who the project is shared with, as well as how much disk space the project is consuming. To create a project, click on the Add button at the top of the screen. After providing a name, you can use the integrated file browser to search for a directory in which to create the project's container folder. To enter a project, simply click on the project identifier. We're going to look at project 33, which contains the full data processing pipeline for Empire entry number 10291, which is an undocked Innexin 6 Hemi channel. We actually published a case study on our blog that outlines how to process this very data set to a better than published resolution structure within 1 hour and 25 minutes. So I definitely recommend checking out the blog to look at this case study. Now back to the CryoSpark interface. Here you can see a list of workspaces and all the jobs that exist within each workspace. Similar to projects, when you click on a workspace card, its details will appear in the sidebar. You can create a workspace just as a project by clicking the Add button and specifying a name. Let's take a look at W1, which contains an initial run through the entire processing pipeline, from the import of motion-corrected micrographs all the way to a sharpened refined volume. The jobs view contains all the jobs of a particular workspace, each showing as a card with preview images. Selecting a job will show you additional information about it in the sidebar. The parents and the children of the job will also be highlighted upon selection. For example, I've just selected J2 patch CTF. And since the patch CTF job uses the imported micrographs as its input, the import micrographs job is highlighted in red. And since the blob picker, J3, uses patch CTF as its input, it's essentially a child of J2, therefore it's highlighted in green. I'm going to go ahead and select J10 now. To inspect a particular job and view its outputs and logs, simply tap on the spacebar or click the job identifier when you see a magnifying glass cursor. Logs are outputted in real time, and they include various diagnostic text and plots depending on the job type. So here I can view my details for this non-uniform refinement job. On the Inputs and Parameters tab, the parameters that differ from the default are highlighted in green. And you can see here that C8 symmetry has been set on this particular non-uniform refinement job. Now heading over to the Outputs tab. Each job has a set of outputs that it creates, depending on the inputs as well as the parameters chosen. There are two primary classes of outputs in CryoSpark, result groups and low-level results. Result groups are semantically related collections. This can be exposures, particles, volumes, etc. Result groups become handy when creating new jobs, as I'll explain in a minute. Here's a diagram that essentially depicts how low-level results for particles and 2D class average data are grouped into particle and 2D class average result groups respectively. We also have a great tutorial that covers in very detail all the information that you essentially need to know about the job builder. So I recommend checking that out after this. I'm just going to head back to the job. You can access result groups from the Overview tab, where it's also possible to click on the download icon to view a list of results to download. So for example, the sharpened map of a refinement is available to download right from this menu. I can click spacebar to return back to the cards view. To create a job, just click the Job Builder button in the sidebar. Here, you'll be greeted with a list of jobs that you can select. Jobs are grouped into different categories, such as imports and motion correction. You can also use the search bar to filter through the list. I'm going to go ahead and create a Select 2D Classes job, which allows me to interactively select a subset of 2D classes for further processing. You can see that this job has been added to the cards view, J28. You can build any other job in the interface that's in building status by simply clicking on the building text in the card or pressing the B key on your keyboard. To build this Select 2D class job, I'm just going to go ahead and select an existing 2D classification job and drag and drop the outputs into the inputs for the job builder. So I'm going to drag the particles into the particles input slot and the class averages into the templates input slot. To queue a job, simply click the Queue button at the bottom of the sidebar, and you can select a compute resource to run this job. Just as you can inspect a completed job, active jobs will also output their status in real time. And for certain interactive jobs, a new tab will automatically appear for you to be able to interact with that job. In this case, the interactive tab allows me to view, sort, and select 2D classes. So I'm going to do just that. When I click the Done button, it's going to complete the job and make the outputs available to use within that workspace. It's important to note that you can create multiple jobs, edit and queue them all at once, and CryoSpark will automatically wait for parent jobs to complete and then start the children jobs automatically as soon as they finish. If you queue multiple jobs on the same hardware resources, CryoSpark will automatically wait until those resources become available and then queue them once resources are available and start to process those jobs. To keep track of larger projects, as well as more complicated workflows, we've developed a tree view and a layout algorithm to automatically display all jobs in relation to other jobs within a workspace. You can enter this tree view by clicking on the tree display icon in the navigation bar next to the import button. Here, you can pan and zoom across the canvas and interact with job cards, just as you can in the cards view. In this workspace, the tree starts with an import job and goes all the way down the data processing pipeline through to the final refinements. The tree view makes it easy to quickly identify splits in the processing pipeline. So here, for example, I can see clearly two Ab-initio jobs, J12 and J8, that all derive from the same set of particles from selected classes. Just as the card view, I can go ahead and click on a job and press spacebar in order to inspect the details of that particular job. It's also possible to interact with the sidebar as well as the job builder when the tree view is active. It's also possible to view a tree view for an entire project, and all the jobs within that entire project, regardless of workspace, will be available to view. So that was a quick whirlwind tour of how the CryoSpark user interface works. At this point, I'm going to hand it over to Sarah so we can take some time to answer questions. Thanks.
So just one extra point, if you can mention for us, how do you zoom and pan in the tree view so you can see different things?
Very good question. You can use the Option key in order to zoom and pan. So if you hold down the Option key and then you use either your mouse scroll wheel or your two-finger drag on a trackpad that's applicable, that allows you to zoom. And then you can also drag to pan or use two fingers on a trackpad to pan.
And Option is also known as Alt on Windows keyboards, right?
Yes.
Great. Okay, thank you.
Awesome, thanks.
Great, so at this point, we don't have any questions specific to user interface. All of this will be covered again in much more detail as we actually walk through processing an entire data set start to finish. But hopefully this was a good introduction to how the various aspects of the user interface are laid out. As always, if you do have other questions, please keep them coming. We'll either reply by text, as we've been doing, or answer them live at the appropriate sections.
Great. Shall we wait a minute in case anybody has any questions that they're still typing up? Just 1 minute.
Yeah, I don't see any questions either on the chat line or on the or on the Q&As right now.
Great, then I will continue and we'll take up all the rest of the questions in the next question slot.
Oh, one question: how to recover a deleted job? This is one.
That's a great question. We actually have a section on data management and dealing with jobs and projects in that way coming up in the next block. So we'll answer that question either in that presentation or in the question period immediately after that.
Thank you.
We do have a couple more that have come in that I think are worth it. So the one is, how do multiple users work on the same project? I'll start off. A single CryoSpark instance can support multiple users. The only thing to note there is that each user can create their own projects, which they may or may not decide to share with other users on that same instance. And that's a file system permissions level thing as well that we can get into. But in general, we support the ability to have multiple users on a single instance who can either process their own data or process shared data.
Yeah, perfect.
Anything to add from the rest of the team?
I think so. Did you point out the share button on the sidebar for a project?
I don't think I explicitly mentioned it, but when you click or select on a project, in the sidebar, there'll be a shared with essentially key, and it will show you a list of tags, which are users in which you've shared the project with. And then there's also a share with users button with a dropdown, which allows you to select a user to share with. One thing to note is that if you're an admin user, by default, you can view everyone's projects. So there's no need to share with an admin user.
Great, thank you.
We do have another few questions that are relevant. Is there a way to export the tree diagram of your procedures?
That's a great question. Unfortunately, there isn't a way to do that at the moment, but it's definitely something that we can add to our to-do list.
Definitely. You can always take a screenshot and save that image, but we haven't started generating, for example, PDF reports or anything like that. However, the tree itself, as Soha mentioned, does generate itself, so you won't ever lose it, and you don't have to worry about it rearranging it or anything like that. It takes care of itself. And as long as you have the project intact in CryoSpark, you can always come back to that page no matter how much later and see the tree view again. I see there's one more question about explaining data sharing amongst projects, workspaces, and jobs. I'm going to try and answer that. I think what the question is asking is, what kind of results can you use between projects, workspaces, and jobs? Now, as Soha mentioned, projects are meant to be top-level containers for processing workflows. So typically you would want to use a single project for every distinct sort of biological project that you're working on, where you know that there's really nothing in common between the data being processed in one project or another. If you are, for example, collecting multiple sessions on the same grid or even similar grids, maybe two different versions of your target, maybe with a ligand bound or not, you can process those all in the same project, because in the same project, it's trivial to use outputs from one job as the inputs to another job across workspaces or any other division. So within a single project, you can always do that very easily. Across project, you can do that, but it requires an export and import step, which is a little bit more cumbersome. So it's better to keep anything that is related in the same project. However, you shouldn't use the same project for everything, because then you'll end up with just one very large project and no way to cut it up in case you want to archive parts of it or so on. So we generally recommend start a new project if it's a new sample, essentially.
One more question. Thanks, sorry to interrupt. One more question just as a point of clarification about whether we are accessing the tutorial data together later, or do I need to download it now? So for the approximately 60 participants who are accessing Stanford Slack compute resources, you would have received your credentials to access your CryoSpark account from Yi. And so you will already have those credentials. For everyone else, we will be starting off with the T20S tutorial, and I'll post the link to that in this chat right now. If you have your own CryoSpark instance already set up, you can just enter one command to download the subset that we will also be working to process.
That's right.
So I will post that right now, and anyone who wishes to follow along remotely and who is not accessing the Stanford resources can do so as well.
And again, anyone who's part of the Stanford practical can, the data is already loaded for you. You don't have to download or transfer anything from anywhere.
Okay, we also have questions about importing and exporting data to or from Relion and other programs, which we'll cover a little bit later on in our data management section.
Great. Okay, then I think what I'll do is continue on the slides. Hopefully in the next few minutes before the scheduled lunch break, we'll be able to start processing some data and at least have some jobs running so they can run while we're on a break. Just give me one moment to share my screen again. Okay. Can we see the screen? Great. So we're going to get right into CryoEM data processing now. I'm going to start by giving a little bit of a background on just recapping some of the things that Dr. DeRosier already mentioned, but just from the context of what it means in terms of real life practical data processing, all the various difficulties of single particle EM data that also are fortunately workaroundable or solvable so that we can actually recover 3D structures.
Just one comment, Ali. Yes, we do have several questions which were hanging from the question and answer session from the previous session, and I presume that many of those, especially involving motion correction and CTF estimation, things like that, will probably be answered by you guys as we go through in the CryoSpark milieu and how it's done in CryoSpark. So we're not ignoring the questions that people had from last time. It's just that they're better answered by the people running the programs themselves. I'm sorry. Sure. Okay, thank you.
Yeah, we'll try to cover all. Well, we will be covering all those topics, but any questions that remain, we can also answer to the best of our ability. So in single particle cryo-EM, there are 3 general large steps involved in actually getting a 3D structure. The first being sample preparation, next data collection, and finally actually computing the structure and getting a 3-dimensional electron density, from which you can then build an atomic model. We won't talk about model building, but everything that we do in our team is focusing on the computational aspect of single particle cryo-EM. However, it's very worthwhile to understand some aspects of the previous 2 phases to know what kind of characteristics we're dealing with in our data and what the implications of those are in data processing. So first of all, sample preparation involves, as we've already seen, freezing a thin film of liquid water vitreously inside of holes which are inside of grid squares which are on a small 3mm EM grid. Each one of those holes, ideally with a well-frozen sample, will contain a thin layer of ice and several molecules of your target protein, hopefully well purified, in hopefully random orientations. The plunge freezing that's used to vitrify the sample ensures that the water that's frozen doesn't form crystalline ice, which would break up the protein, but rather vitreous ice, which is in a glassy state, ideally close to the native state of water around the protein that would ordinarily happen inside of a cell or outside. Some of the problems that can happen in real life in terms of sample preparation that strongly affect downstream processing are some things that we've already heard about: ice thickness and quality. This is often the #1 detail about sample preparation that needs to be thought about when you're considering what's going to happen in your data processing later. Thinner ice is, generically speaking, always better until you get so thin that you start to squeeze particles out of the holes, or they start to aggregate in strange ways, or they form a preferred orientation. Other than those issues, thinner ice is always better. The quality of the ice is also very important. Sometimes if a grid has not been properly placed into the microscope, the vacuum hasn't been shut or started properly, or etc., humidity can condense onto the grid in transit and create ice crystals on top of the grid, which destroy the quality of the sample. Particle concentration is another major important part of the sample. If there are too many particles in a hole, if the sample concentration is too high, they can sometimes that either forces them to interact with the air-water interface, which isn't something you maybe don't want to have, or they're so tightly packed that they become difficult to pick apart, or they have some other interaction with each other that's not ideal, for example, aggregation. If the particle concentration is too low, it may take many, many images from the microscope to collect enough particles to get a 3D reconstruction, or there won't be enough signal in every image to accurately recover, as we've seen, the contrast transfer function by fitting tone rings. And since we know now that those tone rings depend on the amount of actual signal, or rather content in the sample that is diffracting the electron beam to create those tone rings. So particle concentration being at a kind of happy medium is important. Sample heterogeneity is also critical. It's often actually a good thing if you are studying a protein that is likely to be heterogeneous, either in a discrete sense, having multiple conformational states that are all separate and rigid, or in a continuous sense where you may have a floppy region of a protein, or a protein that has some mechanistic function that you're trying to investigate. If you're really looking for a very high resolution reconstruction, often heterogeneity is not so great. And the highest resolution reconstructions we have from single particle cryo-EM are all on extremely homogeneous rigid particles. But we'll come back to that later. Generally speaking, in real life biologically interesting projects, heterogeneity is a blessing. And being able to deal with it is very important. Orientation distributions also, as we've heard, are extremely important. If you've only seen a three-dimensional object from a few directions, there literally isn't enough information in the images to recover a 3D structure, and there's nothing that data processing can do about that. So we'll come back to talking about orientation distributions in a few minutes. Denaturation and aggregation, I think we already mentioned, as related to particle concentration, but often these have to be dealt with during the phase of actually picking out particles in the ice. Data collection is the next step in single particle cryo-EM. And again, we've heard a lot about this, and a lot of details have been illuminated. For our purposes in terms of understanding the implications for data processing, what we need to recall is that the images from the electron microscope are formed by phase contrast imaging of an electron beam passing through our sample and interacting with a direct electron detector, where we're actually counting electrons interacting or hitting particular pixels. Of course, each electron going through the sample actually interacts with the entire sample in a quantum mechanical sense. And in fact, if you think of the energies and timings, while the electron microscope is operating, only a single electron on average is in the column, or less than a single electron even on average, is in the column at any given time. So that means we can't think of electrons only as particles. The electrons themselves are an electron wave function or wavefront, that where a single electron is interacting with the entire sample. And then once it reaches the detector, that single electron, having contained information about the entire sample, is, by a quantum mechanical magic, selecting a single pixel to light up on the detector. It's through the aggregation of many electrons that we actually recover information about what's in the sample. So that's just a bit of an aside. But what's important, one thing I should also mention, is that the radiation damage, as we've seen, is a very important factor in creating the image and destroying the sample at the same time. And so electron microscope imaging for biological samples has to be limited to a very low electron dose to limit the amount of radiation damage that happens. So these are some of the things I already talked about that are very important when we come to thinking about the images from a computational perspective. There are microscope aberrations, things like beam tilt, coma, and other things, the CTF in general, that we've heard about. Stage drift and sample deformation, both which cause motion blur of the sample via different physical mechanisms. The radiation damage that leads to a very high noise level. So that's kind of an overview of the data context in which all of our data processing methods and algorithms have to operate. Now, in terms of actually resolving a 3D structure, the steps are, at least in the most simple cases, the steps can be pretty much straightforward. We start with pre-processing the raw data to estimate and correct for motion. That's done using the frames from a movie that's captured on a direct electron detector rather than a single image. Once the motion is estimated and corrected, we can then start to fit the microscope contrast transfer function. Then we can find particles in the ice, cutting out those particles, extracting boxes, and classifying the particles into 2D, in 2D rather, without actually recovering 3D structure yet, but just looking for similar patterns in the sample. As you can see in real life cryo-EM data, by eye, you can almost never actually tell what you're looking at. And it's only through aggregation of signal from multiple exposures, multiple observations of the same protein from the same pose, that we actually get enough information to tell that we're even looking at the protein of interest. But with 2D classification techniques, we can cluster particles in 2 dimensions and start to separate junk and broken particles from the data. Then we can actually do the hardest step, which is recovering a 3D structure from 2D image data, and ideally at the same time resolving some heterogeneity if there are multiple objects present. And finally, recovering a high resolution structure by refinement. All of those steps and many other branches off this simple linear chain and loops and other things that people do are all supported in Cryo's work. And we're continuously working to continue to build out all the tools that you need for a state-of-the-art high resolution reconstruction. As I mentioned, in real life projects, you often need to deal with many tools in a highly iterative and not linear fashion. That may include multiple iterations through particle picking, 2D classification, using the 2D class results to redo particle picking, getting ab-initio reconstructions in 3 dimensions, using those to again redo particle picking or separate heterogeneity through other techniques, and repeating those loops, and then finally refining every different subset of particles or every different conformational state that you find, and iterating through that as well, and post-processing sharpening. And sometimes for most projects, a single pass through this iterative mechanism will yield the insight that you need more data, in which case you go back to the microscope, collect more data, and come back again. Nowadays, it's common for typical dataset sizes, especially the early stages of particle picking and 2D classification, to reach into the multiple millions of particles, and those are often whittled down by classification strategies. To support all that, a robust software system like CryoSpark is what we're trying to build so that we can deal with this entire pipeline of processing very fast and recover lots of biological insight. The tutorial data that we're going to start using now is a subset of data from Empire entry 10025. This is data of a T20S proteasome molecule, which is a great benchmark data set for a single particle EM analysis, good for testing microscopes and reconstruction methods because it's large and highly symmetric. This data was originally collected at NRAM on a Titan Krios microscope with a Gatan K2 camera. The pixel size, which we'll repeat in a minute, that everyone will need in order to import the data is 0.6575 angstroms per pixel. This data was collected in super resolution mode, 8,000 by 8,000 pixels, 38 frames per movie. And the total electron dose was 53 electrons per square angstrom going through the sample. The great things about this protein are that it's large, stable, without any, at least so far, known heterogeneity or flexibility. We'll find out later that that's actually not true. What we're able to do is use only a subset of 20 movies to recover a 2.9 or 2.8 angstrom reconstruction. So that's what we're going to aim to do in this first part of the tutorial. The data, I should mention, are compressed in TIFF format with LZW compression. That's one of the most common compression types for single particle EM data, raw movie data. And compression is really important because the raw movie files can be very large if they're not compressed. And it turns out that it takes longer to read uncompressed data from disk than it does to read the compressed data and decompress it on the fly. So that's what we generally tend to prescribe to users, is to make sure all your data, once it's collected, as soon as it's collected, is compressed. And when you're processing it, it can be decompressed on the fly. So that's what we're going to start working with. And now we're going to switch over. I'm going to show you the CryoSpark interface, and we'll start by creating our own project. So this is now instructions for the practical participants. Creating a new project. I'll just give you some of the details now and then show you how to actually do it in a moment. You'll be using your own name in the project title so that since there are multiple users on the same CryoSpark instance right now in the Stanford system, you need to know which project is yours. And that same project is going to be used for all your processing today, including across all the data sets. The project directory you're going to choose is // sorry, there's a typo there, it should be // training projects. That's where we're going to create everyone's project directory. And we'll be setting the project level parameter called whether or not to use SSD cache to disabled by default. So I'm going to switch over to CryoSpark now and show you how to actually take those steps. This is actually one of the CryoSpark instances at Stanford that's being used for the tutorial right now. And I'm running this as I'm logged in as an admin user, so I will be able to see all the projects that everyone creates here. But the first step that we want to do is, if you're starting with the CryoSpark dashboard, is go over to the projects page. You can click on.
Sorry to interrupt. I'm just doing a very quick time check and also noting that it looks like we have just about 2/3 of the practical participants have actually logged into their CryoSpark instances. So I think for the benefit of making sure that everyone can kind of start off at the same pace, does it make sense for us to finish off with a few questions right now, head into our lunch break, and during that time we can address helping the remainder of the practical participants?
It's a great idea, sure.
To log on. Okay. So sorry to kind of interrupt the flow there. Just a few questions that are relevant from the sample preparation image formation portion that we were discussing before. Is there a relationship between preferred orientations in the sample and sample thickness?
Yes, that's a great question. There definitely is a relationship. Now, it's not a relationship that we can exactly quantify since it's very dependent on the sample. But generally speaking, what you'll find if you process enough data is that as the ice gets thinner, so if the ice is very thick, if you think of ice that's maybe 10 times the thickness of a particle, there are two things that happen. The particle, first of all, I mean, depending on how the sample preparation was done, the particle is far away from the air-water interfaces, and so by random chance, slightly less likely to interact with those. It's generally somewhat accepted, although not, as far as I know, proven that the air-water interface is actually the part of the sample preparation process that causes a lot of preferred orientation. It's when particles are spinning around just by thermal motion and moving around by Brownian motion, interacting with the air-water interface, that they, depending on their own structure, adopt preferred orientation that has some connection with the air-water interface. So with thicker ice, the air-water interface is farther away, and just naturally the particles tend to appear in a more random orientation. That's not strictly true. There are particles that are so they are so tightly bound to the air-water interface that even with large thick ice, they may still adopt a preferred orientation, but generally speaking, thicker ice will allow for more orientations. As the ice gets thinner and thinner, it's more likely that the particle will start to interact with the air-water interface. And for particles that don't really have any interaction with the air-water interface, the thinner ice is possible until the ice gets so thin that it's now on the same order of magnitude as the particle itself, in which case, just by geometry, the particle, if it's elongated, not perfectly spherical or globular, may adopt a preferred orientation just because of the energy of that state being better than not. It's really a complicated situation, and I don't think there's a perfect understanding of all the physics of what goes on between the time when a sample is applied to a grid, let's say in a blotting type of setup, to the time when the liquid is blotted off and the grid is frozen. During that time is when the whole preferred orientation problem occurs, but it's not exactly clear what is happening at that time, not perfectly clear. It's known, though, that, for example, adding detergents or changing other sample preparation properties like pH and stuff like that, this is not an area where I'm an expert at all, but it's known that those can sometimes impact preferred orientation, especially detergent, which is a commonly tried trick as far as I know. If you do get preferred orientation, add detergent and try to create the sample again. Hopefully that answers the question.
Great. We do have a couple more questions regarding preferred orientation, but I think in the interest of time, we'll hold those back for later on in the session. Sure. We'll keep them open for now, as well as a couple of questions about setting up CryoSpark user accounts and predicting symmetry. So we'll go ahead and I think move on to the lunch break. Michael, Joanne, perhaps we can get your assistance with letting the practical participants know to transition over to the meeting if they're having computing issues.
Great. Can someone confirm that they can see my screen being shared here?
Yes, I can see it. I can't speak for all the attendees, but I can see it. Thank you.
I can see it too.
Yeah, I'll go to my end as well.
Yeah, I see it too.
Great. All right, so we're going to pick up from where we left off, coming back from lunch. Hopefully all the participants who were online before have had a chance to sign in again. I see that some still are joining. Right now, just coming back from lunch, a few notes for the practical participants. Hopefully you have all been able to log in now. I know Yi has been working very hard to make sure that that is the case, and hopefully everyone is able to log in. If you still have any issues getting into your CryoSpark instance, please get in touch with us or Yi via the Q&A on this Zoom webinar. And otherwise, try to follow along as you can. We'll be going relatively slowly through all of the steps, and I'll be making sure to explain very clearly everything that you need to do. So hopefully it will be straightforward to follow along. Now, for those who are following at home, we are, like I said, going to be going through all the steps in the broadcast. I'll be showing CryoSpark and showing you exactly what to click on and so on. So if you aren't processing at home, that's perfectly fine. In fact, that wasn't the intention. So please just watch the webinar and you'll learn everything as well. And the recordings will also be available. For those who do want to process today's data, if you don't already have it, it may be somewhat too late to download it at this point, but you can download today's data with CryoSpark M download test. And that will download the data to your CryoSpark instance if you have that installed locally. Again, a reminder, Q&A, you can also see, all participants can see answered questions in the Q&A box. So feel free to browse those at some point. And please continue to ask questions anytime. We're going to continue to answer as many as possible in the question periods that are set aside when you see the slide that says questions. And finally, just a recap of the agenda. We're going to be continuing on the T20S tutorial that was aiming to be before lunch, but this should be fine to happen now. After we get to the 2D classification stage, we're going to take a small detour and talk about CryoSpark architecture, hardware configurations, troubleshooting, and data management. That's going to answer a lot of questions about projects and project directories and workspaces and exporting and importing and so on. And then we'll continue with the T20S tutorial going through 3D reconstruction, Ab-initio, refinement, validation, post-processing, etc. So that is the agenda. And now I'll return to where we were. We had just started talking about processing our tutorial dataset, which is this T20S proteasome dataset. And I mentioned all the information about it and got to the first set of instructions for what to do in CryoSpark in order to import this data and start processing it. What I'm going to do is to make our lives easy, instead of showing the instructions as a slide and switching back to CryoSpark, I have these instructions now collated into a list of instructions here that hopefully everyone can see in this note. And we're going to be starting with the import and motion correction instructions. So whoever's watching can follow along the instructions on the left and exactly what I'm going to be doing here on the right. So our first step in processing this data is to create a new project within CryoSpark. When we first get to our CryoSpark instance, and for practical participants, you may have a different number up here and you'll be logged in as your own self. And anyone watching from home, this is exactly what CryoSpark looks like anywhere you are. We can get over to the projects page by clicking on this small icon here or clicking on the projects button at the bottom. So I'll go ahead and do that. And now we see that there are right now in this instance 4 projects. Since I'm an admin user, I can see the projects of other users as well, but that's not really important to us right now. What we want to do first is to add a new project. So we're going to click the add button here at the top. And that brings up the new project modal. This is the only place to create a new project, and it only needs 2 questions or 2 answers to 2 questions. One, the title of the project. Here we're going to use a title that has our own name. So I'm going to call it Ali S2C2 processing. And remember that this project is the same project we're going to use throughout the processing today and tomorrow. So you won't need to do this process again, but it's important to put your name in there since there may be other people on the same CryoSpark instance who are also going to create projects. So once you've done that, you can choose a directory in which to create the new project. Now, CryoSpark project directories, as was partially explained before and will be explained in much more detail in our data management section, contain everything about your project, all the files, all the data, all the images, output results, everything. The only thing they don't contain is the input data that you import. The raw files that you import are left on disk, for example, movie files, wherever they were, so as not to create duplication of very large data. But otherwise, anything that CryoSpark outputs is put into a project directory. And the project directories are fully self-contained. So if you have a CryoSpark instance at home, if you create a project, anything that you do in there, you can always take the entire project directory, move it somewhere else in your file system or to a different computer, a different CryoSpark instance, and import it back into CryoSpark, and it will come back fully formed. So for our workshop today for the participants, you're going to choose a specific directory, which is called /scratch/training/projects, but you don't need to enter this directory manually. So if you just type /, for example, you can see the entire file system. You can browse through it and find the scratch directory. And then inside of /scratch, you'll find a training folder. So you can click on that. Now you're in Scratch training, and here you'll see a few folders. One of them called Slack Workshop Data has all the data that we're going to be processing today and tomorrow. Another one called Projects is where we want to store the outputs of our processing. So we're going to choose the projects directory, and that's it. You can see here that there are already 3 project directories, P2, 3, and 4. You don't have to worry about creating a directory here for the project you're about to create. CryoSpark will handle that. What it's asking for is a location where the project is going to be instantiated. So I'm going to go ahead and click select with this Scratch Training Projects directory. And that now shows up here as the directory I've chosen. With this much information, we can now go ahead and click create for the project. And we see that now I have project 6 here that was just created for me. And some of the other users on this instance have also created their projects, which is great. So I'm going to head into project number 6, which is my project. The other users should actually only see their own projects since they're not admin users, just to be clear about that. So inside of project 6, by clicking on the project 6 button, I can enter the project. I'm now, as you can see here by this green box in the project drop down, I'm now inside of project 6. And in the URL, you can see I'm also inside of project 6. So now that we're here, we can start to take some actions. If we look at our instructions, the first step was to create the project, select the directory. And now once the project is created, we want to set a project level default parameter. Because of the way the Slack compute systems are set up, we need to choose this parameter. On most installations, if it's at home on a workstation or a server node or whatever, you may not need to do this depending on how your system is set up. But what we're going to do is disable particle caching on SSD. The reason for that is that these Slack servers are already on SSD, so all of our data and all of our projects are already stored on an SSD, so we don't need to do the double work of caching the particles again on SSD. So we're going to choose disable by default here in this dropdown. That's an important thing. If you don't do that, your jobs in this project won't run the first time. You'll have to change their parameters manually to make them run. So now that we've done that, this project is ready for us to start actually doing some processing. In order to start creating jobs, the next thing we need to create is a workspace. If you recall from the earlier UI workshop, or sorry, UI tutorial, inside of a project are workspaces, and you can have as many workspaces as you want. Each workspace is just a logical grouping for you to manage your processing stages and jobs. Jobs can be moved from one workspace to another with no effort. Their workspaces don't correspond to locations on disk, and so jobs can be moved from one workspace to another without any problem. And you can also use the outputs of jobs from one workspace in another. So they're really just lightweight containers to help you organize your project. So I'm going to click Add, and here I'm going to type in the name of the data set that we're going to be processing right now as the title of my new workspace. And you can call it anything you want, but just to keep things organized, that's what I'm going to do. So now I have project 6, workspace 1. Everyone, I'll just give a minute for everyone to reach that stage who's working with the practical. Okay, so now in project 6, workspace 1, that's where we're going to start creating jobs for the first time. I've clicked on the little button. Sorry, I'll just show you that again. I've clicked on the little project 6, workspace 1 entrance button, and that brings me inside of workspace 1. I can equally choose workspace 1 in this drop-down if there are more than one workspace in the project. Now that I'm here, I have options to start using the job builder. That's what allows us to create jobs in CryoSpark. So when I click over to the job builder, I can see a list of all the different job types in CryoSpark. And right now I can create any of those job types, but of course it won't make any sense since CryoSpark doesn't know about any data that I'm trying to process. So the first thing I want to do is actually import data from the import section. I'm going to use a job called import movies. So I can click on that here and that'll create an import movies job, or I can actually search. When you're creating jobs, this turns out to be a very helpful feature. If I'm trying to import, I can just type the word import and I'll see jobs that match that word. So I'm going to create an import movies job. When I clicked on that button, what happened is that a new job card called J1 appeared here on the screen. That job has now been created and it has a job number, J1. It has a status, which is building. It has a type, which is import movies. You can also see in the center of the job card, it says building. That's just the same as the status. And that's highlighted in purple. And what that means is that this job, number 1, right now, is engaged in the job builder. It is being built, meaning that we can modify its inputs, its parameters, and actually start the job. So on the right-hand side here, you see the job builder. I'll just give a moment for everyone to catch up to actually having created this job number 1 of import movies type.
While we're doing that, perhaps a good time for just a couple of quick questions. So one is, can you process different data sets in the same project, but in different workspaces?
That's a great question. You absolutely can. You can import data in any workspace. However, like we were saying before, it's generally best in terms of organization to create a new project for every different kind of sample that you're working with. Not necessarily every data set. It's very common that you may collect data one day, process it in CryoSpark, and then get microscope time a week later or longer, and then collect more data on the same project. In that case, you would import movies twice. You could do them in the same workspace. You could create a new workspace for each data collection session that you have. That organization is up to you, but you definitely can import and process different data in parallel in the same workspace. You can also combine results from different processing streams in the same workspace.
Thank you. One more question. Can you import data from a remote cluster without downloading it to the machine where CryoSpark is running?
That's a great question. It will be addressed in detail in our data management and system configuration session, but the basic answer is that the data has to live in a place where the CryoSpark instance, the actual process that's running the CryoSpark instance, and all the worker processes can read it. So if it's a shared file system that's remote, but mounted on the nodes that run CryoSpark, that's perfectly fine. It doesn't have to be a local file system.
And last question, I think, before we can move on, are there any problems with uploading K3 data?
No, K3 data is fully supported. In fact, probably most of the data that's being processed in CryoSpark these days is K3 data.
Thank you.
Great. So at this point, I think everyone should be at the point of having an import movies job created here. So now that we're looking at the job builder, by the way, for some reason you have the job created and you can't see the job builder, for example, if you accidentally clicked cancel, you can always re-engage the job builder for this job by selecting the job, by clicking on it, and then clicking on where it says building. And you see that the building label turns dark purple, and the job is now re-engaged in the job builder, so we can set its parameters. So the job builder, I'm just going to go through in a little bit of detail so everyone knows how it works. At the top, it shows you the job number and the type and its status. It tells you the title of the job, which we can change later. And there's a small switch up here. If you hover over it, it says advanced mode. Right now, that switch is on for me. I'm going to turn it off so you can see what standard mode looks like. It's about the same, but in advanced mode, some extra parameters will show up for certain job types that have advanced parameters. Generally speaking, we try to organize things so that parameters that most users will want to change are not advanced, and advanced parameters are things that you should probably change only if you already know what they mean or are just experimenting. So I'll leave that switch on for now. So the first thing we want to do in creating our import job is to specify, tell CryoSpark, where's the data that we're trying to import. So by clicking on the small browse icon next to the movie's data path here, we can see again our file browser that lets us choose a place to find data. And now we're going to go back to our Scratch training directory, /scratch/training. And here we see a listing of the folders in there. One of them is called Slack Workshop Data. So we'll click on that. And finally, we will go into dataset number 1, the T20S proteasome. Inside of that folder, there's a subfolder called Movies. And there we have a collection of images in TIFF format. Like I said earlier, this is a subset of the full dataset. The full dataset has some 200-ish movies. This subset has only 20 movies, and it turns out the data is of such high quality and the protein is rigid enough that we can still get to a sub-3 angstrom reconstruction from just 20 microscope images. Of course, in real life, most projects are collecting between 3 and 10 to 20,000 movies. So that's like 1,000 times bigger than what we're doing here. And that's really actually the place where something like CryoSpark shines, is to be able to deal with that volume of data in still a fast-paced and reasonable amount of time. So now that we're here and looking at this folder where we have Scratch training, Slack Workshop Data, T20S, movies, here now we want to select all the TIFF files. And if you actually click on the scroll or pages at the bottom, you'll see that along with TIFF files, there are a couple of other files in this folder. We don't want to select those files. So what we're going to do is modify this path manually to add a wildcard. So we can type / and then star.tiff. I'm just going to zoom in here so everyone can see what I did there. Star.tiff. Oops. That's what we want to add to the end of the path here. So I can zoom in like this as well. Yeah. By clicking enter, don't click select yet, although you can and it's not a problem, but if you click enter into the path bar now, you can see that now the total set of movies has been filtered, and now there are only 20 items and there's only one page. And those extra items that we had previously seen are not listed anymore because they don't match this wildcard. So here we can be sure that we selected all the TIFF files that we want and click the select button. So that wildcard path now becomes our choice for this parameter, which is the movie data path. Next, we want to select a gain reference path. So there we can click on the browse button again. And in the same directory, you'll notice that right now the bar is populated with the previous path that we used. Here, now we want to select a different file. So I'm going to clear out this wildcard so we can see everything there and go to the second page. Now we can see that there are a couple of other files here, an info file that we don't need, and this special file, norm amibox05-0.mrc. This file is the gain reference for our data. And in general, for single particle CryoEM data, the by far recommended way to collect and store the data is to have the movie data compressed and to have the movie data not be gain corrected at the microscope, but rather be stored in a non-gain corrected fashion and have the gain correction files stored separately. That's what actually allows us to compress the data in the first place. After gain correction, it's very hard to compress the data. So the gain correction is stored separately. In this case, we can go ahead and click on this MRC file, selecting it, and that becomes our selection. Now we can click the select button for the gain reference path. So now that those two parameters are set, we've told CryoSpark where is the data that we're trying to import, where's the gain reference, and now we can fill in the other parameters that it needs to know. In many cases, depending on your camera settings and how the data collection was done, the gain reference may be inverted or rotated relative to the actual image data. That's something, unfortunately, you have to either find out from your data collection facility or see by trial and error when you import the data and the images clearly are not gain corrected correctly. In this case, the gain reference is the right way around, so we don't need to change any of these parameters. We need to provide the raw pixel size, so that's 0.6575, and it's very important that you get the pixel size correct, at least close to correct right now, because otherwise CTF estimation and many other things will get thrown off. The accelerating voltage for this data set was on a Titan Cryo, so that's 300 kilovolts. Spherical aberration for Titan Cryo is 2.7, that's without a CS corrector. And the total exposure dose is 53 electrons per square angstrom. Everything that I'm doing here, by the way, is mirrored in this set of instructions on the left in step number 3. So we've selected our movie path, gain reference path, and now entering these 4 parameters. As soon as you're done entering those 4 parameters, and I'll just give a sec for everyone to do that. Okay, as soon as you're done entering those 4 parameters, we can go ahead and click the Q button. That Q button shows us the queue dialog. And this is a dialog that lets us choose how we want to queue our job so that the CryoSpark system and scheduler can run the job at the right place at the right time. On this system configuration, there's only a single lane, which is the only place where we want to be able to queue our jobs. And so we're just going to go and select that. It's already selected, and we can click the create button. Now you'll see that the job has briefly entered queued status, and then launched status, and then started status. And immediately after that, this window opened up, which is the inspection panel for that job. I'm going to close this window so everyone can see how to get here again. Right now, our job status has entered into running status, and the job is now starting to create some images, which is what we want to see. If you select the job and click on the job number, you'll see a little magnifying glass. Alternatively, with the job selected, you can press spacebar. You'll come to the job inspection panel. And this is what was also described in our UI overview earlier. On the job inspection panel, there's a few tabs that have different information about the overview, the actual outputs of the job, inputs and parameters that were set, and so on. At this point, what we want to do is just verify that this job is doing what we intended for it to do. So if we look here in this left side section of the overview panel, there is a bunch of logs that are coming out of the job. It's telling us that it's loaded 20 movies, and it's starting to make some example plots. So it's reading a file and then showing us the raw image for this particular movie data. For those who are experienced at looking at CryoEM data, you'll be able to immediately tell that this micrograph has a lot of motion blur in the up and down direction. And it's clearly containing proteasome particles. You can by eye see the particles here already. The circles are top views, and the 4 lines in a sort of pattern are side views. Here's another image and another image. So that's what we want to see. To navigate through the stream log, there are a bunch of buttons up at the top here. One of them, called Show from Top, lets us see the log of the job from the beginning when the job was started. So if we click that button, we'll see some extra logs that were there before. The job started on a particular node. It lets us know what resources were allocated to it. If we had needed any GPUs or anything, those would be listed here. And then it starts to tell us what it's doing, importing movies from the place that we specified, importing 20 files, and so on. So that's how much we need to see about this job right now. We can also see on the right-hand side of the overview page, there are outputs. And each of these outputs is a small draggable object that can be used to connect the outputs of this job as inputs of the next job that we want to start. So we'll come back to that in a moment. At this point, we've finished step number 3. And I'm going to go through a set of slides to describe how motion correction works in CryoSpark. But in order for the processing to be happening behind the scenes, we're actually going to start a patch-based motion correction job right now using these movies that we've imported. So we can leave this overview page open or close it, either way is fine. Going over to the job builder, now what we want to do is find a patch motion correction job. That's in the motion correction section, and it's called patch motion correction. So we're going to click on that to create that job type. We can see now here that that new job that we created is called job number 2, and it's active in the builder. If I close this overview panel, you'll see that job number 2 is now also created here, and it's in building status, as I said before. So this job now has an input. It needs movies to be able to process them. In order to fill in that input, which right now is highlighted in red, meaning that it's not filled with anything usable, we can open up job number 1 again, the inspect panel. And on the right-hand side of the overview page, we see the output section, and we can take the imported movies from there, drag them by their handle, and directly drag and drop them over to the green highlighted movies section here that will connect the output of our import job as an input to our motion correction job. This is generically how we connect jobs together in CryoSpark to form chains of processing. And that's enough about that right now. The other parameters of this job are things that we don't need to change. We'll be using default parameters right now. I'll explain what some of these are in the slides as well as in the advanced part of the tutorial tomorrow. Here, if you notice, if you turn off, actually, never mind. For motion correction, like I said, we don't need to modify any of the parameters, and we're going to go ahead and queue this job as well on the default lane. So what we'll see now is that our second job has started. If I close this inspect panel, we can look at it in the tile view. Job number 2 is now running, and that job is now starting to process some data. When it started, it, like I explained, listed the resources that were allocated to it. It has a particular GPU on this node, several of the CPUs, and it will continue processing as it needs to.
Great. If possible, would this be a good time for some quick fire questions?
Yeah, sure. Let's do that.
Great. So these will mostly focus on motion correction and importing data, as we just saw. So the first question is, I'll actually combine a couple of them. So first, how can you know what the correct pixel size is? And and why doesn't CryoSpark read the pixel size directly from the movie header?
Great question. So you generally know what the pixel size is based on the magnification that was set at imaging time. If I'm not mistaken, most data collection facilities also go through a pixel size or magnification calibration procedure where they take a picture of something with a known size or spacing, for example, a gold grading or something like that. And because it has a perfectly known size to atomic precision, we can measure the actual magnification of the microscope. And that's what you would use as the pixel size here. So that needs to be provided from your data collection facility. And secondly, the reason we don't read the pixel size straight from the movie data is that in many cases, at least until recently, and maybe this is less true now, there were so many different data collection softwares being used at the microscope, and many of them didn't create headers in the same format or misspecified the pixel size, and it created a lot of problems. So we opted to always make sure that the user provides the pixel size from data collection time.
Great. Another few related questions. One is, can you also provide a camera defect file?
You cannot provide a camera defect file right now, but CryoSpark does automatically detect defects in the images based on hot pixels and other characteristics. We're actually working on support for defect files in particular formats.
Perfect. Next few questions are related to gain reference files. So first of all, where can I find the gain reference if there is one? What are the acceptable formats that CryoSpark will intake? And what is meant by flip gain in X and Y? When do I use those options?
Great question. So the gain reference generally will again be provided to you from your data collection facility. Depending on how they collect the data, like I said, they will have the option to either pre-gain correct the data, in which case you don't need a gain reference, but the files will be much larger and clunkier, or to not pre-gain correct the data, and in which case they will give you a gain correction file and the raw image data together. And that's a common practice. The second question was, what are the formats supported for?
Formats supported for gain reference.
We only support MRC format gain reference files, not DM4, but those are generally easy to convert. And the last question was, what are flip X and Y? I can quickly show you what those mean by taking this import job and cloning it. That creates a copy of the import job with the same parameters and inputs. And here I'm going to choose the flip gain reference and Y option. What that does is when it loads the gain reference, it will flip it upside down and apply it to the images. The reason we have these options is because a lot of times the gain reference is collected in a way where it's not in the same orientation as the camera when it's actually in imaging mode. I'm not sure why that is the case, but often the gain reference is upside down or sideways or rotated, just in the way it's stored. And so what you'll see if you have the gain reference in the wrong direction is a pattern like this. I'm just going to close this so you can see it a little bit smaller. You can clearly see here that the image data itself has gain artifacts like bright and dark spots in one direction, whereas the gain reference now being applied upside down is correcting them in the opposite direction and therefore causing this aberration. So when you see something like this, you know the gain reference is the wrong way around.
Perfect. Thank you so much. Just a couple more.
Yeah.
Oh,
Sorry.
okay. So I have just a couple questions from the webinar chat end of things. There is a question about let's see, where was that? Oh yeah. How do we decide on the type of motion correction that is needed for our images, whether we should use patch, local, or full motion correction?
I'll be talking about that in the next few slides in detail.
Okay. And
I think we're looking at the same set of questions.
oh, we are? Okay, because
Yeah.
I see
There's
some of
so many.
some that you have that I don't see. So
You know what's interesting about Zoom? Yeah, you know what's interesting about Zoom that I've just realized is that the questions are not sorted in a normalized time zone format. So if you're in Pacific time, you'll see a certain order, and if you're in Eastern like us, you'll see a different order. So that
yeah, I see some questions here that are 3 a.m. questions. They must be European questions or Eastern European questions.
I think, Michael, in general, you can leave the question moderation to us. I believe Sarah and the others are
okay.
on the channel, so we'll catch everything.
Okay.
Yeah.
Oh, one question that I had is there a facility for refining or somehow discovering later that your angstrom per pixel needs tweaking by, you know?
Definitely. So there are two ways in which that is possible. One, after you do a full refinement, the pixel size itself will end up getting it's a free parameter in terms of the rest of the CTF parameters in a sense. So if the pixel size is a little bit off, that will mean that the estimation of the defocus and astigmatism and so on during CTF estimation is a little bit off in the opposite direction, canceling each other out more or less, not precisely. And so what will happen is that the reconstruction you get, let's say if your pixel size is off by 1%, the reconstruction that you get at the end of the day will be scaled 1% big or small compared to the actual distances that atoms should have in between each other. So when you're building an atomic model, you'll find out that you build the atomic model and it's just a little bit off in terms of the scale. And so at that point, you can detect that the pixel size was a little bit wrong. That's commonly done. It's also possible, there are methods not implemented yet in CryoSpark for dealing with anisotropic pixel sizes in case there's some kind of anisotropic magnification distortion in your microscope. That's a very advanced processing topic and generally doesn't make too much of a difference unless it's a very, very large protein. But that's also possible.
Thank you.
Just 3 more, I think, to wrap it up. And then all of the motion correction related questions I will bring up again once we've covered that section in the slides, because I think some of them will be answered at that point. Perfect. Does CryoSpark support or import DM4 format files?
No, DM4 format files are not supported. You have to convert those to MRC.
Perfect. Can the total exposure dose, which is something that we entered in the import movies job, be edited later on?
Yes, great question. It can. Each of the jobs that performs dose weighting, which I'll talk about in the slides, has a parameter. I'll just show you that for the patch motion job to override the dose rate. So if you discover that you entered it wrong at import time, that's fine. You can modify it at motion correction time. You can also redo motion correction later with a different dose rate. In our hands, getting the dose rate a little bit off one way or another tends to not make very much difference, almost at all. But it may not be true for all data sets.
Great. Last one, I think, before we can head off maybe to motion correction. What pixel size should I use if the movies were binned during motion correction? For example, the data was collected at 0.55 angstrom super resolution and binned by 2 in motion correction. What does binning do?
Great question. I will cover binning. So binning is actually something I'll cover in an advanced topic tomorrow for motion correction, but to answer the specific question, it depends on whether you're importing the raw movie data or you're importing the micrographs from motion correction that was done outside of CryoSpark. If you're importing the raw movie data, you should use the 0.55 angstrom pixel size, which is the actual pixel size of the super resolution movies. If you're importing the micrographs that came out of motion correction in a different program, those should be imported with the pixel size that they are stored in, which is double the pixel size of the original movies, since the binning was a factor of 2. Binning is the same as downsampling the images. So it's like the image was very high resolution and we didn't need that much resolution, so we shrunk it to twice the pixel size, half the resolution. And so that's the resolution pixel size that you should use for importing the micrographs. In general, though, we would almost always highly recommend doing the motion correction in CryoSpark, and I'll explain that in the slides. It makes everything downstream a lot easier as well. So.
Thank you. We have several other questions. Like I said, some of those will apply to future sections, and others which we haven't been able to answer now, we'll try and type out a response as soon as possible.
For sure, that sounds good. Okay, then what I'm going to do is switch back to the slides. And hopefully all the practical participants have been able to get this far. It may be that some jobs were queued because of resource contention on these servers, but in a couple of minutes, everything should be fully finished. Okay, so we did all that. Okay, now to talk about motion correction in terms of algorithms and methods. So the general problem of motion correction is somewhat straightforward. In real life, computing motion estimates and correcting for them, there are a lot of detailed things to take care of. But from an intuitive conceptual perspective, what we're trying to do is, out of the microscope, we're collecting data that is in the form of a series of frames, each one collected at a particular time, each one containing only the electrons that arrived at the detector in a small space of time. So it's exactly like a movie of frames. And what we're trying to do is, by looking at the content of those images, track the motion of the sample through time to find out how the sample was moving so that we can undo that motion, align all the frames and average them together after correcting for the motion, and arrive at an aligned averaged micrograph, which is as close as possible to the image that we should have collected had we collected the image in one shot with no motion happening in the sample at all. That's what we're trying to get. We're trying to basically undo the motion that was happening during the time of exposure. The motion itself happens for two reasons. One of them is global full frame motion, that's caused by stage drift. And that generally happens in all microscopes because there's a small amount of vibration left over after the stage is aligned to a new position. And that stage vibration and just other vibrations at the angstrom level cause the sample to be moving relative to the beam and relative to the optical axis. That motion is generally relatively jagged in time, in the sense that it can have sharp accelerations or jitter, but it's very uniform. The entire image will move together over time in the same direction. The other kind of motion is local anisotropic motion. And that happens because of sample deformation, energy that's deposited into the ice by the beam, or energy that was already trapped in the ice due to strain forces that were locked in during the freezing process, is released while the imaging is happening. And so the energy from the beam and the change of temperature and so on together is causing the ice to literally deform and bend as the electrons are going through it. That deformation is generally a little bit smoother over time, but over space, it can be highly anisotropic. Different parts of the same image can be moving in different directions at the same time. And so both of those types of motion need to be estimated and corrected for to get really high resolution reconstructions out of the data. Since at the end of the day, if there's motion in the image that isn't corrected for, that literally means that over the time of the exposure, a single particle will be moving by some distance. Let's say it's 5 angstroms. Because of that motion, the signal from the same atoms that is coming in one frame is in a different place in the next frame and the next frame. And so that signal is being smeared out and lost, and we can't recover the three-dimensional structure at a high resolution if that is the case. So the general problem of motion correction from a computational perspective is that we're given a bunch of frames. Or to generalize it a little bit, we're given a bunch of patches of images. Those patches may be an entire frame, or they may be just the space around one particle or anything in between. So we have a bunch of image data over time. We're trying to find a motion trajectory, which is here what I'm showing in this black and red line, a motion trajectory over X and Y motion, with each dot representing the position of the sample from frame to frame. So in this image, we're saying that the data is starting, the sample is starting at this position, moving to the right, and then turning upward and moving upward, and then changing direction again and continuing to move upward. So that trajectory, which we don't actually know ahead of time, is what we're trying to estimate, so that when we apply this trajectory to the data by essentially shifting each image in reverse of what the motion trajectory suggests and averaging all the images together, we end up with the aligned average that has the highest amount of signal and the least amount of motion blur. The noise from the images, which are the frames, will also start to be averaged out, since if you think about how much signal there is in a single frame, there may be on average less than 1 electron per pixel going through the sample in each frame, which means that the whole image is basically like a very, very grainy picture taken at night with an old camera. You can almost see nothing. There's just a few electrons scattered here and there. But as we average frames together, we'll end up with more and more signal, since each frame has more and more information about the sample. That's what we're trying to get at the end of the day. The process of actually finding the motion trajectory is the hard part of motion correction. And most techniques, or all motion correction techniques, start off by formulating the problem as a maximization problem, trying to find the motion trajectory out of all possible trajectories that maximizes some idea of a matching score between the aligned average and the frames. Both global and local motion can be thought of this way. And that's how we also set up the problem in CryoSpark. What we use in CryoSpark to actually solve this problem in both the full frame motion and local per particle motion problems is a variant of an algorithm that was originally written by, or a paper that was written by John Rubenstein and Marcus Brubaker in 2015, called Align Parts LMBFGS. You don't have to worry about the acronym stands for, but the overall concept is to align particles by solving this optimization problem. The way it's set up is that we want to maximize a cross-correlation score that measures how well this aligned average matches up with the frames after shifting the frames to their correct position according to the motion trajectory that we don't know. For every given motion trajectory, we can measure this cross-correlation score, and then we can optimize that cross-correlation score by searching over the space of possible trajectories. And that search or optimization is carried out with a gradient-based quasi-Newton optimizer. I won't get into the details of that, but it's essentially a very efficient way to find the optimum trajectory given the data. One key aspect, one key principle in the aligned parts method, and what we actually do in CryoSpark in practice, is that there's a smoothness penalty, which encodes the fact that we know that in real life, motion trajectories of our sample can't be infinitely jagged. They can't have very, very large accelerations from one frame to the next. The reason we know that is that this thing that's moving is actually a physical object, so it has some finite mass and therefore takes time to accelerate in any direction. And the reason this is very important is that the image data is so noisy that if we don't apply any prior knowledge about what motion trajectories are plausible, the optimal motion trajectory is actually going to be one that's very noisy, that's corrupted by all the noise in the images. And so having the smoothness penalty is a really important piece of the puzzle. And basically all motion estimation methods out there have some version of this smoothness idea, either more or less explicitly. And that, like I said, is very important. If you imagine what happens if you start to take some image data and find the optimal trajectory given that data without any smoothing, the trajectory might look something like this. It's very jagged, and we know intuitively that from one frame to the next, the sample really shouldn't be accelerating and changing direction so fast. If we apply a little bit of a smoothing penalty, then the optimal trajectory that we get from that smoothed version of the problem is this red line instead of the black line, which was the original one. That red line you can see now captures the overall motion without too much corruption from the noise that is creating that jaggedness. But there's a big question, how much smoothing should we really apply? If we apply a little more smoothing, we get an even smoother trajectory. But who's to say that this red line is better than that one or that one? And this is a fundamental problem of estimation of all kinds. And the same problem occurs also when we're dealing with motion of individual particles. we don't know how jagged is the motion of the particles over time. The next image I'm going to show is an estimate of motion trajectories for a whole bunch of particles in one of these images of the T20S proteasome that we're looking at. Without any smoothing, each red line here, you can barely tell that they're different. Each red line is one trajectory of a single particle. Without any smoothing, all of the particles have very jagged and almost random looking trajectories, which definitely don't look good intuitively. With a little bit of smoothing, we can start to see that, in fact, there is a huge pattern of motion for every particle. We can track each particle in different parts of the ice moving in different directions. But again, there's a question of how much smoothing should there be. Is this much enough, or should we add a little more smoothing, or a lot of smoothing to the point where each trajectory becomes just almost a straight line? It's hard to answer that question. It turns out there is a principled way to answer that question using a cross-validation method. And this is something that we developed years ago in CryoSpark. Never actually wrote anything about it, but it's the basis for the CryoSpark motion correction algorithms that we use. And it's a cross-validation approach for data-driven optimal smoothing of motion trajectories. The way it works is by taking micrographs and doing motion correction by holding out one frame at a time. So let's say we hold out the middle frame from a movie and do motion correction with the rest of the frames from the movie. Then we can take that held out frame from the movie and measure how good our estimated motion trajectory is on that frame across different levels of smoothing. And that's obviously, that sounds like a very computationally burdensome thing to do, but we were able to come up with a clever algorithm to compute that smoothing property, basically this curve, which measures the cross-validation error against smoothing strength. And we're looking for the point where that error is minimal. And that point is actually the optimal, according to the data, smoothing level for the trajectory. Newer techniques for motion correction also use a very similar idea to this to optimize over the smoothing parameters or train them against some data and cross-validate on other data. So that's how CryoSpark motion estimation works in terms of an algorithmic perspective. In practice, what this means to apply an approach like this, I should just say that the optimal smoothing can be computed without any tuning parameters and quite fast. What this means in practice is that motion correction has to be done, at least with this method so far, in two stages. One, where we find the overall full frame motion trajectory. So in CryoSpark, if we look at the job types, there are, I'll just switch over to CryoSpark right now. If we look at the job types and look at the motion correction section, there's a full frame motion correction job. And that job estimates only the rigid part of the translation in every movie. And then there's a local motion correction job, and it estimates the trajectories of each individual particle. Now, in this approach, you can probably guess that in order to apply these methods, the full frame motion correction job can be applied to the raw data itself, but the local motion correction job needs to know where the particles are so that we can track each one of them. It doesn't make a lot of sense to be tracking an empty patch of ice since there's no signal there to track. And so to apply these two methods, full frame motion and local motion correction, the standard workflow is import the data, use full frame motion correction, do CTF estimation, pick out the particles, decide on a good set of particles, and then take those particle coordinates and feed them back into local motion correction to correct for per particle motion at trajectories, and then carry on processing. That's a bit of a cumbersome workflow, and because it has a loop in it, it's a bit annoying to do in real life. It also means that you have to hold on to the movie data a lot longer. You can't just throw it away as soon as you've finished motion correction. So in the latest versions of CryoSpark, we've actually developed, this is about maybe a year or so old now, a new patch-based motion correction algorithm that uses the same fundamental principles that I've just described, but doesn't need to know where the particles are, and instead operates on cut out ordered patches of the micrograph, interpolating motion trajectories in between those patches so that if there is a particular particle in a certain place, we can figure out its exact trajectory as well. And that patch-based motion correction essentially works by cutting up the micrograph into squares that overlap and then using those as the patches for aligning the motion and having a smoothness constraint, just like before, that connects patches that are nearby to each other. So we know that two patches that are close to each other can't be moving in opposite directions very often. And that's the smoothness penalty that we apply. So this now single job in CryoSpark, patch-based motion correction, now performs both rigid motion correction, so that's full frame motion estimation, and local sample deformation, so that's local anisotropic motion correction together at the same time. You don't need to know the particle positions. It tunes itself automatically, as I said before. and performs interpolation to create motion-corrected micrographs as the output. And it applies dose weighting as well, which the previous jobs did as well. The dose weighting is done by using a set of dose weighting schedules developed by Nico Grigoriev and Tim Grant in 2015. And in this dose weighting scheme, what happens is that each frame of the movie, as you move further and further in time forward, each frame of the movie is trusted less and less for high resolution details. The reason being that at the early frames, there hasn't been much radiation damage accumulated in the image so far. So the early frames have a pristine, ideally, hopefully very pristine image of high resolution atomic level details of the sample. Whereas as you go further in time, the later frames have, they contribute more contrast to the image and more signal, but at the very high resolutions, because of radiation damage, some atomic bonds have been broken, some side chains have fallen off, some changes have happened. And so we don't really want to trust the very high resolution details from later frames in the movie. And so what this dose weighting scheme does, if you look at this plot, I'll have to explain it for it to make any sense. The x-axis is a frequency axis. So 0 is the constant frequency, and large numbers are high frequency components in each image. So for example, atomic resolution detail would be at the right end of the range, and very low resolution sort of blobby structures of proteins would be at the left end of the range. Each line represents one frame in sequence. So the first frame, the green line, its weighting is something at the low frequency end, but its weighting is very high at the high frequency end, meaning that we trust it a lot. As we move forward in time, each frame gets the same weight at the left end of the range. So at the low resolution terms, they're all contributing equally. But at the high resolution terms, let's say at this 100 frequency point, whatever that happens to be in terms of angstroms, the first frame contributes a lot, the second frame contributes a little, and the subsequent frames each contribute less and less as time goes on in the movie. So that dose weighting is automatically applied, and these dose weighting curves depend on the total electron dose in the image. So those dose weighting schemes are applied during motion correction. And this whole process now with the latest versions of CryoSpark that we've engineered and tuned very finely is super fast. It takes less than 10 seconds, often far less than 10 seconds per movie on a GPU on a reasonably well set up system with the right input-output bandwidth for disks and SSDs and so on. So that's actually the job that we're using right now in CryoSpark. So if I switch back to CryoSpark and show this, motion correction job that we had created before, I can now just show you plots from this job that mirror the what I was saying earlier. Showing the log from the top, we can see that the motion correction job started processing movies one at a time. Since we're only running it on a single GPU, it is noteworthy that this job is parallelizable over multiple GPUs. One of the parameters that we didn't change, but we could have changed, is the number of GPUs to parallelize. So you can set that to 3, 4, 10, however many GPUs you have on the same node. In the actual output, we'll start to see some plots that look like this. So the first 3 plots here are showing us the rigid motion trajectory for a particular micrograph. And that's showing us first, in the first plot, these axes should be labeled, but in the first plot, the X and Y coordinates of the trajectory. So we can see in this image, the sample starts off with a low Y value and then moves upward over time, meaning the blur is in the up and down direction. The next 2 plots show us over time, the X motion and the Y motion separately. So we can see if there's any jaggedness or whatever it is. But essentially, these 3 plots are all showing the same information. There's also a local anisotropic motion plot here. These images, due to the sample quality and thickness of the ice and so on, don't have a huge amount of anisotropic motion. You can see that there's a pattern, though, that most of the patches and particles in them are moving away from the center of the image. And that is usually because what happens in most cases is that the ice domes as the beam goes through it and energy is deposited. And that doming means when you're looking at it head on, in the middle, you don't see any motion since the particles are just moving up and down. But at the sides, you see particles moving away from the beam. So that's a common pattern that you probably will see. You may see lots of other patterns too, depending on what's going on in the sample. And these images are more or less pristine as far as they can possibly be. So then finally, we can see the non-dose weighted aligned micrograph for this image. And the job outputs both dose weighted and non-dose weighted versions of each micrograph. So that is, I think, everything I want to say for motion correction right now.
If you're okay, we have another many odd questions that I can deliver. So the first sort of general subset of questions is if you can explain again at a high level, what is the difference between the 5 different motion correction job types that are available in CryoSpark and what they do specifically with respect to which type of motion are they correcting for? And perhaps what does the workflow look like if you were to use one over the other, and
Great
when?
question. Great question. So there are 5, like the users or questioner said, there are 5 different motion correction jobs in CryoSpark. One of them, which I'll just write off at the beginning, is a wrapper around Motion Core 2. This is present in CryoSpark for legacy reasons from a time before we had developed these motion correction techniques. We don't generally recommend using Motion Core 2 anymore because it almost always delivers worse motion corrected results than the other techniques. And it's also slower in many cases. So for full frame motion correction, that's the first job listed here. That job does only one thing, which is correct the rigid motion of the sample. So that's stage drift only, not correcting local deformations in the sample. So by itself, that's not usually enough if you're looking for high resolution results. And that job is labeled with the little keyword name called multi, and that just means that it's implemented for multi-GPU parallelism. There's also local motion correction and local motion correction multi. Those are actually the same job, but one of them just supports multi-GPU processing and one of them doesn't. And again, that's only there for legacy reasons. You should use the multi-GPU one whenever you can. The local motion correction job only performs correction of anisotropic sample deformation. And so in order to use it, you would have first had to apply the full frame motion job and then somehow get coordinates of particles by particle picking, and then come back to this local motion correction job to correct for particle motion trajectories. That was kind of the old CryoSpark 2.6 way of doing things. Nowadays, we recommend across the board to use only patch-based motion correction. In our hands, it delivers equally good, in almost all cases, equally good motion trajectories and correction as the previous workflow, but it's just one step that does everything and it's much faster. And once it's done, you don't need the movie data anymore. So in a lot of projects, if the movie data is very large, you can bring it into CryoSpark, do the motion correction, and then either archive or remove the movie data. We don't recommend deleting it because you probably want to keep it as long as you can if the project is still active. But this patch-based motion correction job does everything in one shot. There are a few cases for very high resolution structures where local motion correction can do a little bit better. But for most projects where you're working on something biologically interesting and you're not looking for a 0.1 angstrom increase in resolution for a lot more work, it's worth just using patch motion only. And in a lot of cases, it actually just does better. And I'll explain why in the slides, or I'll explain why in a case study a little bit later.
Perfect.
Did that answer all the questions? Yeah.
Yeah, we have a few more. Okay, so the next sort of set of questions relates to whether motion correction considers only the X and Y axis and or also the Z axis when it comes to aligning movies.
That's a great question. The Z axis can't actually be dealt with at this stage because we have, without a little bit more information that comes down the line, and I'll talk about that later, we don't have enough information yet to detect motion in the Z axis. Since if you think about what's happening here at a high level, the electron beam is passing through the sample. The electrons are diffracting from atoms in the sample. But by and large, what we're really presented with at the detector is a projection image of the sample. That means the Z information is lost. We'll come back to that in a minute because there is actually a way to estimate the Z information. But by and large, in the image, we can't tell if a particle moves up or down. It looks exactly the same in a projection. The only difference, and this is what we'll come to, is that the image moves further into or away from the focus plane, the focal plane of the microscope as it moves up and down. And that's something that we can actually detect with some other approaches during CTF estimation. So far, though, it's not common practice, or actually there are very, very few programs that do it, and almost no one in practice who's doing this to measure the change of height of the particle during the movie. Mostly the reason is that there's just not enough signal. If you look at a signal frame of a movie, you cannot even see the particles, let alone hopefully being able to measure their Z height based on their focus.
Thanks. The next set of questions or question is relating to the actual data or number of frames and making choices about subsets when it comes to motion correction. So first of all, do we need to throw away any of the frames? Is it better to do motion correction on a certain subset? And specifically, what happens if our dose is actually differing across the entire set of frames?
Very good question. So there was a time when it was common practice to discard frames at the beginning and end of a movie that was collected. And that was mostly because the technique of dose weighting wasn't widely used at the time. The reason for doing that is twofold. One, on the tail end of the movie, the last frames, you don't really want them because they only contribute signal from radiation damaged specimen. So when you're looking for high resolution results, assuming there's enough signal at the low end for doing things like particle picking and alignment, in intermediate frames, you don't really want frames too far out because they only contain radiation damaged sample. With dose weighting, that's kind of taken care of for us automatically, since later frames are only used for their low resolution contrast that helps us do particle picking and alignment, not used for high resolution information. So that's kind of taken care of already. The second part is throwing away early frames in the movie. That was done, that is still sometimes done because it's well known that for a lot of samples, the first couple of frames, maybe 2 or 3 at most, have so much motion that it's impossible for the motion correction algorithms to detect and correct that motion, or there's so much motion within the time span of a single frame exposure that that can't be corrected. And so early frames often have uncorrected motion that ends up just adding more motion blur than signal. Nowadays, though, it's pretty rare to see people throwing away frames at all. Motion correction has gotten good enough where those early frames are still useful, if not perfectly useful, and there's a chance that maybe advanced motion correction will make better use of those early frames. But these days, we would recommend not throwing away any frames, unless you happen to know that on some cameras, for example, there's a bug in the software where the last frame is corrupt, so throw away the last frame. But other than that, you shouldn't throw away. If you do want to throw away frames, you can do that in the motion correction jobs with a parameter that is called start frame and end frame. So you can choose where you want to start and end out of the set of frames in your movie. And the last question was about what happens if your last frame has more dose than the others, or other frames are differently dosed?
If perhaps your first frame has higher dose than the others, I think was the question.
To be honest, I've never seen that, and I'm not sure how you would actually end up getting that in a data collection setup. As far as I'm aware, the common practice is to have all the frames be equal in terms of their dose. So unfortunately, I can't help with that one.
Great. Next, couple of questions about the motion trajectory plots themselves. Can you please tell us about the units on the X and Y axis of those plots?
Sure, yes. Yeah. So on the X and Y plots, now this is a question it's best to re-ask on our discussion forum in case I give the wrong answer right now. Don't trust me perfectly, but I'm 90% sure that the X and Y plots, X and Y axes here are in units of pixels in the pixel size of the raw data, not in angstroms. So in this case, with a pixel size of 0.65, this 30 pixel translation translates into like some 15, 17 angstroms, which is actually a lot if you're looking for a 3 angstrom. I mean, it's way too much if you're looking for a 3 angstrom structure.
We have a lot of questions. I'm just trying to pick the ones that are coming up a bit more frequently. Next set is about patch-based motion correction. So specifically, how are the patch sizes actually determined? Are they different for different camera types, like let's say K2 versus K3? And what happens when your patch, or let's say you have particles at the edge, what happens to those patches? Are those discarded? How does that influence the overall result?
So the number of patches and their spacing is automatically determined by patch CTF, and we tune those based on a few factors. One, the image size, so that comes down to what kind of detector that you used. Two, the magnification. So what we try to do is that each patch should correspond to the same amount of physical space. So if you're at a very high magnification, then you need fewer patches. If you're at a very low magnification, you need more patches. So that's all automatically figured out. It's also the amount of smoothing also depends on the number of patches and also on the length of the movie and the total dose. It turns out it doesn't really matter how long in real time, like wall clock time, a movie took to capture. It's all about the accumulated energy. So the length of the movie is actually measured in the electron dose. So a 50 electron movie is shorter than a 100 electron per square angstrom movie. So that's another way that we automatically tune the smoothness over time based on the dose rate, essentially, per frame. So those things are all automatically done under the hood by patch-based motion, but there are parameters if you want to override some of those things, which are the number of knots. I won't go into detail what this means like under the hood of how this is implemented, but they essentially control the amount of smoothing if you want to enforce that automatically, or sorry, rather manually, over X, Y, and Z. So for example, you want to enforce that your motion trajectories are absolutely linear in time. So each particle can only move in a straight line, but they can all move in different directions. You could set the number of knots in Z to 2. Sorry, I can't type here, but you could set that to 2. And that would mean that there are only 2 degrees of freedom in the trajectory over time for each particle. That's not recommended. And generally speaking, the auto tuning works very well. So we've never actually changed these parameters manually for any data set that we process. I don't know if it's common in practice, but I would bet that it's not. I think we should probably, unless there's something very important in the questions, I think we should probably cut it off there and move on to CTF estimation in the interest of time. Yeah.
Yeah, whatever we're not able to get to right now, we'll definitely try and get to a little bit later.
Yeah, for sure, for sure. Okay, so that is motion correction. The next stage of cryo-EM data processing that we're going to talk about is CTF estimation. And this is something that the earlier morning lecture by Dave DeRosier, Dr. DeRosier was very clear about how important it is and how something like CTF estimation could work. In practice, the problem that we're trying to solve is that we're given an image from the microscope, and that image is of a sample that is at some particular plane, hopefully in the microscope, and that plane may not coincide with the focal plane of the lens system. If it did coincide with the focal plane, we would be at, well, I mean, depending on how you define the focal plane, we would be at some natural definition of focus where, as was explained in this morning's lecture, there actually wouldn't be any there would be very little contrast in the image, so we wouldn't see anything. However, the image would contain a lot of high resolution information about the protein, but we just wouldn't be able to see the protein at low resolution to even find individual particles or be able to align them. So one of the main sort of tricks or dynamics with cryo-EM data processing is that you're trying to balance between having lots of low resolution signal so that you can see, find, and align particles. And the smaller the particle, the more signal you need to be able to see it, find it, and align it. And you're trying to balance that with how much high resolution signal you have so that when you do find the particles and average a lot of them together, you can recover ideally atomic resolution detail or near atomic resolution detail. So it's kind of a balancing act between those. CTF estimation is kind of the bridge where if we defocus the microscope, the image is now well out of focus. So we're corrupting high resolution information. But if we can accurately model and fit the CTF, we can undo that corruption. And at that high defocus, because we've increased the low resolution contrast thanks to the defocus, we can find and see the particles, we can pick them out. But with proper CTF correction, we can still recover the high resolution details. And so that's kind of how the whole thing works. Now, CTF estimation essentially means looking at this image and trying to detect its position in the microscope. Its defocus level literally corresponds to a height, Z height along the optical axis. It could also be modulated by the actual lens system itself, but if the lenses are fixed in a particular configuration and current and energy and whatnot, then the Z height is the same as the defocus. So we can measure the defocus literally in angstroms or nanometers in terms of its distance from the focal plane. In order to actually estimate the defocus, what we do is take the Fourier transform of the image, and in that Fourier transform, the magnitude of the Fourier transform now, looking at the spectrum, we see these things called tone rings. And the tone rings are what is present in the sample due to the fact that the CTF has a particular form, which was explained in the earlier lecture, that causes these rings. The CTF modulates only the signal from that's on the detector coming from elastically scattered electrons. And so, and this may be a slight simplification, but essentially the signal coming from the actual proteins and water molecules in the sample is modulated by the CTF. Everything else, like shot noise on the detector or other electrons that have somehow made it to the detector via multiple scattering or inelastic collisions, those are not modulated by the same CTF. And so when we see these rings in the Fourier transform, what that means is that we are seeing the effect of the signal present in the sample overlaid on top of the noise present due to everything else in the image, all the other reasons why the image is noisy. So the background behind the rings is due to all the noise and other electrons that we don't want. The rings come only from electrons that interfered with the sample and therefore are corrupted by this particular CTF. That's exactly why the more rings we see, and it's not actually about the number of rings, but the farther out the rings go in frequency space, the higher resolution information we can be sure that the microscope has captured, because those rings only appear if there's signal from the sample being captured in the image. And if you see a ring at, let's say, 2.5 angstroms, that means there is information from the sample in the image at 2.5 angstroms. There may also be a lot of noise, but there is some signal that is coherently present. Anyway, that's a small thing about CTF estimation. In terms of actually computationally estimating it, but basically the problem is an image analysis problem. We get this literal image that looks like a bunch of rings, and we have to fit a model of the size and ellipticity of those rings to it. The model is very constrained since the CTF only really has two parameters, the defocus and the astigmatism, and those correspond to essentially the spacing of the rings and the ellipticity of the ellipse. So we try to fit those parameters using the model. And what's most important about CTF estimation in practice really nowadays is that older techniques and most still widely used techniques tend to fit the CTF assuming that the image is in a single plane within the microscope. And that's something that we know is not true. When we think of the actual ice, the proteins may be at different heights in the ice. The ice may not be perfectly flat. The ice could be tilted, it could be bent, it could be any other shape. And it turns out that, oops, actually, I'm just going to go to the next slide before we get back to the practical. It turns out that it's now recently well known that single particle EM samples, this is a great paper, by the way, for anyone who's interested in this kind of stuff. Single particle EM samples, when you study them under tomography using tilt series, you can actually see and map out the positions of particles within the ice and the shape of the ice. And for a whole bunch of samples of different kinds, it turns out that the particles are never really in a flat plane. Often they adhere to the air-water interface and form these kind of concave shapes. And that's very common. But even in cases where you intended for the ice to be flat, because of crinkling of the grid and other strange deformations, in a particular square, in a particular hole, the ice isn't flat. And so particles from one end of the micrograph to the other have different defocus levels. They're at different positions in the ice. And that small, tiny difference actually makes a huge difference at very high resolution reconstruction. Since, like I said, when we're capturing images at a defocus level, we are assuming, we're relying on the fact that we can accurately reconstruct and accurately undo the CTF for every single particle to be able to recover high resolution information. So in CryoSpark, what we've developed is a patch-based CTF estimation technique, similar kind of motivation to the patch-based motion. Essentially, instead of thinking of the image as a single plane, we try to estimate a defocused landscape that also has some notion of smoothness and other prior knowledge about how defocus for micrographs should be. And that landscape is measured by cutting the image into small patches and then estimating jointly the defocused landscape across all the patches together, each one being allowed to have a different actual defocus value. They all share the same astigmatism and other parameters that don't change with height, but the defocus is allowed to vary spatially. And because of that, we're able to find what is the relative difference in defocus between individual particles across the micrograph. And this is something that we can do up front. There are other techniques that we'll come back to for refining the CTF. Once you've done a whole refinement in 3D of a structure, you can go back and try to refit the CTF to account for the differences in ice position. But it turns out that this technique works very well right away from the beginning. And in fact, in many cases of small molecules or flexible molecules, membrane proteins, this technique works a lot better than trying to do post-hoc CTF refinement. So we always recommend that everyone should use this. The GPU implementation in CryoSpark is extremely fast as well. It usually takes about 1 second or less on most micrographs. And it can also measure a ice thickness score. That's not an actual ice thickness value in absolute units, but just a relative measurement of the thickness of the ice, and I'll explain how that works between micrographs in the same data set. And this technique also, we'll talk about this more tomorrow in the advanced part of CTF estimation, can work directly on tilted data without needing to know the tilt or direction of tilt. bent samples, places where the ice is very curved, deformations, all kinds of other weird things. And it
Ollie?
just off the back. Yeah.
Ollie, there are people here who might be interested in tomography. Can this be applied at determining and correcting the CTF on an entire image of a tomographic tilt series, where each tilt series, of course, is usually made of frames?
Right. The overall algorithmic technique definitely can be, and I believe many of the tomography packages now that are available, especially more recently, do something exactly like this in terms of the overall algorithmic setup and construction of the problem. The particular implementation we have in CryoSpark, I honestly don't know if you could use it directly on tilt series data, since you kind of want to assume that in the tilt series, you're also you want to know that you're looking at the same object, whereas this algorithm doesn't know that different images came from the same tilt series. So in that sense, I'm not sure if it would be directly applicable, but definitely ideas like this are very much being used in the more recent tomography packages. Hope that answers the question. I think I'm not going to stop for other questions about CTF estimation yet. I'm going to switch back to the practical and start off CTF estimation, and then we can come back for questions. So at this point, you now have motion correction finished. And I'm actually going to switch over to our own CryoSpark instances rather than use the Stanford one, just so I'm not wasting resources that other practical students need. So I'm switching over to our own CryoSpark instance. And this one, I've processed the exact same data through just importing and motion correction. So what we're going to do next is go over to the job builder and find our patch space CTF estimation job. And you'll see that even for CTF estimation, we do have several job types. I'll just explain those right off the bat. We have 2 wrappers for older programs that, again, we don't recommend people use anymore, CTF Find 4 and GCTF. We have patch-based CTF estimation, and that's a multi-GPU enabled job. And we have patch CTF extraction, which is only a legacy job that is useful for projects that were done in older versions of CryoSpark that now want to use this algorithm and need to kind of jiggle with the metadata formats. So that one you don't need to use. Basically, you only need to use patch-based CTF estimation for just about everything. So you can create one of those jobs. And now, sorry, looking at our instructions, we created a patch CTF job. We want to connect the outputs of our motion correction job to the new job. That means we have the patch CTF job opener and builder here. Again, as a reminder, if you don't have that as the case, you can click on the job and then click on where it says building. Alternatively, you can, as a shortcut, you can select the job and press B on your keyboard, and that'll also get to building state for the job. Now we want to connect all the movies from patch-based motion. So we can open up job number 2, take the micrographs, connect them to patch CTF estimation, and carry on. Again, here we're going to use default parameters for everything. I'll explain some of them. More of them I'll explain tomorrow in the advanced session. We can choose to only process a subset of the movies if we want, or only plot a subset, which is by default only 10. We can change the amplitude contrast, which actually, if you import negative stain data, this number should be something more like 0.3. And that gets automatically set, or it should get automatically set when you import negative stain data and specify at the import time that it was negative stain data. Otherwise, you can change that manually here. We can also set the minimum and maximum resolution that we want to look at for CTF estimation. And this is, again, something that you may want to change for negative stain data or other data where, for some reason, the low resolution information in the image is very messed up. If it's like, I can't even think of a good reason, but you can change these parameters in some cases. We generally don't touch them. You can also change the minimum and maximum defocus search range. If you did collect data with a defocus beyond 4 micron, which I believe is rare, for most single particle stuff, it's between 0.1 and kind of 2.5, 3 micron as the range of defocus to consider. You can change that here. And if you're dealing with faceplate data, you can specify various phase shift search as well. And similar parameters for the knots in X and Y for the smoothness of the defocus landscape. I'm not going to change any parameters right now, just running this job on our instances here. And you should do the same thing on the Slack servers for whoever's watching doing the practical. So this job is going to start, and it will load up our movies and start processing them. And what we'll see are a bunch of diagnostic plots, and I'll just show you a few of them. The first plot that's shown is a 1D search over defocus for this particular micrograph. So now note that we're not looking at the movie data anymore. We're looking at the motion corrected micrographs that came from motion correction. So first we see that there's this 1D search. And what this diagnostic plot is really just showing us that over a bunch of defocus values of which we're searching, a particular defocus value here really stands out. So that's our initial guess of the defocus. The next one is an initial guess of the envelope of decay of the tone rings. And those two are used when we're optimizing and re-optimizing the 2D landscape. So these two don't really matter as long as they're close to correct, because both of them are re-optimized during 2D landscape fitting. The final plot is the real diagnostic plot that shows us the experimental power spectrum in black. This is now a 1D rotational average. So we're looking at the tone rings after averaging in circles or ellipses. The black line, the experimental power spectrum, the red line is the model from our CTF estimate. So the red line is what our physics model predicts the CTF should be, and the black line is what we actually observe. They match up very, very closely until a certain resolution where they start to be out of phase with each other. And this light blue line measures that correlation between them. And at a certain point, the light blue line drops below a threshold that's by default 0.3. And that's what we define as the CTF fit resolution, which for this data set is 2.73 angstroms. So after 2.7 angstroms, we can't be sure that we can see tone rings in the data anymore, but below 2.7, the tone rings do appear and they do corroborate with our fit model. That's a really good sign. Generally speaking, if you get CTF fits out to 3 angstroms or better, then you're sure that everything else about the microscope and its the sample itself is pretty good. You can't be sure about preferred orientation, about heterogeneity, about any of the other things like sample concentration and so on, but you know that you can detect high resolution signal being present. Whether or not you'll be able to use it is a different story, but there is signal present up to 2.7 angstroms and potentially beyond, but we can't see it in this way in this data set. I should mention that it's not true that your reconstruction will be limited to the CTF fit resolution. The CTF fit resolution is more of an early warning system, a proxy for how good the data is. There are many cases where your fit resolution may be 4 or 5 angstroms and you still get a 2.5 angstrom structure, or where you have 2.5 angstrom CTF fit, but you only get a 5 angstrom structure and so on. Yeah, but it's a pretty good estimator of how good your data is. The last plot I'll show here is what we use for estimating the relative ice thickness. And this is done based on the background noise that is present underneath the actual oscillations from the tone rings. Like I was saying before, all that power in the image, all the information in the image that's not part of the CTF, the tone rings, is there for a reason that we don't like. And for example, if there's lots of crystalline ice or just very thick ice in the image, there will be a lot of multiple scattering events and other things going on, and that will contribute a bunch of power to it may not actually be due to multiple scattering, but there will be electrons scattering from the ice. And those electrons will contribute power to a certain frequency range around, I believe, 3.5, 3.7 angstroms. So the more power there is in this background hump, the more ice thickness there was. So this is, again, a proxy, not an absolute measurement, but it's what we use to estimate relative ice thickness. And we'll talk about that more in tomorrow's advanced session as well. Okay, so that's CTF estimation. Our CTF estimation job is now finished, and it's got CTF landscapes for every micrograph. So we can go ahead and use that in our further processing. Okay. Should we stop for questions right now? Otherwise, there's just one more thing to talk about, and then there's a question break anyway. So I think maybe I'll just keep going. Sure. Great. Okay, so the next thing we want to do, now that we've been able to estimate the CTF landscape, motion trajectories, motion patch-based everything, we've now pretty much finished the pre-processing of our data, and we're ready to start looking for particles. But before that stage, for really large data sets, or actually data sets of any normal size, there are going to be a lot of images that aren't great. There are going to be maybe some subset of the total images collected on the microscope that are really good in real life that you can use for reconstructions, and a bunch that have carbon edges or broken ice or large crystalline patches of ice or no particles or too many particles or aggregation, whatever it is, contaminants and so on. So it's really important. Well, it's quite important, not absolutely critical, since you can also kind of just ignore that junk, but it's relatively helpful to remove that extra data that's not useful at an early stage like this. So for that reason, we've built an exposure curation tool in CryoSpark. And this is, without this kind of a tool, it's usually a tedious process to try and determine which images are good or bad. I mean, you realistically can't look at 10,000 images and by eye and pick each one. So having automated sort of population statistical ways to do this is important. And that's what exposure curation in CryoSpark allows. Primarily, we'll be curating exposures based on characteristics about their motion trajectories, about their CTF fit, or their ice thickness measurements. And generally, we're looking for anything that indicates that an image has plenty of particles, but the thinnest possible ice and the least possible motion. The motion criteria is not absolutely necessary. If you have lots of motion in all the images, you may still do fine, but less motion is better than more motion in most cases. So the next thing we're going to do in our practical is start an exposure curation job. This is the first interactive job that we're going to see in CryoSpark. So to choose exposure, it's called curate exposures. So it's called manually curate exposures, and you'll see this little icon that means it's an interactive job. We create that job, and we can take the micrographs that came out of our motion correction, our CTF estimation, and connect them to exposure curation. Exposure curation also works for micrographs where we've already picked out particles. Then we can curate based on statistics about the particle picking, but I won't show that right now. Queuing this job launches the job. This is an interactive job, so it doesn't really have any compute requirements. It actually runs just on CPUs only, and it's relatively lightweight. Sorry, I'm just going to get some water. And so the job can be run relatively lightweight and doesn't take up resources. Once the job starts, you'll see on the overview page that there are some logs here, but the interactive tab starts to show up. You can click on that interactive tab, and now you see on the left side a table of micrographs that are in our data set. This data set is very small, only having 20 images, so this is not really going to be very useful, but I'll just show you how the job works. In tomorrow's advanced session, we'll deal with a larger data set that actually has some interesting characteristics that we can curate. You can create on the right side in the overview panel a 2D scatter plot of any properties that you want. So for example, index is just the order of the micrographs, and then you can look at average intensity or astigmatism or average defocus or CTF fit resolution. And for larger data sets, you would start to see trends here. Like for example, if your image data, if you're looking at a square with very thick ice, your CTF resolution estimates would be bad. And then when you shift to a square with better ice, you'd start to see better CTF estimates and so on. You can look at total full frame motion. You can also plot these things against each other. So CTF fit resolution versus, CTF fit resolution versus full frame motion. Again, like I said, in this data set, there's so few images that we can't really see any trends. I'll just zoom out here so you can see there's a bunch of controls up here to change the view. If you do decide to subset your images or curate your images based on some property, you can use the sliders down below. So let's say we only want CTF fit resolution better than 3.5 angstroms. I mean, these are all very good movies anyway, so we don't need to do this, but we can change the slider down to 3.5, and you'll see that some, right now just one image, let me go a little further. Some images now turn gray here, some dots. And so those are the images that we're going to be rejecting, and the blue ones are our selection. You can see the total number of selected images is 15. And for the selection, you can click this checkbox, and that marks the selection as movies that we want to keep. You can repeatedly do this by changing the sliders and accepting or rejecting selections to make any complicated query you want based on these properties. But generally speaking, you only are going to be filtering based on one or two properties. Once you're done, you can click done, and the job will finish outputting different subsets of movies based on your categorization. I'm going to click done, but we don't actually need to, oh, sorry, I forgot to show a bunch of things. So on the individual tab, you can click there and then choose a row in the table and see a bunch of individual plots for each micrograph. First is the micrograph itself. You can also full screen interactive jobs if you want by clicking this button. So first is the micrograph itself. We can see this particular micrograph. Next is the Fourier transform of the micrograph along with the simulated CTF for the micrograph. So the actual micrograph, you can see clearly has this band of extra background power, this white band. That's what corresponds to the ice thickness. The thicker and more power there is in this band in the image, the more ice there was in the sample. Otherwise, you can clearly see the tone rings in the image out to a very high resolution. This is super resolution data, so the pixel size is very fine, and we don't need to go out that far. You can also see the experimental CTF, the tone rings get finer and finer and closer as you get further out. Okay. And then you can see the 1D CTF fit, the same plot that I was showing you before, where we can see the experimental and simulated CTFs and the correlation, motion trajectories, and rigid motion trajectory. Okay, so that's the exposure curation. I'm going to click done. I'm not actually going to use the output of this job. I was just showing that as a demonstration. And now it's a good time for any questions.
Great, we do have a few. Some of these track from a little bit earlier on, so I'll try and give a heads up as to the section that they cover. So first, going back a little bit to when we're actually importing raw movies, what is the effect or consequence of inputting the wrong electron dose?
Great question. So if the electron dose is extremely wrong, like if you enter 1 instead of 10 or 1,000 instead of 100, that will totally throw off the dose weighting, and you'll end up with far more or less information coming from each frame than you should be. If it's off by something more like 10% or 20%, it probably will make no measurable difference at all. At least in our hands, that's been the case. If you want to, you can try to reprocess data with different exposure doses, but I don't think I or anyone else has ever really found that to be worth it. If you'd like, or well, rather, you should kind of know the exposure dose from the data collection session, since that's usually a parameter of the setup of the beam brightness and so on. And it's often also measured with a bright image, like without any sample. And so that's something that you can usually know relatively well from the data collection session. And then beyond that, in our hands, it doesn't matter very much.
Great. Another question relating to importing of movies. When I collected the data, I noticed that each micrograph has its own gain reference file. When processing the data, should we just use one of those gain reference files?
Interesting. I'm not sure what software was used for the data collection. Generally speaking, the gain reference file should have been computed and stored once for the entire session. And it doesn't really change unless you really change something in like the way the camera is set up. So it's usually computed. It's only the gain reference itself is only measured usually once per session. So if there is a single gain reference for every image, that's kind of a tricky situation, since the import job in CryoSpark is designed for the opposite case, where you have just one gain reference on a lot of images. I think this is something you might have to ask on our discussion forum in case somebody has found a way to deal with that.
Great, thank you. Now, a question relating back to sample preparation and how that will actually influence the data processing. So in your experience, how does the use of carbon holy grids versus gold grids affect motion correction? Is it the use of one type of grid computationally limited, i.e. it's always worse?
I definitely can't say that it's always categorically worse. I've heard reports, not firsthand, that gold grids tend to produce less beam-induced motion, not necessarily less stage drift, but beam-induced motion is the harder one to correct. So there have been plenty of extremely high resolution data sets collected on carbon. But if you're doing something like tilted data collection, or you just for some reason happen to have a lot of motion happening in your sample, switching to a gold grid is, at least colloquially in the field, known to help in some cases or in many cases. But I don't know if it's categorically always better.
Great. Can CTF estimation be used at a later stage to go back and inform what's the best motion correction strategy?
Estimation. In a sense, yes, because the tone rings show up better the better the motion is corrected. If the motion is not corrected, then the signal that creates the tone rings in the pattern that they are also gets blurred out. What you would see actually in an image where the motion correction hasn't been done well is that the tone rings in the experimental data are strong in one direction, but they fade out in a different direction. And that means that there's a lot of motion in the perpendicular direction that hasn't been corrected for. Generally speaking, you won't ever see that by eye. Like if you just use patch-based motion, the motion correction will be so close to correct, if not as correct as possible, then you won't actually be able to tell by eye. On a population of images, you could potentially measure the CTF fit as a way to tell if the motion correction was better one way or another, but you're much better off getting all the way to a 3D reconstruction and measuring the final refinement resolution as your metric for how good was one motion correction strategy over another.
Somewhat related, but relating to a later stage of processing, can we do per particle CTF prediction? And by that, I think the user means per particle CTF correction, or estimation and then correction.
Yes. CryoSpark does do per particle CTF correction, and that's possible after you've done a refinement. Actually, it's possible during a refinement as well. I'll talk about that in a few more slides. Like I was saying though, it doesn't always actually do better than patch-based CTF. The reason is, and I'll get to it, the overall reason is that when you're doing reference-based CTF refinement, the reference may not be exactly correct. For example, if you have a membrane protein that has a micelle, if the micelle is disordered, then in every single particle image, the reference that you have doesn't actually match the image perfectly. And so trying to refine the CTF against the reference versus the image when the reference isn't correct often yields worse CTF estimates than patch-based motion. I'll just show an example of where that's the case.
Later on or now?
Not right now. It's in the
Okay.
case.
Sorry. And going back to the idea of having multiple gain references, i.e. one gain reference per movie, one of our users is commenting that EPU, or at least EPU version 1, did in fact output one gain reference per movie. So,
well, if you can verify that they're all the same for a given data collection session, then you only need to use one. That actually saves a lot of disk space as well. So
right.
That'll be the right way.
The next couple of questions relate to the CTF or patch CTF related plots that we were looking at.
Sure.
So if you don't mind going back a couple of slides.
Patch CTF plots. Is that the diagnostic plot or the 3D?
The CTF radial plot. So one question is the CTF radial plot rescaled in some way? In one particular user's experience, the high frequency tone rings are much smaller than the ones actually shown in the plot.
I'm not sure if the user is referring to this figure or the actual CryoSpark. These figures have been cropped. So like this resolution is something like 5 angstroms or something like that, just to highlight the tone rings. In real life, the tone rings look exactly like we saw in this curated exposures job, which I can run again by clearing and queuing to show what they look like again. We don't rescale them in any particular way in the display. They're shown to exactly the same scale and pixel size as they would be, I mean, they actually are. So for example, in this case, the pixel size of our data is 0.6575. So that means the Nyquist rate out here is about 1.2 angstroms, which is for this data set well beyond where we can see tone rings. At half of that resolution, which is about here, that's about 2.4 angstroms, which is still a little bit beyond where we can see tone rings in this image. But the place where we stop seeing tone rings around here where the ice band is around 3 point something angstroms. And if we look at this fit level, we see the fit comes out to 2.7 angstroms because the tone rings actually do extend. I mean, when you average around the ellipse or the circle, you can actually detect the tone rings all the way in this ice band out to 2.7 angstroms beyond where you can see them by eye in the 2D plot. And that's what this 1D plot shows, is that after averaging, we can see the tone rings, these ripples, still present all the way, and they match up with the model all the way up to this 2.7 angstrom resolution. Hopefully that's answering the question that the user has.
I hope so too. Going back to that CTF fit plot for a moment, can you please further explain what the green fit line means?
Sure. The light blue line, I'm guessing, is what they're referring to.
Yeah, it looks like it, yeah.
The light blue line is a measure, a windowed correlation. So it's literally taking windows, like, I don't know exactly how wide they are on this plot, but local little steps in frequency space, sliding across from left to right, and measuring for that little window. Let's say the window is about one of these rings wide. It's measuring the correlation between the experimental and simulated CTF. So where the CTF simulated and experimental are oscillating in the same phase, like they're actually matching each other, this light blue line will be a large number, close to 1. Where they're not together at all, like they're out of phase, it'll be close to 0. And if they're completely opposite, it'll be close to -1, which we don't care about. So what we're really looking for here is the resolution at which this light blue line, which is a local windowed correlation, drops below some significant level like 0.3. That's an arbitrary measure because this resolution estimate is really not meant to be used for much other than an intuitive idea of what your data is like. So when that light blue line falls below 0.3 is when we say, okay, after this point, the experimental and simulated CTFs don't really match up. There are some points later where they seem to match up again, but as soon as there's a dip below 0.3, we know we can't trust anything after that anymore. These spurious correlations are just due to random noise happening to have the same oscillations as the simulated CTF.
Finally, if we have data that was collected using a Volta phase plate, what do we have to take into account when doing CTF correction?
Great question. So when you import your data, if it's from a faceplate, like a Volta faceplate, you can turn on faceplate mode, which lets CryoSpark know that this data is faceplate data. Every job after that should take care of itself in terms of changing its parameters or what it does to account for the fact that it's faceplate data. What in particular, the only thing that actually changes is in CTF estimation. The CTF estimation job will end up, if it knows that the inputs are faceplate data, it will search over phase shift for every image. The phase shift is a single value across the image since we don't expect it to be different from one location to another, but it'll search for that phase shift between min and maximum radian phase shift. So this is between 0 and pi right now. You can change that if you want to search in a smaller or bigger range. Generally speaking, you're looking for a phase shift that's like close to 90 degrees. With real Volta faceplates, it won't be 90 degrees and it'll keep fluctuating over time. But the phase shift will be optimized and searched for by CTF, patch CTF. And this parameter, do phase refine only, I believe it is useful if you're doing CTF estimation a second time and you want to refine the phase shift. Honestly, I can't tell you when you would actually use this parameter, so let's forget about that one. But it will handle faceplate data directly without any other modifications.
And while we're on the subject of modifying parameters in patch CTF, can setting the max resolution in patch CTF to, let's say, 4 angstroms affect CTF estimation? And if a higher resolution is used, i.e. a smaller number value, can the estimation become better?
Great question. Theoretically, yes. If you see that in your data, you actually have really strong tone rings way out to a higher than 4 angstrom resolution, you can get better CTF estimates by allowing the CTF estimation technique to see higher resolution information. In practice though, the CTF, because the CTF is a parametric form and it only has 3 parameters, one for defocus, well, in this case, it has 1 parameter for every patch or a few parameters for the whole micrographic, for the landscape and the astigmatism. There aren't that many parameters. So having a lot more data, like if the tone rings are really clear up to 4 angstroms, that's more than enough data to very well constrain the estimates of those parameters. So having more doesn't actually help that much. So you wouldn't expect things to be like amazingly better by increasing that resolution. But if you do see tone rings very far out, it can help. If you don't see tone rings beyond 4 angstroms, which in most cases you don't really see them beyond 3 or 3.5, 2 angstroms, if you don't see tone rings there, then including that data can hurt because now you're forcing the algorithm to listen to noise where the tone rings aren't really present, and you definitely can't see them, and you can't see that they're there in these 1D plots. So you don't really want to force the algorithm to have to deal with that extra noise if it's not necessary.
Great. And I think just in the interest of time, we can wrap it up with just one more question, and this is relating to manually curate exposures, which you have open. Can you please run through again the combination of factors that you might apply to get rid of bad movies or bad particles in
Definitely.
bad movies?
Sure, I can do that just verbally right now, but in tomorrow's motion correction and data curation sessions, the first block tomorrow, we'll be covering that in a lot more detail and a more interesting data.
That might then be a better time for it, because we also don't have very many. Okay, sure.
I'll just name the things that you probably want to look at. You almost definitely want to look at CTF fit resolution. That's usually the most important, most easy to see metric. You can also look at relative ice thickness, which I'll show tomorrow ends up being very good at detecting when you shift it from a good area of a sample to a bad area or vice versa. And you can look at the total full frame motion or the total full frame motion distance. That tells you how much total motion was there over the span of the movie. And images with a lot of motion, like in this case, 45 pixels, are generally worse because they'll have more in-frame motion that can't be corrected. Even if the motion estimate is perfect, over 45 pixels cut into only 38 frames, in each frame, the sample is moving by at least 1 pixel. And so that means that there's that much blur that we just can't get rid of since it's already baked into each frame. So those are the kind of things you want to look for. Generally speaking, those CTF fit and ice thickness are the more important ones that people use.
Great.
Okay. Back to the slides. So we just finished CTF estimation and we talked about exposure curation and we ran our exposure curation job. So at this point in the practical, everyone has curated their data, although we're going to use all the movies, all 20, but we know how to do that at this point. The next thing we're going to work on and talk about is particle picking. And this is a bit of a larger topic since there are many different ways to do particle picking in single particle EM. And CryoSpark supports all of them. So there are often options to choose from on your data set, unlike pre-processing where we kind of prescribe a certain way to do it. First of all, at a high level, particle picking overall is the problem of trying to find particles in your ice. The reason it's hard is we already know that the noise level in every image has to be very high because we can't have too much contrast, or we can't increase the dose of electrons that would increase the contrast because that would create radiation damage. So generally speaking, the micrographs that we get are very noisy. There's lots of just random shot noise from the detector that we can't reduce. And then there are particles, and then there's also all kinds of other stuff in the ice. There could be carbon edges, there could be broken areas of ice, there could be crystalline ice, there could be gold nanoparticles, there could be other contaminants, there could be broken proteins or some other protein that you didn't intend to be there, or if you've doped your sample with some kind of ligand, there could be clumps of those floating around, or empty micelles if it's a membrane protein, all kinds of junk. And the real task of particle picking is to find particles that are actually the protein that we're looking for. It is not the easiest problem, but there's one sort of silver lining, which is that we don't have to be perfect at the particle picking stage. In practice, what you really want out of particle picking is to just get all the particles and maybe a bunch of junk. The later phases of classification, especially 2D classification, will be very powerful at separating and purifying your particle set, especially if you rinse and repeat a few times. And so you really don't have to be too perfect with particle picking. There is another consideration in particle picking, which is that you don't necessarily want to introduce bias that isn't necessary to pick the particles. Of course, you have to have some bias because you do know that like empty ice is not a useful particle and your protein looks like something, so you do have some bias. But the less bias you can introduce, the better, because particle picking, because it's so free form, has the opportunity to do things like, for example, accidentally pick one view much more than another. If your protein has some shape where a certain viewing direction looks very different from another one, and you set up your particle picking in a certain way, it may pick only side views and no top views, even if the top views are there, creating an induced preferred orientation problem when you don't really have to have it just because your particle picking was incorrect. Or you might end up picking conformations one over another, which again, you don't want since you really want to sample all the conformational space if possible, especially if those conformations look different. So the trick with particle picking is to pick a technique that's the least biased that still provides high quality picks, getting lots of protein. For that, there's a spectrum of methods that are available. On one end of the spectrum are template-free particle picking methods. Those don't really require any prior knowledge about your protein at all, other than maybe the approximate size of the particle. So for example, there's blob-based picking. And blob-based picking in CryoSpark literally does what it sounds like. It's looking for anything in the ice, anything in the image that can be characterized as a blob of density that's a little bit more than the ice background. And of course, there's lots of noise. So it's possible that there may be a patch of noise that randomly happens to look like it have more density than another just because of the noise. But statistically, particles will have actual density that you can find with a blob-based picker. The nice thing about the blob pickers is it's very fast, it's unbiased, it doesn't really require any setup time, and it's the least discriminative. So, well, actually that's a con. It's the least discriminative. It may pick up anything. carbon edges, aggregates, junk, whatever, anything that has density will get picked up, but it's unbiased. So it'll pick up all those things and it'll get all the different views and all the different conformations and everything, hopefully. So in practice, it's actually one of the most commonly used particle pickers. And for a lot of data sets, you don't need anything else. And I'll show some case studies, even of difficult membrane proteins and stuff where the blob picker just works fine. However, it is possible and often useful to move along the spectrum to slightly more discriminative pickers, like for example, template-based particle picking. Template-based picking relies on having a set of 2D or 3D reference templates for what your particle looks like, and then using those to search the image for other parts of the image, patches that look like your particle of interest in terms of their shape. So that's obviously much more discriminative than blob picking, because template picking won't pick up things that don't have the same shape, and it'll generally center itself much better on the actual particle rather than just pieces of density. Template picking, however, can have false positives where a region of the noise in the ice happens to have the same shape, not the same amount of density, but the same shape as one of the templates. And like what's shown in this example here, these 4 picks from a template picker are not great, not what we actually want. And the template picker can also introduce bias if you've left out some views from your template picker that are distinct from each other or conformations. Luckily in CryoSpark, we actually have a method that at least deals with the false positives problem very well by measuring for both a blob picker and template picker 2 different independent types of scores. One of them is what we call the template correlation or normalized cross correlation score. And that measures in a shape sense, how well does a candidate region of the image look like the particle in our template. So if the shape is about the same, the correlation will be high. If it's not, it'll be low. The other score is something that we call the local power score. And the local power score is something that measures how much statistically, how much stuff is there in this region of the micrograph. Is it much more than the noise background or not? And that score tells us an independent measure of whether a certain patch could be considered an actual particle or not, since we know that our protein has at least some amount of density. And so in combination, these 2 characteristics help us pretty easily and cleanly separate good particles and bad ones, or good picks and bad ones for these 2 methods in CryoSpark interactively. And I'll show how to do that on the example that we're using today. The third kind of picking is even further along the spectrum in terms of specificity and discrimination, but it's more cumbersome, or often much more cumbersome to use, and also has its own issues like introducing bias. And that is to train deep neural networks for doing machine learning based particle picking, where we provide a neural network with training data of example picks, typically manually picked, usually in the thousands. Usually in the thousands. And then those particle pick locations are used to train a classifier using standard machine learning methods that reports whether a particular patch of an image is a particle or not, or sometimes formulated in other ways. And the ideal thing is that this deep particle picker would somehow learn exactly what makes a particle look like a particle and discard everything else. In practice, it can work very well and can be very specific. And in some projects, it has proved to be very useful. But in general, it requires manual picking to be done very well. So you have to be able to pick your particles manually to be able to use this kind of a technique, unlike blob picking, for example. You need to pick usually lots of them, thousands across multiple micrographs. And you have to train the classifier, which can sometimes take time. And the final main point is that if your manual particle picking is biased, let's say you're trying to pick out a protein that's not very circular, let's say it's sort of elongated, it may be much easier to see the side views in the images than the top views. And if you don't pick any top views or not enough top views, the neural network will actually learn the exact same bias that you provided it in the training data. And so you want to make sure to avoid that. Again, like I said, in some cases, the deep particle picker can work extremely well. So it's worth trying in cases where the other methods don't produce good results. In CryoSpark, we have options for all of these. I will start by actually moving back to the practical and showing you how on our particular data set, we can use first blob-based picking for totally unsupervised, unbiased picking to get some initial picks, and then use that and along with 2D classification to create templates that we can go back and do template-based particle picking with to get much more accurate picks from our data. So coming back to CryoSpark, I have this curate exposure job here, which I'm just going to kill by selecting the job, looking at the job details panel and choosing the kill button. That'll stop the process behind the scenes and make sure that it's not using up any resources. and then move over to the job builder and choose blob picking. So I'll create a blob picker job type. From there, I will connect the output of my CTF estimation. And this is important because we actually need the CTF estimates to do particle picking. And I'll explain exactly why that is in a minute. Take the exposures of CTF estimation, plop them back into our blob picker. And then I will choose to set a minimum particle diameter for my blob picker of 100 angstroms and a maximum of 200 angstroms. And that's just because I know something about this protein. In general, you would have to have some idea of the size of your protein in order to do this, or you can just try it with some numbers approximately around the range of sizes that you expect, and you may just get very good picks since it's really not too sensitive to these parameters. The blob picker has some choices. For example, if you want to use differently shaped blobs. So by default, the blob that we're searching with is circular, but let's say you know that your protein is a little bit elongated. You may want to use an elliptical blob that has a short side of 100 angstroms and a long side of 200, or a ring-shaped blob that has an inner diameter of 100 and an outer diameter of 200. For example, if you're picking viruses or apoferritin or something else, then ring-shaped blobs can work well. The rest of the parameters I'm not going to change, except I'm going to choose to only process 5 micrographs. And that's really just for convenience right now. You don't have to do this because right now what I'm trying to do is generate initial particle picks. I will only use the first 5. So I can go ahead and queue that job. And all the practical participants should be doing this as well with the same parameters. The instructions are now written here. So we can see that the blob picker has immediately loaded up the micrographs and started picking a bunch of particles. Whether these are actually good or not is something that we can find out with the next job type, which is another interactive job called Inspect Particle Picks. And this is a really helpful tool to look at particle picks of any kind and see how they fall on the micrographs, sort them, and interactively modify thresholds on the parameters or on the criteria that we have so we can pick good particles and remove the bad ones. So I will create an Inspect Particle Picks job. And now from my blob picking job, which is completed, I can take the particles and connect them to my Inspect Particle Picks job. And I will also take the micrographs from which those particles have come and connect them to my Inspect job. And go ahead and queue this job as well. Now this interactive job will load up. It'll do a bunch of preparation and then show me the interactive tab. Once I show you that interactive tab, I'll be able to explain what all the various plots are and how we can use this tool. Okay. So what we're looking at here now is the view of our interactive job, which is an Inspect Particle Picks job. It has a few different sections, and I'm going to make it a little bit bigger so everyone can see the different parts. On the left side, there is a histogram, a 2D colored histogram, the exact same histogram that I was showing in the slides, and that is template correlation versus local power. And this histogram is actually a better example. What we're looking for are particles that have a high template correlation, meaning that their shapes match up well with our templates. In this case, we're looking at blobs, so a high template correlation means a thing that is more blob-like than not, as well as a local power score that is somehow intermediate. Very low local power scores indicate empty patches of ice that happen to look like our template, and very high local power scores indicate carbon edges, aggregates, contaminants, and other things that have too much density to be a particle. So in this plot, I'm going to start and move these sliders, and you'll see the green circles on the right-hand side start to appear and disappear in real time as I do this. So what we're seeing is literally the picks that are left over at a certain level of this threshold. So right now we're selecting particles that have a correlation score better than, let's say, 0.2. I think I wrote in the instructions approximately what you should end up settling on. You can choose any threshold you want, but these are the numbers that I know will work well. In order to visualize this a little better, since the green circles are a little bit hard to see and we can't see the micrograph underneath, I'm going to change the box size here, which is right now 256. And that's actually showing me, the circle is showing me what a 256 pixel square box, its inner circle, would extract. This box size is not actually what we're going to use going forward, but I can just change it to any value for the purpose of display. So I'll set it to 32, And now you see the green circles are much smaller and they're just pointing at the center of the particle picks. I'll also show you that there is a slider at the top here called low pass filter, and changing that slider allows us to apply a low pass filter. I'll also hide the picks for now so you can see. A low pass filter to the image that helps to remove a lot of the excess shot noise that doesn't help us in mentally as a human visualizing and seeing what's in the micrograph. With a good amount of filtering, you can now see lots of clear individual particles. There are these circle views that are top views. There are these 4 stacked ring side views that are the side view of the T20S barrel. And so you can see plenty of particles. You can also scroll on the bottom left here through various micrographs in the set. We only have 5, so I'm just gonna pick another one. You can order them by defocus or CTF fit or the number of particle picks. And actually, this is actually probably a good demonstration just for completeness. The first micrograph here has a defocus of 1.2 micron. The units of this are in angstroms. If I turn off the low pass filter, we can actually see the difference between a high defocus and a low defocus micrograph. So this one I'm looking at right now has a defocus of 2.1 micron. So that's pretty high. You can see very clearly without the low pass filter, there are lots of intact particles and everything is kind of clean. You can see the particles, you can identify them visually by eye. Every particle has this sort of white halo, and that's actually what the CTF does, is it delocalizes information from the particle image. And so instead of seeing just a shadow of the particle, we're seeing both bright and dark spots created by the refraction pattern of the electrons through the sample. So this is a high defocus micrograph. Now I'm going to switch over to this 1.2 micron lower defocus micrograph, and we'll see how different it looks. You can see now that it's definitely much more noisy looking, and the contrast of the particles is worse. That's exactly what happens at a lower defocus. As we approach focus, the particles start to disappear into the noise. In fact, this low defocus micrograph has somewhat better high resolution content, but it makes it harder for us to see and find the particles. Anyway, coming back to our particle picking problem, I'm just going to choose this other micrograph, 2.1 micron, and bring in the low pass filter again so we can see all the particles really cleanly. And you can now really tell where they are very easily. I'll show the particle picks again. You can see that the green circles there are a bunch of particles that are, for example, in empty patches of ice that we want to get rid of. And there are a bunch that are actually on the particles. A lot of particles are sometimes picked off center because the blob picker isn't perfect, but that's what we're going to fix with our next iteration of particle picking. So in this case, I'm going to choose particles only that have a power score at least 600. So now you can see we've gotten rid of all the particle picks that were in the empty patches of ice, and also below 1000. And that, as I'm dragging this, you should see that I'm removing those particle picks that are on, for example, double and triple particles that are aggregated like these, where there's particles on top of each other. That's not really good for our algorithms. There are also, you can't see them very clearly right now, but lots of gold nanoparticles distributed in this sample. And those also have a lot of contrast that we want to avoid. So these settings allow us to pick out particles that are pretty reasonable for a blob picker. The particle picks aren't exactly centered, like I mentioned, but we're going to fix that. So now we can click Done Picking Output Locations. And this button is only going to output the locations of the particle picks that we've selected here. It doesn't actually cut out the particles from the images or extract them or do anything else. So now this job is finished, and it's outputted our 5 micrographs along with 3,500 particles picked from those micrographs. The next thing we're going to do is actually extract that small number of particles from the micrographs. So what we want to do is create a new job. This is now an extract from micrographs job. It's part of the particle picking section, but it's called extract from micrographs. And I'll just give a minute for the practical participants to catch up and drink some water. Extract from micrographs literally does the simplest thing, which is to take each micrograph, load it, cut out small squares of a certain size that we call the box size around each particle coordinate, and store those cut out square particles in a stack, essentially. So we're going to start the extract from micrographs job, take the output of our inspection job, micrographs and particles, and then choose the box size. And this is again written in the instructions on the left-hand side, step number 3. We're going to choose the extraction box size to be 440 pixels. Again, I happen to know that because I'm very familiar with this data set, but you would have to choose a box size based on the size of the particle and the pixel size and so on. The rule of thumb, and this is something we always get a lot of questions around, the rule of thumb is that the box size should be approximately twice the longest diameter of the particle. That's not a hard and fast rule. It can be smaller, it can be larger. The reason it should be that big is because if you remember what the CTF does, it takes information from the shadow of the particle or the refraction pattern that we want to capture and spreads it around nearby to the particle. If we cut the box too small around every particle, we will end up cutting off lots of useful signal from the outsides of the box that we want to keep. So we're going to keep an extraction box size of 440, a Fourier crop box size, and I'll explain what this is, of 256. What Fourier cropping means, it's the same as binning, another word for binning. I mean, they're not actually the same mathematical operation, but they both correspond to downsampling an image. Fourier cropping is lossless in the sense that it doesn't create any extra artifacts, whereas binning sometimes does. So Fourier cropping means that we're going to downsample the images from their original 440 size down to 256. The reason being is that the pixel size of this data set is so small at 0.6 angstroms that we're just wasting time and compute resources processing images of such high resolution when we're not expecting to get a 1.5 angstrom result here. Again, this is a choice I can make because I know the data and I know that I'm aiming for a 2.x angstrom reconstruction. So with this with this downsampling factor, I'm going to be shrinking the images and storing them at a lower resolution after extraction to save disk space and compute time and everything. The reason this is important for compute time and disk space and memory usage is that later down in the pipeline, all the processing that we do with particles takes either the box size squared or the box size cubed worth of memory. So if you double the box size, that means either 4 times or 8 times more memory necessary to deal with the same images, and vastly more time as well. So smaller box size is always useful where possible. So again, I'm finally going to run this job. And what will come out of this job in a moment is a set of micrographs and a set of extracted particles. You'll notice here that the number of particles is slightly less than the number we had previously identified. And that's because some particles are too close to the edge of the micrograph. And so the extraction can't extract them. It only extracts particles that are far enough away from the edge that we can get a whole box. So right now we have 3,000 particles. I'm next going to start a 2D classification job. And I won't explain anything about this because we're coming to that in the next section. But I'm going to start a 2D classification job, taking the outputs from my extract from micrographs job, just the particles this time. So I'm dragging just the particles output and connecting it to my 2D classification job. This is step 4, by the way, connecting the particles. And for the 2D classification, I'm going to change one parameter, which is the number of 2D classes, and I'll set that to 20, since I really don't have that much data, so I don't need to waste time looking for more classes. With larger data sets, you may want 50, 100, 200 classes, and depending on what you're trying to do, and I'll explain all of that in the next section. But for now, we'll just continue with 20 classes. So this 2D classification job is now going to run. And on your instances, you should also see that run. If you see any errors about SSD caching, it may mean that when you set up your project, you didn't flip that switch. And if anyone has that problem, I'll just tell you what to do right now. In your 2D classification job, this one, there's a parameter that you see at the very end that's called cache particle images on SSD. You have to manually turn that off and then run the job again. Okay, so my 2D classification job now has already started. In a few seconds, it started to resolve very coarse 2D classes, and it's continuing to optimize those. I'll explain how that works in a few minutes, but the purpose that we're doing this is step 4 here, to create some 2-dimensional templates that look like our particles that we can then use for template-based particle picking. And template-based particle picking, as I explained, is more discriminative, more accurate. In this case, since our protein really only has 2 distinct views, the top view and the side view, since it's so highly symmetric, we don't have to worry about bias of missing views or confirmations or anything like that. So we're just going to go ahead and use the template picker with just 2 templates. In practice, you can use many more templates, 20, 30, 40, whatever you want. You can also generate templates from a 3D structure. So for example, if you already have an initial model of your protein, or you've gotten to a later stage of processing where you've created a 3D reconstruction and you want to go back and make your particle picking better, you can take that 3D reconstruction and feed it to a create templates job that will take the 3D structure and project it along different viewing directions and generate a whole bunch of 2D templates that can be used for template picking. So that's another option. In general, if you're going to use the template picker, that's a good idea. You do have to be very careful about one thing, which is that you shouldn't bring in outside information into your processing flow at this point. For example, if you're working with some difficult protein and you can't really see it well in the images and you think, well, I know there's a PDB structure of a similar protein, why don't I load that as a 3D structure, generate templates, and use that for particle picking? That is a very bad idea because the template picker is highly biased by the templates that come in. And if the templates are generated from outside information, it's perfectly possible for the template picker to pick up a bunch of things in the sample, in the ice, that are not actually your protein or may not be anything at all, just because they happen to correlate somewhat well with the templates that you provided. We're safe as long as those templates were generated from the data itself, like what we're doing here. We're not introducing any outside information. Or if you had a 3D structure resulting from the same data. Otherwise, it's not safe to use templates from external sources. There are some caveats to that. For example, if you're working on multiple samples of the same protein, maybe with different ligands bound, you can use templates from one across to the others. As long as you can actually see the particles in the ice, it's safe. But you just have to be careful about this notion of bias. The same thing is true for deep particle pickers trained on one data set and then applied to a different one. You can't necessarily trust that result. Okay, so I see that there's a question about the SSD fix. For somebody who's having that problem, I'll just explain that again. If your job failed due to the SSD problem, you can clear the job, click on clear, choose yes, and then you'll now have an empty job that has not been processed. Click on where it says building to enter the job builder again for that job, and then scroll all the way down to the bottom, and you'll see a parameter called cache particle images on SSD. You have to turn that off manually. Right now it's off for me by default since I had changed the setting correctly, but you may see that it's on and you should turn it off. Okay. So now I'm going to assume that the 2D classification job is either running for most people or already completed. We can move on to the next stage of particle picking, which is to select the templates out of these that we want to use for template-based picking and then proceed to picking. I'm just going to open up this 2D classification job so we can look at the templates in a little more detail. There's clearly some templates that are of particles that are picked off center. So like this proteasome is clipped off at one side. There's a good template of a top view. We can start to see the 7-fold symmetry of the proteasome. There's a great centered side view. There's another one. This is one of those gold nanoparticles that is contaminating this data set. And then there are a bunch of other various strange kinds of side views or slightly partially oblique views and so on. We don't really care about any of those. We just want to use the top view and the side view. So what we're going to do is go to our job builder and create a select 2D classes job. By the way, I see someone who asked, how do I exit full screen for the jobs? You can click this little arrow button in the top right corner of any job card. So creating a select 2D classes job, we now have 2 inputs, one for particles, which we're taking from our 2D classification job that we just ran, and one for templates, which are coming from the class averages of our 2D classification job. So once both of those are connected, we can queue our select 2D job. And the select 2D job is a very simple interactive job. It just shows us all of our templates, allows us to interactively click on the ones we want to keep. So coming over to the interactive tab here, I can see that this job is now ready for me to use. I want to choose this one top view and one side view, and that's it. So once I've selected those two, I can click the green done button, And the output of this job is going to contain just those 2 templates and the particles associated with them, which we're not going to use. We're just going to use the 2 templates for template picking. So I'm going to click done. And then move over to the template picker. This is now step number 6, creating a template picking job. So that's the job called template picker.
Sorry to interrupt, Ali. Maybe it's a good time for a quick recap, since particle picking is one of the longer sections,
for sure.
to just tell us in our roadmap where we are in our picking strategy and what's coming next, what we've done so far.
So far, what we've done is to use first the blob picker directly applied to the output of our CTF estimation job to automatically pick using just 2 inputs, one being the minimum particle diameter of 100 angstroms and the other one being 200 angstrom maximum particle diameter. Pick particles automatically on 5 micrographs. We then inspected those particles to select the ones that we thought were good by applying some thresholds. That was step number 2. Then we extracted those particles from the micrographs with a certain box size and a certain Fourier cropping size, 440 and 256. Then we took those particles that were extracted from blob picking, so they're not perfectly picked, but they're reasonable, and we ran a very fast 20 class 2D classification on those particles. That yielded a bunch of templates that are averaged particles that now have more clear details in them. And we're going to use some of those for template-based picking as a second round of picking. In order to choose the templates we want to use, we ran a select 2D job to select 2 templates, just one top view and one side view. That's as far as we've got now. And the next thing we're doing is to go to the job builder and create a template picking job, template picker job.
I had a question then on the in the select 2D. You selected the 2 views that you wanted, but you also had to select the particles again because these 2D pictures didn't contain which particles. Is that why? Is that you had, because it seems like you should just have to select those 2 views, the 2D views you wanted, but you actually had to also include the set of particles.
We didn't actually have to do that manually. What happens in 2D classification is that 2D classification generates these averages, and each average is a cluster of particles. So for example, this top view contains 443 particles. We don't actually care about those particles or which ones they are, since what we're really looking for is just the shape of the template. But the select 2D job that we just ran, by default, when you give it particles and templates and choose the templates, you only choose the templates, but it will itself, behind the scenes, separate the particles into the particles that you chose and the particles that you excluded. So there are a bunch of outputs here, one for the selected particles that came from these 2 classes, one for the excluded particles that came from all those classes. We are actually only interested in this one output, which is template selected. But in a different scenario, when we're using select 2D, let's say to purify a data set, we may actually be interested in the particles that came from the classes that we liked. Does that answer the question?
Yeah. Okay, it's a different. Okay, fine. You're getting them from different places. Yeah. Okay.
Great. So now the place we're at is to create our template picking job. So by creating a template picker job, it has, again, 2 inputs, one for templates and one for micrographs. So this is going to be a little bit different than the previous jobs that we built in that it's going to take inputs from 2 places. We're going to open the select 2D job first and take the template selected from our select 2D job as our templates in template picking. Next, we're going to close this job and go back to our CTF estimation job. Open that up and take the exposures, the set of 20 exposures from there, as our micrographs to process. The reason we're doing that is because so far in the blob picker, we had chosen to process only 5 images. And so the outputs of our jobs up to that point contain only 5 images. But we actually want to now look at the entire set of 20 images, or in a different case, maybe 20,000 images, and process them all with the template picker. And so we've now connected the full set of micrographs after CTF estimation, along with our just 2 templates that we wanted, to our template picker. We can see this a little more clearly in the tree view, where now we see that by zooming in, holding Alt or Option and scrolling, I can see that we had an import movies job followed by patch motion, patch CTF. Patch CTF was used for blob picking, which was then used for inspect picks, extract from micrographs, 2D classification, select 2D, and finally that, as well as the original patch CTF, was used for template picking. Hopefully that's clear. I'm going to now queue up this template picking job. Oh, sorry. It needs one parameter, which is the particle diameter. Here I'm going to estimate 200 angstroms. In the template picker, the particle diameter can be any number that's larger than the largest particle diameter. So for the proteasome, its real actual length is about 190 or 180 angstroms. And so 200 is a good number to choose. So I'm going to go ahead and queue that job. And that job is now going to actually do some template-based particle picking for us, which will hopefully be more accurate. Looking at the log of this job from the beginning, we can see that 2 templates are being used, one top view and one side view. Templates in template picking are always filtered to a low-ish resolution. By default, that is 20 angstroms. So we're never using information beyond 20 angstroms to pick particles, since we can't trust that high-resolution detail yet. And these templates are now used to pick particles on our micrograph, and we can already see that they're much more centered on the particles. And we'll see this again in inspect particle picks. So the template picker is very fast, just takes about 1 second or less per image. So we can switch over now to create another inspect particle picks job. And I'm going to switch back to the cards view to keep things clean. I'll go to the job builder and create an inspect particle picks job. This time taking all the particles and all the micrographs from template picking. And now I'm going to queue that inspect picks job. And I'll just take a sec to allow the practical participants to catch up at this point. This is more or less the set of steps you should see on in your project. Okay, so now coming to the inspect picks job, which we have running, opening that shows us the interactive view. And this time we see a lot more particles in this histogram, and we see our micrographs as before, but our particle picks are now much more well-centered. And I can show you that by, again, choosing a different micrograph, sorry, and changing the box size for display to 32, just so that the circles show up as smaller circles, pointing at the center of the picks. And you can see in most cases, wherever there's a particle, there is a pick right at the center, because our templates provide that much more specificity and discrimination in picking particles. There are, however, still some particle picks in places that aren't actually particles, ice, empty patches of ice, or aggregates or other places, but overall the particle picking is substantially better. What we're going to do next to refine this set of particles to the final set that we want to use for our further processing is to set the cross-correlation threshold. Again, looking at this histogram to a value that separates those picks that have a very low score, like 0.25, from the sort of cloud of picks that have a better score, something like above 0.35 or 0.4. And I think I wrote here that we should use something like 0.34. It doesn't have to be exactly that, but we can start to see as I slide the slider, we're losing a lot of the bad particle picks that are not really what we want. And at 3.34, we're pretty much left with only good particles in terms of their shape. We still have some particle picks that are on aggregates or other contaminants. To get rid of those, we're going to use our power threshold to pick images that, or sorry, particles that have a power score at least 1100 and at most 1700. And as you're moving those sliders, you should be watching on the right-hand side, and you'll see the particle picks start to disappear from areas that have multiple particles overlapping, aggregates, and other things that we want to avoid. One thing I'll explain at this point, as practical students are catching up, is that these scores, the correlation score and the power score, computed in their most naive way, are actually highly dependent on the defocus of a given micrograph, since each micrograph, depending on its defocus level, has a different level of contrast. And so the literal correlation in a numeric sense between the template image and the micrograph at a particular location depends on how much contrast there is in the micrograph, and that depends on the defocus. And so if we don't account for that, then a perfectly valid particle in one image at a low defocus will get a much lower correlation score than the same particle, equally good, in a high defocus micrograph. And so if we don't account for this, we'll end up selecting mostly particles from high defocus micrographs since they seem to have a better correlation score. And that was actually a problem for a long time. In a recent version of CryoSpark, we fixed this by introducing an automatic calibration for the defocus. There's a little article about it, or a tutorial, particle picking calibration. This is not something you have to actively think about because it's done automatically under the hood, but this tutorial explains what happens, how we account for this bias in terms of the median correlation score versus defocus. We can see on this large data set, there's a very strong trend that higher defocus means automatically a higher score, even if the particles are of the same quality. So we actually correct that out now. And at this point, the inspect particle picks job will, generally speaking, give particles from a wide range of defocus values using a single threshold for all of the micrographs. Same thing with a power score. It also has a strong correlation between defocus and the power score. Okay, so at this point, the inspect particle picks, hopefully everyone has been able to enter these two thresholds. You can click through a few images if you want to see what particle picks look like on a different image than the one where you tune the parameters. But otherwise, we can go ahead and click done picking output locations. Now we'll finish up this inspect particle picks job, and we'll see that in its output, we now have something like 10,000 or 11,000 particles, somewhere in between there. Each person's result here will be a little bit different just because your 2D classes were different since they're randomly initialized. And so your template picking was a little bit different and so on. Finally, we are almost done our particle picking. Inspection of those particle picks is done. So now we have a good set of some 10, 11,000 particles that we like. And we can finally create a new extraction job, extract from micrographs, that we take the micrographs and particles from our inspect job, the most recent one, enter the correct box size, be sure not to forget this, and the Fourier crop size of 256, and finally queue that job, and that will at last get us a set of good particles that have been cleanly picked, inspected, and verified to be well-centered particles ready for 2D and 3D reconstruction. So my extraction is now finished, and I have 9,700 particles left after extraction because of the edges, and ready to proceed. I'll leave this time for practical students to catch up with this, but I'll just go back to the slides. The next topic we're going to talk about is 2D classification. So maybe I'll just pause right there and wait for any questions at this point.
Sure, we do have some. Also, just in terms of timing, I think we were meant to take a break around now as well. So perhaps we should finish up the questions, take our break, but does it make sense to queue up the 2D classification so that's going to run in the background before you start talking about it?
How about we take a few questions right now, start the 2D classification, and then take a quick 10-minute break and come back. I think after this break, we were supposed to go to the meeting mode for participants, but we still have a lot of content to cover here. I think we're delayed overall through the day. So after the break, we can just come back and continue through 3D reconstruction, refinement, and so on. There's less practical elements in those parts and more slide-based discussion, so those will hopefully move faster.
Great. So some of the questions that we have, can you please recap the sort of rules of thumb or strategies for determining the two kind of difficult numbers. So the first is when you're doing picking, how will you know what the particle diameter is if you don't know very much about the data set? And the other one is how do you determine the extraction box size? You had mentioned a rule of thumb for that.
Both very good questions. In terms of the particle diameter, usually in most projects that I know of, that particle diameter is somewhat known because there may be either homology studies of similar proteins or negative stain data that has been analyzed before, or some other previous source of information about maybe the overall low resolution arrangement of the protein. If not, it has to be measured or imaged, or rather looked at directly on micrographs. CryoSpark, unfortunately, right now doesn't have a simple way to like drag on a micrograph and measure a distance. But if you're familiar with any other software for looking at images of most kinds, a common one is called ImageJ that can load MRC files, for example, the micrographs of our motion correction. On your own laptop or whatever computer you're using, you can use that to directly drag a little ruler and measure the size of particles in the image and convert that to angstroms, and that will give you an idea of the particle size. So that's usually what people do. In terms of actually choosing the number you should use for the blob picker, it really doesn't matter too much. You don't want it to be so far off that you're going to end up picking everything other than your particle. But so for example, for this proteasome, it's a sort of barrel-shaped protein. The top view diameter is maybe 120 angstroms, and the side view length is maybe 190 or 200 angstroms. So we use a blob particle diameter between 100 and 200 angstroms. And that was perfectly fine to get our particle. Blob picking is just not that sensitive. The 2D template picking, rather, is also not sensitive. As I mentioned, you just need to pick a number that is at least larger than your particle diameter, because the way the template picker works is that when it prepares the templates for using them, it adds a little bit of padding around the number that you chose, and that's where it cuts off the template. So if you chose a number that's too small, it'll end up cutting off the corners of your template, and then what you're actually matching in the images will be different than what you intended. So 2D classification and looking at these plots is another way to just validate that your particle diameter is approximately right. As long as your particle's a little bit away from the edges of this circle where the template generation has cut off that shape, then you're good. Another way to measure the particle diameter is if you have gotten to 2D classes already and maybe you're seeing that your box size is a little bit too big or smaller, you want to readjust it, you can actually look at the 2D templates. Each one is a little square image. You can also do this in the inspect particle pics or any other view of the 2D templates, and you can measure or eyeball the fraction of the box size that your particle takes up. And then from there, you know the box size that you used, and you know the pixel size. So for example, in the early parts of the log of 2D classification, we get a little line that tells us the box size being used for doing 2D classification and the pixel size at that box size. So we know that the extent of the image in angstroms is 128 times 2.2 angstroms. That tells us how big is one square in angstroms. And if we see that our particle is about half of that, then we know our particle diameter is about 100 or 200 angstroms, whatever it happens to be. So those are other little tricks to get that. In terms of choosing the box size itself, again, this is a question that we always get asked, and the answer, unfortunately, is that it both matters and doesn't matter too much. It matters in the sense that if you're going for a very high resolution reconstruction, you have to make sure that the box is substantially larger than the particle, either 2 times or 2.5 times the diameter of the particle. So for extremely high resolution, for example, apoferritin data sets, it's common to use a box size that is much bigger than the protein. What that means computationally is that you're keeping all of the signal from the CTF that has spread information about the molecule around nearby to the molecule in the image. You're keeping all of that. On the other hand, in your 3D reconstruction, your 3D volume also has a tiny little particle and a lot of empty white space. And so computationally, there's just so much waste. Everything takes longer, way more memory, it's slow. So in practice, if you're like, when you're first processing data, pick a box size that's maybe 1.5, 1 3/4, up to 2 times bigger than the diameter of the particle. Once you process a little bit of data, you'll start to get comfortable with what box sizes typically look like. This is a perfectly fair box size around this T20S proteasome. If you look at these squares, the long side of the proteasome is a little more than half the length of the box. So we're not quite at a factor of 2, but this is perfectly fine. If we were looking for a 1.x angstrom structure, then we would want it to be a little bit bigger. But that effect also depends strongly on the defocus range. If your images are defocused very little, so the defocus values are small, then the extent of spreading of the CTF information is not very far. So you don't need a big box. If your defocus is very high, like 4 micron, then your CTF is spreading information very far and you need a huge box. But then if you're at that high of a defocus, you're probably not going for a very high resolution anyway. So again, it's a trade-off. The overall rule of thumb is that pick something that's not insanely large, but as close to 2 times the particle diameter as you can. If you end up getting a really good result, it's worth trying again with an even bigger box size, basically.
Great, thanks. In this example where we're looking at T20S, we have a micrograph that's well populated, but I wouldn't say that it's crowded. Would we have to adjust our picking strategy in any way if we had a very crowded micrograph where there are lots of particles?
Excellent, excellent question. So in the template picker, there's a parameter that's called minimum separation distance, and it's in units of diameter. This is a parameter that controls the picking strategy in the sense of how close are particles allowed to be before they're counted. Sorry, how close are particle candidates allowed to be before they're considered to be the same particle and one of them is thrown away. So in this example, for instance, we're saying that our diameter of 200 is how big we're saying a particle is, but a nearby particle can be up to half that diameter, so 100 angstroms away from center to center, and still be considered to be a different particle. And that's because in our images, we actually do have crowding in the sense that if I zoom into this image, you'll see there are often proteasomes that stack up one another side to side. And their 200 angstroms is longer than the long length. So if we said that the center of the next one has to be more than 200 angstroms away, we would throw away a bunch of good particles. So that separation distance controls how much crowding we're essentially tolerating. If you know that your image is not crowded at all and you just have sporadically well-distributed particles, it's better to increase that number so that you never have the chance of accidentally picking 2 things that are too close together. You know that those both can't be particles. So that's kind of what you would do in a crowding situation. Other than that, you don't have to really do anything special. There is something special you have to do in 2D classification, but I'll cover that in the advanced tutorial tomorrow.
And finally, does the resolution of the 2D classification reflect the resolution of the final structure? So I believe that's where we've got our class averages and they've got some statistics associated with them.
That's right. The class averages each have a resolution estimate and some other numbers that I'll explain later. No, the 2D class resolution estimates are not a reliable measure of the final result you can expect to achieve. In both directions. It's very possible that 2D classification hasn't separated out different views very well. So there may be a bunch of different side views that are off by maybe 5 or 10 degrees from each other in terms of 3D pose in the same class. And averaging all those images together will obviously lead to a poorly resolved, blurred out result. What you're really looking for in a 2D class is whether the particle is intact, whether it looks like what you think the particle should look like, which I know is a very vague notion, and whether you see things that look like secondary structural details. So for example, even in this class that's made of very few particles, only 160 particles, we can already start to see some little lines and other small features in there, which it will turn out, and at this point you may not be able to verify directly, but it will turn out that those are actually alpha helices. Other classes like this one really don't have that kind of structure that we can consider. And so that's really what you're looking for in a 2D class, but by no means does this resolution indicate what resolution you're going to get at the end of the day. It could be that you're missing a whole bunch of views. If you only had side views of this proteasome, you're never going to get a 3D reconstruction, let alone a high resolution one. So it can go either way. But 2D classification is definitely the most powerful, straightforward way to tell the quality of the data without doing a 3D reconstruction and finding out the hard way, more or less. Right. Shall I go back to the slides then, unless there's another?
I think in the interest of time, we should probably kick off the 2D classification and give everyone a break as well.
Okay, so we talked about particle curation in terms of picking. The next stage of processing in Cryo-EM, single particle EM, analysis is 2D classification. The point of 2D classification is to be able to inspect and curate, generally speaking, massive data sets of particles where you can't look at every image on its own. And you want to be able to separate junk particles from good particles, improve the homogeneity of the particle stack, and get an investigative view, not necessarily to separate things, but to be able to just intuitively see different conformations that may be present, different viewing directions that you may have, or missing viewing directions that you may be looking for, and really just get a much better, cleaner sense of what the data looks like other than what you can tell from micrographs. Since, as we know, each micrograph is very noisy, and it's only through the power of aggregating signal that we can actually recover anything. So 2D classification is a very important tool. It's generally widely used in a project. Like, you will do many rounds of 2D classification, often multiple 2D classifications in parallel. Usually you're inputting all the particles that you got. So on 2,000 or 5,000 movies, you may have 1 million or 2 million particles. All of those are going into 2D classification. So it's important that 2D classification is very fast. And that's one of the reasons why CryoSpark is very popular. Its 2D classification is very fast, even for very large data sets and large numbers of classes. It uses something called an online expectation maximization algorithm, which I won't get into the details of right now, but might come up a little bit later. It also uses something called branch and bound alignment, which is another algorithm that we developed. And again, I'll describe that a little later in the context of 3D refinements. Finally, it's important to know that CryoSpark's 2D classification is doing what's known as probabilistic classification or soft classification. At every iteration of a 2D classification job, as it's optimizing the 2D classes and the assignment of particles, it's never actually discretely choosing that a single particle image belongs to a particular class. It's always making that choice in a probabilistic sense. So the classification of every image is actually a probability distribution over all the classes. Every particle gets a score of how much probability does it have of belonging to this class. And those probabilities evolve over time until we can become very certain of the classification of each particle into a given class. So that's a helpful thing to note, and one of the diagnostics that we look at when we're looking at 2D classification running. How confident did we become in the classification? The implementation of 2D classification in CryoSpark is GPU accelerated. It can also be used on multiple GPUs at the same time for scaling. And recently, in newer versions of CryoSpark, we've made some other improvements under the hood in how the GPU code works, and it's gotten a lot faster, even more faster rather. Let's just switch over to CryoSpark and we can start creating our 2D classification. It's very simple to do. We'll go over to the job builder, look for 2D classification, create that job. We're now at step 1 here in 2D classification. We're going to take the micrographs from our extraction job, the particles from our extraction job. There's 9,700 of them here. So this is obviously a very small set of particles, and we don't expect 2D classification to take long here, maybe a couple of minutes. And we're going to leave the parameters as default right now. I'm not going to explain any of these in the interest of time today, but tomorrow I'll be explaining a lot more of them. And we're going to go with a number of classes of 50, which is the default. So we can go ahead and queue this job. And that's going to start it running. And that's actually all we need to do right now. I actually have a note here to create another 2D classification with 100 classes at the same time, just so we can see the difference. And in order to do that, I'm going to take this job that I've already made, number 28, that's running, select it. In the details panel, I see a button called clone job. So I'm going to click that button. What that does is create a copy of this job that has the same inputs already connected and the same parameters set, but it hasn't been run. That's an easy way, if we're experimenting with multiple parameters, to create copies of jobs and change one parameter in each one and then run all of them at the same time and see what happens. So here I'm going to use 100 classes in my 2D classification and queue that job up as well. So now these two 2D classifications are going to run in parallel. You can see that one of them has already started making beautiful looking 2D classes in a few seconds, and that's because this data set is very clean and we've done a great job with our particle picking already. So we don't have too much junk and the particles are large, easy to align, everything's good. Tomorrow we'll see examples where that's not always the case, but for today that's what we're looking for. Okay, so that's starting the 2D classes. I'm just going to switch back to the slides because there's a few more things to mention about 2D classification while the practical participants are setting that up. In terms of speed, as I mentioned, CryoSpark's 2D classification is very fast, much faster maybe even an order of magnitude faster than other methods, even on the same GPUs, due to the algorithmic choices that we've made. Generally resolving 2D classes in a variety of conformations and states and orientations, and being able to resolve high resolution details, even up to the point of seeing secondary structure, sometimes even helical pitch, if you're lucky to have very clean data in the 2D classes. So for example, 100,000 or 125,000 particles can be classified into 50 classes in just 8 minutes on a single GPU. 1,000,000 particles into 50 classes in an hour on a single GPU, and 1,000,000 particles into 200 classes in 2 hours on a single GPU. In the latest versions of CryoSpark with the latest hardware, for example, if you're using an NVIDIA V100 GPU, 1,000,000 particles can be classified into 200 classes in just 1.2 hours. So that's very fast for anyone who's done 2D classification and any other tools. Makes it possible, the reason this is really important is that it makes it possible to run multiple 2D classifications in parallel, or to do multiple rounds of 2D classifications sequentially, where you do one 2D classification, select a subset of particles, maybe only the good looking classes, or maybe everything except for the very poor looking classes, and some medium classes are accepted, and then do 2D classification again, find another subset and separate that into more conformations and views. And that repeated rinsing is a great way to remove junk, remove aggregate proteins that aren't, or picks on aggregate proteins that aren't actually the particle of interest, broken particles, carbon edges, etc. And this is generally the recommended way to deal with particle picking on interesting or challenging data sets. Don't spend too much time trying to optimize your particle picks. Instead, get lots of data, lots of picks, and put them all into 2D classification and spend more time doing classification, both because it's much more effective at separating good and bad particles than particle picking can be, and secondly, because it gives the practitioner, the user, a really clear idea of what's in their data. You get to see all the different viewing directions. So for example, this ion channel, trip V1 ion channel, we can see different top views, even some slightly tilted oblique top views. In this case, unfortunately, I can't zoom in here, but you can even see the alpha helices that form the central pore of the ion channel. You can see side views where secondary structure is visible. Side views with what looks like different size micelles, like this one or this one. I mean, at this stage, we can't be sure if these are different views of an oblong micelle or different size micelles, but because we know the protein is C4 symmetric and pretty much round, we're pretty sure that these are different size micelles. And so on. All that kind of heterogeneity can be detected at this stage. We can even find very oblique views. We can find, in some cases, if you look hard enough, versions where one of the subunits has disappeared and stuff like that. We don't need to actually manually separate those at this stage. If there are conformational changes, we're going to look for those in 3D rather than 2D. But at this stage, we can really tell what's in the data to a great extent. Okay, that's all I want to say about 2D classification for now. We can spend a few minutes on questions and then take a break.
Great. Okay. This, I think we're going to cover in a little bit more detail as we go forward with the rest of the tutorial and also tomorrow. But at a high level, at what point in data processing would a user think, I need to make particle picking better, and so therefore I would like to generate a template from a 3D volume, let's say one from Ab-initio Reconstruction?
That's a great question. So I would say the most telling point is when you're doing 2D classification. If you find that the vast majority of the 2D classes that you're getting, like let me show you what we're looking at right now. In this perfectly clean data set with great particle picks, in our experiment, we're seeing that in terms of weighting of particles going into classes, almost all the particles are going to very well resolved classes with secondary structure detail, lots of, you can see the symmetry very clearly, everything's great. And there's barely any particles in the junk classes where we don't see the particle of interest, the protein of interest. There we can say that our particle picking is great. The other telling thing is that all of our templates are really well centered. We don't have any half cut off proteasomes or other strange arrangements of multiple proteasomes in the same image. And so we can tell that our particle picks are centered and there's not much other than protein that's being picked here. On the other hand, if you do particle picking and you get like, you do 2D classification and you get like 1 or 2 classes that are what you think your protein looks like and the rest is unintelligible, unrecognizable, it probably means that your particle picking is picking up so much extra stuff, so much junk, that it really should be something that you spend time to make better. And that could be done by using the templates that you have gotten that are good and using that for template picking, but there you have to watch out for orientation distribution bias if you accidentally only have side views, let's say in your 2D classification. Or if your data is kind of mediocre, getting to a 3D reconstruction ab initio stage, maybe just a coarse resolution reconstruction, projecting that back into 2D and getting a diverse viewing population and using that for template picking can be very effective at that stage. So those are the kind of things that you want to look out for. In 2D classification, actually I can just show you in comparison the 2D classification that we did with our blob picker that was of poorer quality. You can see that there's miscentered particles, that's very clear. There are also kind of junk looking classes that maybe have a particle, maybe are just not really a particle, but two particles together. Those are telling signs that your particle picking is suboptimal. I mean, this is still not bad, but this is a great example of what you don't want to see, where you have density, where you have significant density at the edges of the template, either because that template is miscentered or because this is actually a combination of picks that are a little bit too far one way and a little bit too far the other way on a long molecule, for example. That's what you don't want to see.
Speaking of the centeredness of the particles, if the 2D classes are not well centered, will this impact the final resolution and how can I fix it?
It depends on the degree of miscentering. If it's to the point where the particle is being cut off at one side, then definitely yes. It also has to do with the box size argument that we said before, that if in all the images your particles are a little bit off center from the center of the box, then by definition you're cutting off information too close to the particle where there actually was signal due to the CTF. So centering in that sense can also have an impact on high resolution. On the other hand, if the miscentering is just a little bit, like 10%, 20% this way or that way, it doesn't matter, because in 3D refinement, we're also going to be searching over the position of the particle in every image. And so that will get optimized out. So only if it's really severe miscentering, then it matters at a higher resolution.
And is there any way to fix that?
The way to fix that is really to redo the particle picking, if possible, with the new templates that you have. Alternatively, you can somewhat manually, after you've done a refinement and now you know the position or the optimized position of the particle in every image, go back and calculate the center of the protein in every particle image and then re-extract the particles around those new centers. That's something that isn't a very well supported workflow in CryoSpark right now, but you can do that manually.
Great. I think that's pretty much the questions that we have at the moment. I just wanted to reiterate that we are really happy to receive everyone's questions. We've actually answered over 150 of them since the beginning of the CryoSpark tutorial. So thanks to the team for that. If we weren't able to get to your question today, we will definitely try and get to it tomorrow. I'm keeping note of the ones that we weren't able to answer today, but please feel free to continue asking. Also, it's not just today, you have access to us every day on the CryoSpark discussion forum, so please do feel free to post there as well. And also via email at feedback@structura.bio. I think it's perfect timing to go into a break.
Just before we go to break, I just want to tell everyone what we're going to be doing next, because it's probably the even more exciting part. So for those who are getting a little tired, stick around a little more. We're going to be going through ab-initio reconstruction to recover 3D structures from 2D images directly, refinement to get to high resolution, sharpening, local resolution estimation, and then in the slides, we'll be talking about some of the more advanced techniques that we'll go into depth in tomorrow, but give an example of ideas and how you can use them and kind of results that people can get in today's seminar.
Great, thank you. We'll pass it back to the Stanford team.
For a 10-minute break.
Yeah, yes, we can take a 10-minute break, and thank you for stop the screen sharing so I can. Thank you.
Great, thank you. I'll just start showing my slides again, one moment. Okay. Can you see my screen yet?
Not yet. Now I can.
Yes. Yeah.
Thank you.
Thank you. All right. Thanks to everyone who's listening and watching. We still have a fair bit to cover, so I will continue. We were going to have a section on performance and troubleshooting and data management, but we're going to move that to tomorrow now. What we're going to continue with is, now that we are finished 2D classification, moving forward into 3D reconstruction for single particle EM. And this is kind of the core problem for single particle reconstruction, and the place where we're actually gaining the most insight by aggregating the data from many different orientations, viewing directions to recover 3D structural information that we haven't directly observed in the images. What makes the problem difficult is interesting and important to keep in mind. First of all, we don't know which way we're looking at the particle in every 2D image that we have. There are 3 orientation parameters that we don't know and 2 shift parameters. We don't know the center of the particle in every image. There's also a very high noise level that's irreducible due to beam damage in each image. There may be many particles, 100,000 or more, or even millions in many cases. And, there's also corruption by the microscope transfer function, contrast transfer function, that may be different for every single particle image. There may be multiple conformational states present in the different particle images, or even multiple distinct particles entirely. And there may be flexibility or disorder of the molecule. So each particle image is different in that sense as well. All of these different problems are also things that we need to solve computationally now that we have the data in this form. And some cases, for example, flexibility, disorder, and conformational states, if we can deal with them properly computationally, they may actually be able to give us a lot more biological insight into the protein itself that we're looking at. That's really the overall aim of a single particle EM, is to extract that biological insight. So just to get into a little bit of math, really in a very shallow level of detail, overall, what we're trying to do, the way we set up the problem when we're doing 3D reconstructions, and this is common to almost all single particle EM approaches, or at least you can formulate almost all approaches in this kind of a framework. The way we look at the problem is a problem of inference, a problem of probabilistic inference, where we're shown a bunch of data in a certain way, a certain form, those are 2D images, and we're trying to infer an entity, a quantity, in this case a mathematical object, which is a 3D density, electron density map. So that's literally a grid of voxels, each one assigned a value, a floating point number, or a real number rather, describing the electron density at every point in the protein. We don't know what the electron density map is, but we're trying to find it. And we're trying to infer it from the images that we did see. There are also microscope settings that we may have seen, we can assume that we know at this point. Those are the CTF parameters and so on that we've talked about so far. And there's the unknown pose that we don't know for every particle image. So in this setup, what we're trying to do is think of this mathematical entity, the probability of seeing of a particular 3D structure given all the images that we saw. This object, this abstract mathematical notion of the probabilistic likelihood of having a given 3D structure, given all the images that we saw, that's what we want to optimize. We want to find the structure that's the most likely given the data that we saw. This arrow that in this diagram, which I won't explain too much, that connects all the variables, the image data, the microscope settings, the unknown pose, and the 3D structure, this forward arrow is what contains the image formation model. Everything we know about physics of the electron microscope, how projections work, the Ewald sphere, CTF aberrations, beam tilt, etc., is all contained in that one arrow. And we're trying to go backwards. Given the data, we know, given the structure, how to generate what the data should look like. Given the data, we want to infer the structure. What we do in practice, and again, this isn't necessary to fully grasp, but just to give an idea for those interested in the mathematical side of this, in order to actually find the structure that best explains the data, instead of thinking of that whole probability function, which is a very large and messy object, we're looking for just one thing, which is the maximum probability estimate of the 3D structure. We want to maximize the probability of the 3D structure given the data. And we're searching over all possible 3D structures, looking for that just one 3D structure that best explains the data. Different choices of how we set up V, like what I explained, V is just a 3D density, or maybe it's a different model, actually yield all of the different single particle reconstruction techniques that have been developed so far. So if V, instead of being a 3D structure, is a collection of 2D densities, that's 2D classification. If V is a single 3D structure, that's a refinement. If V is, I'll just go to the next slide. If V is a single 3D structure, that's a homogeneous refinement. If V is actually composed of a set of different 3D structures, where each image is drawn from one of those 3D structures, then we get the case of discrete heterogeneity. That's like 3D classification. If V is a composition of multiple 3D structures that can rotate relative to each other, we get things like local refinement or multi-body refinement. All of these different methods are actually all the same problem class that we're solving, which is inference. And in all cases, we have to solve this optimization problem. And that's kind of the core of 3D reconstruction in single particle analysis. Every algorithm is a way to solve this optimization problem, and every type of method is a certain model in which we're doing that optimization. So making this a little more concrete, what we're going to focus on first is kind of the first problem in single particle reconstruction, which is how do you get a 3D structure in the first place? How do you get a 3D structure from only having seen 2D images of the object? And that problem is something that we call and is widely known as ab-initio reconstruction, or reconstruction without knowing the structure already or having an initial model. The way we actually do it in practice is that in CryoSpark, we were able to invent an algorithm back in 2017 that was published in our first Nature Methods paper that's called stochastic gradient descent, or it's an application of an algorithm called stochastic gradient descent to the Cryo-EM reconstruction problem. Stochastic gradient descent is one out of a class of modern statistical optimization methods known as stochastic optimization. It's very successful in a lot of diverse optimization fields, and it powers all of modern deep learning in terms of actually being able to train neural networks. The same exact optimization problem or process is used. What stochastic optimization does is it's a way to solve this optimization problem by searching over the space of all 3D structures. So those are all the V's that we could possibly consider, and trying to find the one that maximizes this probability, this likelihood. That space, if we think of that actual objective function that we're looking at, it's not very neat in the sense that it may have multiple local optima. And this is a well-known problem in single particle cryo-EM. What it boils down to intuitively is that if you start with an incorrect initial model and you use a technique like refinement, 3D refinement in any program of your choice, all of those methods are what are called hill climbing or local optimization methods. They will start from the initial guess and climb the likelihood hill in the space of 3D structures to find the one that is optimal locally nearby to the starting point. So if we use standard refinement techniques in whichever program of your choice, we'll actually end up with an incorrect structure that's not the one that best explains the data, but just a locally optimal one where if you take that structure, there isn't really any way to change that structure that makes it look better, which is the definition of an optimum. But it's not a global optimum, it's just a local optimum and an incorrect structure. And there have been actually many cases, not very recently, but a few years ago, of cryo-EM structures solved where the final result ended up being wrong because the initial model was wrong. And that's a danger that we have with single particle EM, is that it is possible for a refinement technique to converge and give the wrong answer. And this is exactly why ab-initio reconstruction is so important. For new proteins or any kind of project that you're working on where you don't already know the structure of the protein that you're trying to solve, without this algorithm, there weren't really easy or straightforward ways to deal with that problem. You'd have to create either find a homology model or create an initial model from scratch by hand, or use some other technique like random conical tilt or some other imaging technique to try and get an initial 3D structure of your protein. That's no longer the case thanks to this algorithm that we were able to develop that actively searches over the space of 3D structures in a stochastic fashion. You can intuitively think of it as like bouncing around in that space, but in a way that's in a sort of guided and principled manner, which actually has some guarantees as well of convergence, in a way to search over the space of 3D structures to find the region of the optimum structure in terms of likelihood. So with stochastic optimization, what we call ab-initio reconstruction in CryoSpark, you can start with a random initialization that's completely wrong, and still resolve the final correct structure at least a coarse resolution. The algorithm is not designed to refine to high resolution, but just to find an initial model that's correct. In practice, it works very well across a wide range of molecules. I'll just explain a little more detail about what's going on in stochastic optimization. It's actually a very simple and kind of elegant idea. The notion is that the problem that we're trying to solve overall is this maximization over 3D structures of the probability of a 3D structure given all of the images in the whole data set. And n might be 100,000 in this case. That problem is difficult because we have to, in order to even measure the likelihood, the probability, we have to compare the volume V to all of the different images, of which there are so many, and then we could try to update V to make it a little bit more likely. Instead, in stochastic optimization, what we do is we take a random subset of the data. And the size of that random subset is a choice, and that's called a mini batch. We might choose 100 or 500 or 5, it could be a small number, of images. And what we do is in each iteration of stochastic optimization, we solve an approximate version of the whole problem where we're just looking at a few images. And for those few images, we try to compute what is a 3D structure that better explains those images relative to the one that we have right now. So we take a small step in the direction of the locally optimal structure for these images, and then repeat that with different random subsets of images. And the stochasticity introduced by this random selection, it turns out has some very beneficial properties. And overall, the algorithm is really neat because mathematically we can guarantee that it actually converges to an optimum of the overall problem, which I won't get into those kind of proofs right now, but that's a kind of interesting and important result, that it's still, even though we're doing something weird, we're still solving the original problem. But in practice, because this computation, each iteration now takes very little time, we only have to look at a few images, and we can do thousands of iterations in the same amount of time as we could of a single iteration before. Those small incremental changes repeatedly, many of them, add up to move us from the location of an incorrect initialization towards the correct structure of a protein, given the image data. So what that actually looks like in terms of on real data, these are some videos, hopefully they'll come through okay on the webcast, of ab-initio reconstruction applied to data sets of single particle EM proteins. The first one is a ribosome, starting with an initialization that's randomly generated. You can see here, hopefully that video loaded for you well. I'll just play it again. Oops, sorry, wrong direction. Just play it again. That the ribosome structure is generated from a random initialization just based on the data. The second one is an ATPase molecule. It's a dumbbell-shaped membrane protein. And again, from a random initialization, we can solve the entire structure from scratch without knowing anything about the protein or its overall shape or anything like that. Just the image data alone, using this algorithm, can resolve this initial model. And this is another example of a symmetric CryoEM molecule. And this is an interesting example because ab-initio reconstruction in this case is not aware that the protein is symmetric or that it has the shape at all. It just so happens that the most likely structure that explains the data is this symmetric structure. And we can go ahead and look at this ab-initio result after it's been computed and say, well, it definitely looks like there's symmetry. And then in later stages of processing, we can enforce that symmetry and use that to our advantage to get higher resolution results. So that's ab initio reconstruction to solve 3D reconstructions from scratch from 2D particle images for a single object in the sample. What's beautiful about ab initio reconstruction in CryoEM is that it actually we've extended it and it works very well in the heterogeneous case. It can actually solve multiple ab initio structures of multiple conformational states without any initial models and without assuming that the different states are similar to each other in any way. So you can have totally different molecules in the same sample and solve all their structures simultaneously, classifying particles as we go, and even solve multiple conformational states that are very different of the same molecule. What I'm going to do right now is actually switch over to CryoSpark so our practical students can start off an ab initio reconstruction. In order to do that, what we'll do is, actually I missed a step here. Step 1 should be select classes. What we'll do is we had our 2D classification runs from before, and hopefully if in your projects, at least one of them is finished. If the second one with more number of classes hasn't finished yet, it should have, but if it hasn't, then you can kill that job. We don't need it. We can take the output of our first 2D classification, create a select 2D classes job, take all the particles and all the class averages from our 2D classification, connect those, and queue up this job, which again is an interactive job that's just going to let us choose templates and particles that went into each class from 2D classification. In this case, we want to select all of the good-looking classes. And right now, the classes are arranged in order of their number of particles, which is often a relatively good proxy for the quality of the class. So I'm going to come up to here and right-click on this class and choose to select all the classes above this point. So that selects all of these. And I'll select this one as well. And all of these classes I'm going to ignore since they don't contain many particles and they are not my protein of interest. So I'm going to go ahead and click Done here. And what I have now is a selection of templates and particles, and I'll see in a second that I have 9,492 particles after this point. And then I will go ahead to the job builder again and choose an ab-initio reconstruction. All right. Just type ab dash, and you'll find ab-initio reconstruction in the 3D reconstruction section. So I'm going to go ahead and create one of those. I can take now the output of my select 2D. I just need the selected particles. Like I said, we don't need anything else. We don't need an initial volume. We don't need the 2D classes. We don't need anything else, just the raw data itself, particles. And the ab-initio reconstruction job has a number of parameters that we won't get into today. Those will be reserved for tomorrow. The most important parameter, of course, is the number of classes that we're going to look for, if we're looking for heterogeneity or not. And right now, we're just going to look for a single class. So we can go ahead and queue this job without changing any parameters. And that will start off our ab-initio reconstruction. We'll come back to this in a moment to see what it has done. This will take only about 4 or 5 minutes to run. I'll just show you at the beginning of the job, it starts off with a completely randomly generated initial density, just a bunch of randomly placed blobs as the starting point. So that could be arbitrarily wrong. And then it goes through many, many iterations of stochastic optimization very quickly. And we'll see as it continues that after a little while, it will have resolved our structure. It looks like it's already started to, in a few seconds, get the coarse overall shape of the proteasome from a random starting point, which is great to see. And you can look at these plots. They are three orthogonal slices through the 3D volume of our reconstructed density so far. So this is a slice through the middle, a slice through the middle the opposite way, and a slice through the center of the tube. So overall, this structure is like a barrel shape with 4 rings. And that's exactly what the proteasome looks like at a coarse resolution. And this job will continue until it has resolved more detail. In this case, it'll start to resolve the 7 subunits. You can also already start to see them showing up in this early stage here. And if we let it run for a few more minutes, it'll resolve a coarse resolution, maybe 8 or 10 extra resolution structure of our proteasome in just a few seconds. While that's going on, I'm going to go ahead and continue talking about ab-initio reconstruction. Like I said, what's really powerful about ab-initio reconstruction is that, and all of this is published in our 2017 Nature Methods paper where we first introduced this algorithm, is that it can be used for solving multiple conformational states at the same time, all from scratch without any initial models at all. So one example here is an ATPase molecule. We're actually going to be processing a subset of this data tomorrow. From an initial model that's been generated from an external source, you can use standard 3D classification techniques to tease out 2 different conformations, which are different rotations of the central stalk. In contrast, in CryoSpark, you can start with just the particles, no initial model, start with 3 random initializations in our ab-initio reconstruction job, basically by just changing that one parameter to 3. And what will happen is, the transitions here have been messed up, but what will happen is that those 3 different classes will all optimize together jointly at the same time, recovering 3 different conformational states of our molecule. And if we refine those, each of them, and cut a slice through the middle, we can see that the algorithm has actually found 3 different rotations of the central stalk of this ATPase, which is a rotary enzyme. This is an interesting case, but obviously in this case, the 3 structures are very similar to each other. So we would expect that more typical standard 3D classification approaches that all start from the same initial model could also find these differences. And that's probably true. But there are many other cases where ab-initio reconstruction is able to generate results that can't be had any other way. So for example, this is a structure that was published in 2017 of a AAA plus unfoldase, which at the time had never been seen in its active conformation. The team that was working on this actually purified this protein, anecdotally, as far as I'm aware, as a test sample for their microscope because it has a well-known 6-fold symmetric state, that's the inactive state, that's been crystallized. So it's a great test to see how good of a reconstruction you can get from your microscope and software setup. They created a sample, had 170,000 particles in there that they picked out. It was very crowded. This is actually something we're also going to be processing tomorrow to deal with the crowding situation and some advanced 2D classification. Using all those 170,000 particles, they just threw all of them into a 5-class ab initio reconstruction in CryoSpark. And what they found was very interesting. They found 2 low population junk classes, 1 class of 2 particles. These are probably missed picks where the picking has focused on the midpoint of 2 particles rather than a single particle. And then they found 2 larger classes. One, the 6-fold inactive symmetric state, 6-fold symmetric inactive state, well known of this unfoldase. And another one which seemed really odd and didn't have symmetry, but still showed the same overall protein structure. You could recognize it and it had something else attached. When they refined that structure, it turns out that they had found and isolated a state of the unfoldase unfolding its siblings in the ice. And this was just coincidental that when they prepared the sample, the concentration was so high, which they thought was a mistake, but the concentration was so high that in between blotting and freezing time, some of the unfoldase molecules had started to unravel their siblings in the sample. And then they were frozen. And that meant that they found a population of particles where the unfoldase was actually acting on a substrate, which was another unfoldase molecule. And they were able to see for the first time the unfolding mechanism and how the symmetry breaking happens in this unfoldase, which is a really nice story. And so ab initio reconstruction was critical in being able to find this conformational state that's both rare and unexpected. Another example, even more drastic, is data from a 2016 eLife paper about a holiday junction. I'm not too familiar with holiday junction biology, but this data set was very dirty, lots and lots of broken particles, junk, and very few intact holiday junctions. Starting from the entire data set that was used in the study, which for the 2016 paper was manually curated and processed through many weeks of processing and manual visualization and curation, we just took the entire particle stack, put it into a 5-class ab initio reconstruction in CryoSpark, and found 5 different structures appear, one of which was an intact holiday junction. The other 4, making up the majority of the particles, were broken bits of something. Taking the particles that went into this intact holiday junction, we did a further sub-classification using ab initio reconstruction again with 3 classes, and we're able to solve, again, 3 different states. 1, the intact structure, 2, a structure where some of the junction proteins had fallen off, and 3, one where one of the hairpins had broken off. And so with these final particles, we were able to get a refinement that was actually better than what was published in this paper, as far as I recall. And this is just, again, showing an example of the power of these algorithms to resolve heterogeneity, even when you can't define it or you don't know what all the classes look like, and you don't know how many there are. So we'll talk about more advanced 3D reconstruction with ab initio reconstruction tomorrow for multiple classes and so on. We won't actually do that with today's data set since it doesn't have any appreciable heterogeneity at this point. I should just mention that in CryoSpark, we also have an implementation of heterogeneous refinement, which is similar to standard 3D classification methods, where you start from 1 or more starting models, for example, from ab initio reconstruction, and they don't all have to be the same. They can be all different starting models, and this job will simultaneously refine and classify particles into the different classes. So you can end up with higher resolution conformational changes between classes, as well as better classification of the particles. And it's common practice to do a multi-class ab initio reconstruction and then do a heterogeneous refinement right afterward with the same outputs of ab initio reconstruction. So I'm just going to switch back to CryoSpark for a moment since our ab initio job here is now finished. In this case, we can see now that the final result here after 800 iterations or so, and the job figures out its convergence automatically. After 800 or so iterations, sorry, lost my mouse. 800 iterations, the structure has now resolved the overall T20S along with its clear 7-fold symmetry along the axis. Again, this ab initio reconstruction job does not know that the protein is symmetric, but based on the top and side views, it has constructed the 3D structure that best explains the data. We can actually look at that by downloading, downloading a 3D map from our ab initio reconstruction job by clicking this little download button in the volume output. And that will download straight to our browser. And I can open that on my laptop with UCSF Chimera. So I'll just pull over here. And also this one. And we can see that in just a couple of minutes, this reconstruction, ab initio reconstruction, has resolved our proteasome at coarse resolution, and enough for us to detect that there are 14 subunits that are, at least at this resolution, more or less similar. We may need to do a C1 refinement to really verify that there is symmetry that's strong enough to be worth enforcing. And then we can do a D7 refinement since we happen to know that this proteasome is D7 symmetric. So I'm actually going to have the practical students do that at this point. If your ab initio reconstruction is finished, even if it's not finished, in fact, and this is an important point about CryoSpark, is that even while jobs are running, you can take their outputs and connect them to other jobs and then queue up those new jobs. And the CryoSpark scheduler will automatically launch those secondary jobs once the first one's finished. In this way, you can construct a long chain of processing, queue it once, and then just let it run overnight or what have you to process a lot of stuff. So I'm going to start a refinement job. And here, there are also a number of refinement methods implemented in CryoSpark. We're going to choose homogeneous refinement, new. There's also a legacy implementation that's still there. It's slower and older. It's still there just for compatibility reasons, but everyone should be using the homogeneous refinement, new job type at this point. And to it, I'm going to connect all the particles from my ab initio reconstruction and the starting volume from ab initio reconstruction. And in this case, I'm just going to go ahead and apply D7 symmetry as the one parameter that I'm going to change. And we won't be changing.
Fair question at this point. Why did we do 2D classification if we're not going to use that particle stack for ab initio reconstruction?
We did actually. So in the workflow that I showed, we did use 2D classification. We completed the 2D classification. Then we used a select 2D job from which we selected all the good looking classes. And along with that, behind the scenes, the select 2D job also separated for us all of the particles that went into those good classes. So in my case, I had 29 classes that I rejected, and those had 221 particles. And I also had 21 classes that I accepted, and those had 9,492 particles. So I only used these particles in my ab initio reconstruction job. If I show you the tree view, that might be more clear. What happened here is that I asked everyone to run 2 2D classifications in parallel, but I only used the output of one of them. I did the select 2D, only those particles went into ab initio reconstruction, and now only the particles that came out of ab initio reconstruction, which are the same 9,492, so that's post 2D classification, are going into the refinement. So we are using the output of our 2D classification in that sense.
Great,
what I meant to say before is that ab initio reconstruction doesn't actually use the templates. It doesn't care which particles went into which 2D classes, and that information is not used for constructing the 3D reconstruction.
Okay, and one more question here. Can you please explain why we did 2 2D classification jobs with different number of classes?
Sure, actually the reason for that is that I wanted to show everyone what happens when you use more classes or less on the same data. We just haven't had a chance to come back to look at that yet. So let me do that in one moment. I'll just have everyone start off this refinement job with D7 symmetry. Again, this is a homogeneous refinement new. It's using the particles from ab initio reconstruction and the volume from ab initio reconstruction. And we can go ahead and queue that. And now while that's running, I'll just show you the difference between these 2D classifications that we did in parallel. So the first one, which was done with only 50 classes, I will open this image in a new tab, so we can come back to that. And the other one was done with 100 classes. So we can see the difference now between these. I'll flip between the images. Maybe I can zoom out a little. Sorry. So what we can see is that in the 50 class version, we have a bunch of, good-looking classes and some very poorly populated, bad-looking classes. In the 100 class version, we have a bit more diversity of different classes that we found. So for example, we have multiple oblique tilted views that are a little more rare, even oblique tilted views from slightly different angles like this one. We also have many more poor classes that have few particles but in different configurations. We also have some classes where we've started to resolve not only a protein molecule but also its relationship to a neighbor. And that's actually something we don't want, and that's an advanced topic we'll cover tomorrow. We really want to focus on individual proteins, not pairs of them or triplets. And we've resolved, for example, proteins that have a gold nanoparticle beside them. We just have a wider diversity of sampling of the different conformations or views that are present. So with more classes, we always will achieve that sort of stratification of the particles into more classes. And that can be helpful, especially with larger data sets where we're looking at more different views for, let's say, an asymmetric molecule. So that's what I wanted to show. Okay, that is it for ab-initio reconstruction and refinement, or refinement we're coming to next. So high resolution refinement is the next step of single particle processing. And ab-initio reconstruction, which we've talked about already, can only get us to a coarse, low resolution reconstruction. And that is due to the way the algorithm is set up. It can solve the initial model problem, but it can't actually resolve high resolution detail from all the images at the same time. That's where an algorithm called iterative refinement is necessary that can proceed to recover that high resolution detail. In the past, this iterative refinement technique or method has been computationally very expensive, using hours or days, in the past even weeks or months of multi-CPU cluster time, multi-node time on CPU clusters. Nowadays with GPUs and better implementations, other programs can do it now in hours or days. And there may be many refinements in a complicated CryoEM workflow. In CryoSpark, we've developed a new method, a new algorithm, which is, I mean, it's not new anymore. It was part of also our 2017 Nature Methods publication. It's a technique that massively minimizes the computational burden of high resolution refinement, allowing us to do refinements of large data sets up to high resolution in minutes, and obviates a lot of the redundant computation that happens in other approaches. We've already started our refinement jobs, so we can continue with these slides to explain how our technique works. First of all, it's important to understand that in the refinement process, what we need to do is take an initial model of our 3D structure and take all of our images, for which we may have 100,000 or more. For each image, search over all the possible ways that the image and 3D structure could be aligned. So that's 5 dimensions of pose space. Search over that space to find the one pose that is most likely given the image and the current reference structure. So we're trying to find that image alignment. And then using that image alignment for all the images, we can reconstruct a new structure, which is an improved version of the old structure, and then repeat the loop. Align, reconstruct, align, reconstruct. That's what iterative refinement is all about. And of course, there's mathematical ways to write that down in terms of expectation maximization and so on, but I won't get into that right now. The most expensive part by far of a refinement technique is the pose search. Because like I said, for every image, we have to search over 5 dimensions of pose. We have to look at every direction, viewing direction, to see which way are we looking at the protein, every possible 2D shift and all combinations of those. And existing techniques have all solved this problem either exhaustively by literally scanning over all possible views to find the one that best matches, or locally by taking either a previous guess or some other estimate of the pose and only searching nearby poses, a few degrees this way, a few degrees that way. Both of those techniques have their drawbacks. Exhaustive searching is just excruciatingly slow, and local searches can get stuck in a locally optimum looking pose that may be totally incorrect as the structure improves. So in CryoSpark, we were able to develop a new technique, a mathematical optimization procedure using a concept called branch and bound, which is a sort of classic algorithm design principle. The idea of branch and bound for alignment in a simplified one-dimensional sort of figurative world, we can think of the space of poses, all the different 3D poses that we're looking for. And we can think of this dashed line, which is the actual error, what we call image alignment error, between the observed image and a projection of the 3D structure that we currently have from a particular pose. So what we're trying to do is search over this pose space to find the one pose that has the minimum alignment error, that's the optimal pose. Now this dashed line is very expensive to compute. It's the true error function where we have to literally take our 3D structure, project it in some direction, take our 2D image, compare them, add up the differences of all the values and sum those all together and finally get this image alignment error. Very expensive to compute. So we don't really want to compute the whole thing and then find the minimum. Instead, in the branch and bound approach, what we can do is if we can cleverly think of a different function that we'll call a lower bound, some different function that's inexpensive to compute, but is guaranteed to always be less than the dashed line. That's what we call our lower bound. And figuring out what that function is the hard part of deriving this algorithm that we were able to do. And secondly, pick one point on that lower bound, let's say the minimum of the lower bound, and evaluate the true error one time at this point. That forms what we call an upper bound. What we can say after having computed the red line and the blue line is that we know that the dashed line is always above the red line. So we know that the error at our optimal pose has to be above the red line everywhere. And because we've computed the true error at one point, we know that the minimum error has to be less than that one point. I mean, if it wasn't, then that would be the minimum. So we know that the minimum error is less than this dot. And that means somewhere between this blue line and the red line lies our optimum. And all of a sudden, by computing this lower bound, which is ideally inexpensive, and one upper bound, we've shrunk our space of candidate poses that could possibly be the correct alignment to a very small set. We can then repeat this procedure with candidates from this first iteration of branch and bound with another lower bound that's still inexpensive, but a little bit tighter, a little closer to the gray line, another upper bound, and so on, and repeat that, over and over until we keep shrinking the set of candidate poses. And this is an optimization strategy for doing this kind of search that's highly effective in a lot of fields and is equally powerful in single particle EM, where we can now, using this technique, align 2D images and 3D structures in a matter of milliseconds. So for example, this is an image of a ATPase molecule, and this is the actual reference structure. And we're trying to find which way should we rotate this reference structure to look like this image. The true alignment error is this large function over the space of viewing directions. It's projected on a globe. And the optimal pose is this red hotspot where the image alignment error is minimized. We don't want to compute this whole function though. So instead, we compute the lower bound everywhere. It's very inexpensive to compute. And I won't go into what the lower bound is, but it's essentially a way of using only certain Fourier components at certain times and computing some other extra terms that account for the higher resolution Fourier components to compute this lower bound. So that lower bound looks like it has lots of great red regions that may be the optimum. And then we compute that one upper bound, and using a lower bound at a certain level, we can call down the space of poses to this gray region. And that took very little computation. Now, only in this gray region, we can start to evaluate the next level of lower bound and cull it down again, and then again, until we've now narrowed down our possible search space of the optimal pose to this tiny region, doing almost no computation at all compared to the exhaustive version of the search. The two great things about this technique are that, first of all, we've done a global search over poses. We haven't assumed that we're looking at the protein from any angle. We could find any result, but we don't have to do any of the extra computation that has been done in other methods. And this is what makes CryoSpark so fast. The same technique is used in 3D reconstruction, in 3D refinement, in 2D classification, and every time we have to do image alignment or search. So overall, what that means is that branch and bound dramatically reduces the computation required without any loss in quality, since we're not actually we're not losing or we're not changing the result. We're just reducing the computational burden of finding the result. And we can refine structures and reconstruct them to high resolution in minutes. So for example, this benchmark data set of 105,000 ribosome particles that refines to 3.2 angstroms can be done in just 11 minutes now on a single NVIDIA GPU. For comparison, that's according to the, for example, Relion, which is another GPU accelerated CryoEM computational tool from an academic lab that's developed in an academic context, is about, according to their benchmarks, about 20 times slower on the same hardware for the same benchmark data set. On large data sets and on real projects where you have to iterate through many refinements to get a high resolution structure, this is particularly important because it dramatically cuts down the time to get a reconstruction. So all these techniques together are what have allowed us to, well, part of what has made CryoSpark so popular and widely adopted, and with its adoption growing very fast, but also allowed us to construct some new overall methods that rely on these building blocks, One of them that I'll just touch on very briefly is CryoSpark Live, which is our newest addition to the suite of things that we're trying to build. CryoSpark Live is a real-time 3D reconstruction engine for doing data processing on the fly. And it does all the pre-processing that we talked about, patch-based motion, CTF estimation, particle picking in various ways, 2D classification in real time, and 3D refinement in real time with data collection. So as images are coming out of the microscope, we can extract them, pick them, cut them out, do 2D classification, select the 2D classes, and then have those particles that are good according to our 2D classification be used in a streaming refinement that updates every few minutes every time new particles are seen from the microscope. And this is a great way, this is now being used widely by several of the largest facilities that do single particle EM data collection, even for external users. And it can be used for many purposes, especially for identifying regions of a grid or square that are better than others based on 2D and 3D reconstructions, and for getting an initial reconstruction that can be used for downstream processing immediately as soon as a data collection session is finished. That's especially useful in contexts where the pace of data collection is high and the pace of solving structures needs to be high as well. Okay, and I think that's where I'm going to pause at the moment and switch back to questions, or if we can just quickly look at our CryoSpark window. Our refinement may be complete, so this refinement that I've just done has finally got us to a 2.9 angstrom reconstructed map. I'll just download this result for everyone to see. We'll talk about, depending on whether we have time today or not, we'll talk about interpreting all the different plots that come out of a refinement and various parameters that can be changed. All of that stuff will also be discussed tomorrow in the more advanced session. Yeah, that's a refinement in CryoSpark. Obviously, in this case, we're using a relatively small amount of data, so we would expect this to be fast anyway, but I can just open this map in Chimera once more. And this time we will see our nice 2.9 angstrom structure where we can zoom in and look at interior of the helices and beta sheets, lots of side chain detail, and even maybe some water molecules, but maybe not at this resolution. Great.
Great. We do have a few questions. So first of all, with respect to ab-initio reconstruction, should we or should we not enforce symmetry if we know something about the symmetry of the particle, and let's say in the case of a large virus?
Great. Viruses are definitely a special case. What's important to think of for symmetry is that when you have a highly symmetric molecule, many of its views end up looking very similar. And so, for example, if you think of a virus, if you have, let's say, icosahedral symmetry, all the views that you can get at a coarse resolution pretty much look like spheres. And there's very little alignable information at that resolution where ab-initio reconstruction is working. So what ab-initio reconstruction ends up doing, and if you just think intuitively of what would this algorithm try to do, it's trying to come up with a 3D structure, not knowing the symmetry, a 3D structure that best explains all the data. But all the images kind of look the same. They're pretty much just circles. And so the simplest, easiest 3D structure that explains all those images is a donut. That projected all in one direction creates that low resolution version of the virus. And that's exactly what we don't want, since obviously we know that the virus is a shell, not a donut or a ring. But ab-initio reconstruction doesn't know anything about the structure, and it doesn't assume anything about the structure. So not enforcing symmetry in a virus case, you probably won't end up with a ab-initio reconstruction that works. It is possible depending on playing with the parameters and what have you, but most of the time you want to enforce symmetry in that case, especially if you know the symmetry of the virus. On the other hand, if you have lower symmetries, like any kind of C or D symmetry that's sort of reasonable, even for example, this proteasome, which is 14-fold symmetric, you want to not enforce symmetry as far as possible until you can be sure by, for example, doing a C1 refinement that the reconstruction actually does have symmetric properties. And then you want to enforce the symmetry. In ab-initio reconstruction, it turns out in those lower symmetry cases, if you enforce the symmetry, that can actually create local optima and sort of sticking points that ab-initio reconstruction can't break out of. So for example, the proteasome, if you enforce symmetry and at the initial iterations of optimization, ab-initio reconstruction starts to think that the particle is, if this is the z-axis, the particle is, the long axis is across that. the symmetrization operator will turn that structure into a 7-sided star shape. And immediately after that, ab-initio reconstruction can't really make the huge change to rotate the structure along the symmetry axes, and it'll get stuck in this star-shaped multiple copies of the proteasome land where it can't escape from. So it's always best, if you can, to not enforce symmetry. One of the important things that we'll discuss also tomorrow about ab-initio reconstruction is that you can generally assess some degree of confidence in the structure, either because you know what the structure looks like or based on viewing directions. And in this case, with this highly symmetric molecule, that's not a good example, but with other molecules that are less symmetric or other shapes, the viewing direction plot distribution helps understand whether or not ab-initio reconstruction is actually constructing a 3D structure from many different viewpoints, or for example, in the case of the virus, it's just constructed a structure that only looks right from one direction for a few images. And so we'll discuss that tomorrow.
Okay, Ali, in that case there, where where you just showed the orientations, the orientation distribution,
Yeah.
I would have expected, since from the top it's got sevenfold symmetry, I would have expected 7 peaks along the equatorial band, where it could have found any one of 7 different ways, which would have been good. And this looks like it's picking one direction from the side. Wouldn't that, I would have expected that to have an elongated missing wedge sort of thing.
Yeah, definitely. To be honest, I feel like this plot is not making a lot of intuitive sense to me either. I did also expect an equatorial band. I think, let me see what the refinement has.
Yeah, that's cool. That's
This is more.
That's perfect. That's that's what you expect. Top views and a whole bunch of side views in all the different possible directions. Why did that other one show that?
I'm honestly not sure. We may need to investigate this a little bit, but I mean, the structure is obviously correct. And
oh yeah, from the top it's sevenfold, but from the side you can't tell that was sevenfold.
Exactly. So I'm not sure. But we'll have to look into that a little. It is reassuring that in the refinement we do get the right.
Eventually, yeah. And obviously, if you enforce it, it's gonna that one's the enforced one, of course.
Actually, the orientation distribution here, we don't actually use the symmetry during the alignment stage in CryoSpark. So each particle is allowed to align at any position around the sphere, around the viewing sphere.
Okay, so it's not the 1/7 of the rotation, but that's all the rotations. Okay, exactly. But still, then the other one doesn't make sense.
Yeah, the other one doesn't make sense. Some things, we'll have to look into that. Thanks for pointing that out.
Okay.
Other notes about ab initio reconstruction. Is there a resolution limit that we should be using or enforcing?
Yes, so ab initio reconstruction has no notion of measuring resolution. In fact, the optimization technique is set up where you tell ab initio reconstruction what resolutions it's allowed to consider while it's optimizing, but it can't tell you whether there's statistically significant signal at any particular resolution. The resolution limits do matter a lot though, especially for smaller particles. So our default tuning of the algorithm is set to use an initial resolution of 35 angstroms and a maximum resolution of 12 angstroms. But for small particles at 12 angstroms, even at 12 angstroms, the whole object may still look more or less like a sphere, in which case there's nothing really to align. And at 12 angstroms, like if you're looking at a very small membrane protein or something, you actually won't be able to get an accurate ab initio reconstruction with these settings. So you have to increase both the resolutions to smaller numeric values. So for example, you could do initial resolution of 15 angstroms and maximum resolution of 6 angstroms. Computationally, that's a little more expensive, but for smaller particles or for very highly symmetric things like apoferritins and so on, where again, at lower resolutions, they just look like spheres, those changes are necessary.
Thank you.
But again, it's not a resolution estimate. It's just a limit for the algorithm. Yeah.
Perfect. In the case of heterogeneity, if you're not quite sure about the heterogeneity within your data set, how many classes should you specify for an ab initio reconstruction? And how long does a 5-class ab initio reconstruction take?
That's a great question. So you should probably try in parallel multiple numbers of classes. The reason is that ab initio reconstruction doesn't assume anything about the number of classes. So it is perfectly able to find a solution where, let's say you asked it for 5 classes and 2 of them will be empty. Like they'll have almost 0 particles classified to that class at the end of the day. So in that way, you can sort of detect the number of distinguishable classes, at least for this algorithm. There may be other conformational changes that ab initio reconstruction can't distinguish. So you should generally try until you start to either find some empty classes, or another phenomenon that I was going to talk about more in detail tomorrow is that ab initio reconstruction, again, not knowing anything about the 3D structures, can actually take your particles, like for example, with this proteasome is a great example, and instead of classifying them based on their conformation, classify them based on their viewing direction. So for example, the proteasome, if you do a 2-class ab initio, you're highly likely to get one structure that absorbs all the top views and becomes just a small round donut of top views, and another structure that takes up all the side views and becomes like a ladder, just a flat 4 lines thing that from one direction looks like the side view of the proteasome at low resolution. And those are the two conformations that it separates. Again, because it doesn't actually know anything about the 3D structures, and it can't enforce any bias since it doesn't have any. So once you start to see viewing directions separating, which again you can diagnose by the viewing direction distributions, then you know that ab initio reconstruction is now splitting hairs and turning things that should have been one class into multiple classes in an incorrect way. But that's something that you have to do by trial and error on each data set. And yeah, it's recommended to do a 1 class, 2, 3, 5, 7, as many as you want. In terms of the runtime, I'm not sure if I actually recall the runtime for a 5-class ab initio reconstruction, but it does depend on the number of particles. I would say a 3-class ab initio reconstruction for 100,000 particles probably takes something like 30 or 40 minutes. But don't quote me on that. It's probably in that ballpark though.
Great. I'm going to move on to a few questions about refinement specifically. Why did we choose D7 symmetry for the T20S dataset?
In this case, because the protein has a well-known D7 14-fold symmetry. We knew it already, so we enforced it, and that helps us get a much higher resolution. You can actually try, and for those doing the practical, you can try creating a clone of this homogeneous refinement job. I'll just do that right now, where you don't enforce symmetry at all. And so it's a C1 reconstruction, and see what that does. And you'll find that it still resolves the same proteasome, but just at a very much lower resolution because the protein actually is symmetric, at least to this resolution. We can use each experimental image as 14 different observations for the same subunit that's repeated 14 times in the molecule. So each image counts 14 times as much as if we had collected 140,000 images of an asymmetric protein, getting the same result here. And so because we need the symmetry, we can enforce it. If we didn't know the symmetry, we would always do a C1 refinement first, find out what the structure looks like, and then decide if we want to enforce the symmetry. In a lot of cases, you may have pseudo-symmetry. Like for example, many people are processing the coronavirus 2 spike protein that is, parts of it at least are C3 symmetric. And the actual receptor binding domain often breaks the symmetry because of its flexibility. And so if you don't apply symmetry in that case, you're likely to start to align particles so that whichever of the receptor binding domains is in the up position, they all start to align across all the images. On the other hand, if you do enforce the symmetry, you can get a much higher resolution structure of the part that is symmetric. And so it depends on the data set and depends on what you're doing.
Thanks. Can you show us again how we can queue up a chain of jobs and just let them run?
Sure.
Let's say in a case where we don't have all of our resources available, or we already know kind of what we want to do and we just want to queue up some jobs and go do something else.
So right now I have this job number 33 that's in running status. So it's not finished and I can't use the outputs, or the outputs are not ready for me to actually use since they haven't been created yet. But what I can do is create another job. Let's say I'm doing a heterogeneous refinement. So I can start a heterogeneous refinement, and this job number 33, which like I said is still in running status, I can inspect it and its outputs still show on the right-hand side, but they're not final. They're outputs from an intermediate iteration. What I can do is take those outputs, like the particles, and connect them to my heterogeneous refinement, take the volume and connect it to my heterogeneous refinement maybe 3 times to start off a 3-way classification, set up any parameters, and queue this refinement job. Sorry, heterogeneous refinement job. And what that is going to do is, oh, sorry, the refinement already finished, so that was a bad idea. Let me stop this and clear this as well. I'll just run this refinement again so that it's still running instead of completed. And I will now start off this heterogeneous refinement. So now what we see is that if I go over the cards view and scroll down, the refinement that's running, job number 33, is a parent of job number 34. But job number 34 is in queued status and it stays there and it says waiting because inputs are not ready. And that job will continue to sit there and wait until the previous refinement job is finished. And in fact, we can continue doing this chaining, like this heterogeneous refinement, even though it hasn't even started yet, still reports all the different outputs that it's going to create. It hasn't created any of them yet. The count is 0 for all of them. But we can still go ahead and let's say we want to further refine one of the subclasses that we're going to find here, or all of them. Then we can go ahead and connect particles from class 0, volumes from class 0 to this refinement and queue that as well. And now we have a chain of 3 jobs that if we look at our tree view are all connected together and waiting for each other. So this refinement will finish, this heterogeneous refinement will run, and then this refinement will run. We can even create multiple refinements here to refine each of the different classes that come out of the heterogeneous refinement, and those will start up and run in parallel as soon as the heterogeneous refinement is done.
Perfect. Okay, going back a little bit to ab initio reconstruction and the influence of your particle stack. How forgiving is the ab initio reconstruction? We did a 2D class selection to help and then got a refinement to 2.92 angstroms. If we use all the particles from our 2D classification in ab initio reconstruction, I'm assuming this means without actually selecting a good subset, and refine that, how bad would that be?
That's a great question. Ab initio reconstruction is surprisingly robust to outlying particles, so junk particles. In fact, many groups have a strategy of not even doing 2D classification in a lot of cases and taking all of their particles and going straight to a multi-class ab initio reconstruction. For some reason that's not completely understood by us yet, doing classification in 3D, especially with ab initio reconstruction, can often be more powerful and selective in a single round than 2D classification. Somehow in ab initio reconstruction, when you get one class converging to the correct structure, and it may be that in that case, you only need 20 or 30% of the particles to be true particles, the other 70% can be junk. One class will converge to absorb all of those good particles, and the other classes will turn into wacky shapes that absorb all the junk particles from different viewing directions. We're still not sure why that works so much better than 2D classification, but in a lot of cases it does. So it's highly recommended to use ab initio reconstruction as a way to sort out good and bad particles as well. And many people do that in practice. Another common strategy is to take all your particles, maybe do 2D classification once just to get rid of the really obvious junk, feed it to a, let's say, 3 or 5 class ab initio reconstruction, and then take all of those particles and use them in a 5-way heterogeneous refinement, which has been seeded not only with the good classes from ab initio reconstruction, but also the bad ones. And that heterogeneous refinement will also classify particles between the different structures, one of them being the intact particle and the other ones being junk, and make a even more robust way of separating junk from good particles. But that again is a really dataset dependent type of thing that has to be tried experimentally.
Perfect. Another question in a similar vein. How might ab initio reconstruction work for a heterogeneous protein cage wherein you might have some cage samples with 1 or 2 subunits missing? Presumably, those particles would be weeded out during particle picking since they would look different in the 2D class relative to a complete cage, correct? And I think a little bit, for a little bit more context, maybe what we can kind of get into here is how sensitive is ab initio reconstruction or multi-class ab initio ab initio reconstruction to the differences or similarities between the particles in the data set?
That's a great question. I think the cage example is sort of special because the cages, like viruses, are often shell-like at a low resolution, kind of spherical, and the missing subunits in a cage often you could think of as a pseudosymmetry, where still the rest of the cage is more or less symmetric. And assuming I'm understanding the data context right, I haven't done too much with cages, but what you would kind of expect to see in that case is that ab initio reconstruction wouldn't be very good at separating the complete cages from the incomplete cages because the incomplete cages still look very much like the complete cage except for a missing subunit or 2. And so they're much more similar to the complete cage than they are to each other unless you can already align the pseudo-symmetries of, like, let's say you have two cages, both missing two subunits. If they're misaligned, they look less like each other than they both look like a complete cage. Only if they're already aligned do they look more like each other than they do to a complete cage. And so ab-initio reconstruction, not knowing anything about the structures ahead of time, is probably highly unlikely to find the complete cage and the incomplete cages. You can definitely classify cages of different sizes or different assemblies that end up looking different no matter what. But missing subunits is not too easy, unless the missing subunits dramatically change the conformation of the cage. Hopefully that's enough of an answer. There is some more advanced detail about parameters that you can change to make ab-initio reconstruction more or less sensitive to smaller or larger conformational differences between structures, but that's going to come tomorrow in the advanced section.
Wonderful. We just have a few more questions, I think, to kind of wrap this up. One is going back to 2D classification. You mentioned that the 2D classification algorithm scales well with dataset size. Is this big O and log n 2D classification?
It's actually linear. It's actually just linear in the number of particles. It's technically it's quadratic in the number of, well, it's actually like O of n times k, where n is the number of particles and k is the number of classes. And in practice, it ends up being more like, it ends up being a little more than linearly dependent on the number of classes because of the way online expectation maximization works. Iterations of refinement will need to use fewer particles at the beginning if there are less classes. So when you increase the number of classes, not only do you make the computation bigger, you also need to look at a larger n at the early iterations. The final iterations of online expectation maximization use the entire data set, and so they are only dependent on n times k. But the overall runtime can actually appear to get faster more than linearly as you decrease the number of k, the number of classes. Hopefully that answers the question.
Perfect. Just a few more questions to wrap up refinement. First of all, is there a way to increase the number of iterations in refinement?
Yes, you can change the advanced parameters to add more iterations. So for example, you can go to the parameters and choose number of extra final passes. And after the refinement algorithm has detected convergence based on resolution estimation, it will continue for a certain number of iterations. That generally doesn't hurt. You can tend to always add 4 or 5 if you don't really mind a few extra minutes or time spent. And that can sometimes be beneficial. There are lots of other advanced parameters that, again, I'm hoping to talk about tomorrow for making refinement work better in some cases.
Perfect. Is it possible to use an external volume with a different pixel size as a template for refinement?
Definitely. You can use the import 3D volumes job and import any volume with any pixel size and box size, and then you can use the volume tools to take that input box size and pixel size, crop it, resample it, either upsample or downsample to the same box and pixel size as your protein, your target, or your particles, and then use that as a reference.
Perfect. And finally, we have a user who actually has experimented with 2 homogeneous refinement jobs, one where they applied C1 symmetry, both in the case of the T20S proteasome, and the other where they applied D7 symmetry and got a drastic difference in resolution with the D7 symmetry, which was 2.92 angstroms. So can you please comment on the difference?
So the difference is due to several factors, mainly that in the D7 case, you literally have 14 times as much signal as you do in the C1 case. In the C1 case, every experimental image only counts from a single viewing direction. In the D7 case, because we know there are 14 identical subunits, every experimental image contains information about all 14 of those subunits. And because we know they're identical, it's the same thing as saying that each image is actually 14 images of this asymmetric unit. And so in effect, when you're enforcing the symmetry, you have 14 times as much, because of the D7 symmetry, 14 times as much signal. And that alone is the largest part of the contribution, but that actually ends up causing a snowball effect where with the C1 symmetry, initial refinement iterations are so low in resolution that there isn't even enough structural characteristics in the C1 result to align images well. And that causes a kind of chain reaction that later iterations don't actually improve the resolution much because we can't align the images because the reference is so bad. And a way, it could be possible that if you start off the C1 refinement and use set the initial resolution cutoff of the initial model to a higher resolution, that could help in forging the initial alignments in the C1 symmetry a little bit better. But overall, you would expect it to be much, much worse than the D7 case.
Perfect. I think that's all that we have time for at the moment. So perhaps we can call it a day for the webinar portion and move on to meeting with our practical participants as well.
We actually have, unfortunately, we did have a lot more to cover in today's plan about sort of more advanced topics, measuring resolution, orientation distribution, CTF refinement, high resolution refinements, local resolution and filtering, non-uniform refinement, and stuff like that. And even flexible proteins and stuff, and some case studies. But I think we'll just go over those tomorrow at this point, since we're already at quite a late time.
Yeah, Ali, that has been wonderful. Same as Sarah, being able to digest all the questions and pose it to Ali. I enjoy. I learn a lot listening to you. Thank you very much. So I think in view of the time, I wonder whether we could call it off today, and maybe we can start a bit early tomorrow, since most of the registered participants probably will be here. Some of them are different time zones. So I would suggest perhaps we can start tomorrow at 8:30 with a question and answer to start with, and then you resume your tutorial. Would that work okay, Ali?
I think that sounds like a good plan. Yeah, I think everyone's a little bit exhausted at this point. So
that has been wonderful and a lot to digest.
For sure.
And I'm impressed that you're able to talk continuously, basically, for several hours. So
I don't do it too often, but I'm
yeah,
glad
no,
I was able to
really,
start.
that's a great treat to us. So with all the audience, for those of you who can get up early, well, depends on where you are. And then we'll start at 8:30, and the formal tutorial will start at 9 o'clock tomorrow.
Great, awesome.
Okay, and the participants are getting now a questionnaire, which we would love to have your responses and your feedback for Ali and for the lecture that we had this morning from David. We would love to hear from that, and we look forward to your responses. And I second the having fielded the questions from the morning lecture. I'm really impressed with how Sarah and all of the other people answering the questions in the background have fielded, interpreted, and filtered all the questions. It was a fantastic job to all of you.
Awesome.
Thank you. Well, we're really excited for day two rather. So we'll see everyone tomorrow.
See everyone tomorrow. Take care.
Take care.
Have a great evening.
Thank you.
All right.
Thank you.
Hey, Waj, shall we talk now?
Yeah, that's good. Why don't I set up a separate Zoom, or in the same Zoom?
No, we'll use a separate one.
Separate, right?
Yeah.
Okay, I send you a Zoom link, okay, because there's something teaching need today, so.
Cheers.
Yeah, okay, I call you in a minute, thanks.
Bye.